Welcome everybody for the refree track session, and take it away.
Okay. So, hello everyone. My name is Alessandro Carminati from Red Hat, and this talk is about understanding the BSP behind their demo purpose and how to map safely into the main line. So, here's the plan. What a BSP really is, how to make sense of one you didn't write, and how to separate real hardware support from noise. Finally, how to turn that upstreamable work while keeping BSP stable along the way. So let's begin with the first section, understand the BSP. And to warm us up, the first thing everyone learns about BSP is that they are like a bit novels written by someone else. You open them and you are sure there's a plot. You're just not entirely sure where it starts. Let's take a closer look to what a BSP actually is and what isn't. A BSP is a snapshot taken at bring-up time, enough to prove the silicon works, not designed for the kernel evolution. It mixes real enablement, shortcuts, and frozen dependencies. Our work is to figuring out what can survive in the main line. Sorry. Once shipped, the BSP freezes on an LTS baseline. Upstream moves, subsystem evolves, and none of that flows into the BSP back. The result is a growing divergence, and over the time, the cost of rebasing, the cost of rebasing it becomes prohibitive. The good news is that divergence can be understood, controlled, and eventually eliminated through upstreaming. BSP arrives in very different shapes. Sometimes as a clean Git tree, sometimes as a Yocto patch stack, sometimes my favorite, both of them at once, and sometimes as a vendor tarball with no history at all. Regardless of the format, they all mix real hardware support, backports, refactor, and long-dead experiment. And because upstreaming is the only sustainable endpoint, the first step is always the same, figuring out what a BSP actually contains and reduce it to the parts that really matters. Understanding what is relevant and what is noise is the foundation of everything that follows. Device tree bindings are designed around the IP families idea. The kernel documentation explicitly say, do use fallback compatibilities when devices are same as or a subset of prior implementation. And this is important for us because it means that identify lineage is not a guesswork. It is part of the DT models. We are not declaring equivalence, but we are allowed to use family-level hints to understand where the upstream support might exist. Bindings are essentially the catalog of the upstream supported IP. Many common blocks like UART, timers, IO controller already exist there. What is actually missing is the SOC-specific integration, clocks, resets, power domain, PIN-max. Bindings describe expectation, not the full glue. Making that distinction earlier prevents us from chasing proprietary ghost. It also gives us the vocabulary to reason about what upstreaming drivers may be relevant and which part need a new support. Fast walk through the BSP tree already reveals a lot. Vendor-only directories, duplicate frameworks, and kconfig option that doesn't exist upstream. This pattern tells you where the maintenance burden live, which subsystem have forked, and which driver will almost certainly need extra attention later. One of the early challenge with a vendor BSP is that many IP blocks that look new are actually familiar. They are just renamed, wrapped, or slightly revised. Vendors reuse common IP, but changes offset, IRQ lines, and the glue logic around them, which hides the upstream lineage if you only look at the compatibles, sorry. And compatibles themselves aren't always a reliable indicator. A lot of vendor string predate the T-schema convention, so you will see mismatches even when the hardware family is the same. If you never run a DT binding check target on a vendor BSP, you can picture it like a spell checker on a Shakespeare. It doesn't tell you that Shakespeare is wrong. It just tells you that the spell checker wasn't invented yet. Schema validation is therefore noisy, and that noise mostly reflects how the BSP binding drifted over the time, not whether the hardware is unique. All this means that shallow check, names, compatibles, simple diff can reliably tells you what truly new. We need a deeper and structural analysis to separate the real deltas from inherited EP. Once you step into the vendor tree, the landscape changes quickly. Names drift, compatible drift, and sometimes you find files that feel much older than the base kernel you are dealing with. From here on is archaeology to reconstruct what the BSP really contains. You often inherit a BSP that reflects years of bring-up work, product constraint, and quick fixes. And the challenge is to understand which parts are essential and which are historical artifacts. They mix backport, partial rebases, experiment, and leftover in a way that hides what actually matters. So before you can maintain anything or upstream anything, you have to reconstruct the starting point, what the BSP will be built from, what was added, what was unused, and what's actually belong to your board. In the next slide, we'll see how to do exactly that, using artifact, drift, and lightweight analysis. When you open a BSP, it often looks like the whole driver's directory matters. The easiest way to cut through it is that start from the running system instead of the code. Which modules load, which built-ins the DTB references, which symbol appears in the call sim, and which kconfig really enables. When you trace those back to the tree, you usually discover that most of the BSP isn't used for the board you are targeting. Once we know which drivers are active, the next step is to mapping them back to their source tree dependencies. DTB tells us which nodes are enabled. The running kernel tells us which modules are built in, are actually used. From there, we follow the trail, the source file, it's include the helpers it relies on, and the subsystem glue around them. BSP fall into two categories. Some come from usable history, some arrive as a single snapshot. So if the history is available, we can often see exactly which commits add feature, which are refactor, older upstream code, and where the drift begins. When history is missing, we need to switch to a structural clues like layout, flows, register patterns, not to declare the equivalence, but to identify likely ancestry and inherited behavior. And one of the most reliable hints is simply the build metadata. Files like the top-level makefile or version markers are rarely rewritten by vendors. They often anchor the BSP to a specific upstream release, or at least narrow the search space before they begin a comparison. And if the BSP drivers look related to a known upstream family, we use that family documentation bindings and driver expectation as a reference point for triage. In both cases, what it matters is separate what is genuinely new hardware support from older upstream code that are simply drifted over the time. This keeps us focused on the real delta that needs upstream attention. Now that we identified the BSP drivers that are inherited, refactor, or genuinely new, the next step isn't more guesswork, it's validation. We look at what the BSP actually does at build time and runtime and compare against what the upstream driver expect. This is where build artifact become extremely revealing. Modules show which object really load and map directly into the source code path. This cut through the massive BSP tree and expose which driver are alive versus which are fossilized vendor leftover, or simply are not used by the board we are targeting. DTB tell us exactly which compatibles are active. When we follow this to upstream bindings, we can see which framework the hardware is supposed to integrate with. So clock, reset, power domains, IRQ, layout, and whether the BSP were them in a way that mainline expects. CallSim here is the symbol level ground truth. It shows which function the kernel actually references, cutting through the noise of the vendor tree. It exposes which symbol the BSP actually depends on a runtime, including built-ins, hidden subsystem, glue, you never spot by just grabbing the source code. Once we combine these three views, modules, object, DTB bindings, and symbol usage, we can map out the board what really needs and where it diverges. So this is also where we find practical issue like unused drivers, ABI mismatches, private helpers, missing bindings, downstream only probe sequence. This isn't about portability. It is about reality. These signals tells us exactly what dead, what divergent, and what truly needs attention. Tools help us find patterns, but they can see silicon errata, board timings, quirk, and vendor-specific workaround. DT schema is noisy. Most warnings come from perfectly legitimate integration-specific properties. And even when two systems looks identical, the reality can quietly diverge. A great example of this is the ARM generic timer. Same timers, same register, same driver, same programming model across dozens of ARM v8 chips. Structurally, everything matches. but on two NXP SoCs, the LS2088 and the LS1043-8, that identical timer sometimes return wrong values, an hardware bug documented only on vendor errata. So nothing visible in the architecture tells you this. If you only rely on structural similarity, the process will lie to you. Everything appears the same except the part that breaks. So automated analysis shows us where to look, not what is correct. Human review and subsystem expertise are what BSP logic into an upstream patch. One of the most honest ways to understand a BSP is to look at what it exports. Exporter symbol together with the public header are the kernel ABI. They are the contract that all driver must obey. When a BSP rename export adds a new one or expose helper that upstream keep internal, that is extremely telling. It usually means that BSP needed an API that mainline did not provide, or it crossed the layer boundaries that upstream deliberately enforced. Structural layout changes and missing helper are also huge red flag. They almost perfectly predict which BSP driver will fail if you build them out of tree against the upstream kernel. A quick example. In 6.6, DMA IP add is internal. In a Qualcomm BSP based on 6.6, if you diff the mod inverse, and you suddenly see that it is exported along with half a dozen new IP helpers. Why is that? Because the BSP implements several IP types that upstream doesn't have. It needs the internal DMA IP helpers, so it exported that function upstream that never intended to expose. And for the sake of true, this is common to many BSP integrating the Android kernel. It is not just a Qualcomm peculiarity. This BSP has drifted, and the upstream will reject this export unless you provide a very good reason to accept them. After the classification came subtraction, reducing the BSP to just what the code that truly belongs the vendor. And the step 0 is always the same, subtract the main line. Anything identical is removed first, so we can focus only on the delta. If the BSP has an history, the upstream commits and backport will fall out automatically through metadata. Things like hashes, upstream tag, patch ID, and message ID are your friend. But without an history, you need to subtract upstream by content similarity and by spotting vendor layer shim, those compatibility wrapper that reveal when code was adapted rather than invented. Once the upstream work, backports, and cosmetic refactor are removed, what remains is the genuine vendor-specific functionality. That's the code that needs engineering attention and ultimately upstreaming. All right, we've been archaeologists so far, brushing sand off ancient driver, discovering subsystems that reflect history of bring up and not necessarily what production board requires, and learning more about BSP than the vendor ever documented. But this is where we stop digging and start building. We carved out the real feature, the real delta, the part that actually matters. Now the goal is to turn this giant vendor block into something that upstream can recognize, ideally with far few patches that we started with. Upstreaming BSP isn't about volume. It is about ordering. If you're sending everything at once, even good code becomes unreviewable. So this strategy always begins with the foundation, which in almost all SOC means clock, regulator, power domain, reset, and interconnects. If these aren't upstream, nothing else can probably really be. Upstream follow dependency order, whether we like or not. Bindings also need to appear early, and they must validate cleanly. DT bindings will make you iterate, and that is normal. Its strictness is intentional. Upstream binding must match documented expectation exactly, and the tool will tell you precisely where they don't. Once the foundational pieces land, you can slice the remaining work into subsystem, DMA, and all the remaining peripherals, for example. Maintainers, on the other hand, strongly prefer small, self-contained series instead of a full SOC landing as a monolithic patch on Friday evening. And finally, follow what maintainers and documentation/process describe. Those documents define expectation for patch structure, review flow, and subsystem responsibilities. If you align with them, your review are supposed to go smoothly. When people hear about OOT out of 3 builds, they often image a compatibility test. But most failure come from a perfectly normal header churn or internal refactoring. But even with that noise, the pattern of failure can tell you something useful. When a downstream driver fails to out of 3 build, it often points directly to the assumption the BSP makes about the subsystem internal, like private headers, unexported helpers, fragile struct layouts, or ordering dependencies. So the value here isn't correctness, is triage. OOT builds show which part of the BSP still rely on internal kernel details that upstream never promised to be stable. And this is the signal we care about. The place where cleanup needed before upstreaming can even begin. So when the out of 3 build explode, and it will, the individual compiler message are what matters. What matters are the categories of the failure. Build failures will tell you the driver depend on private header, the vendor only helpers. Link errors reveals the use of subsystem internal symbol. Type or layout mismatches means the driver silently relied on a version-specific kernel internal. And if the module actually loads, probe order failure often expose deeper integration assumption, like clock, reset, and power and sequences that the BSP never encoded explicitly. None of these error will tell you what to upstream. They tell you where the upstream violated kernel boundaries, and therefore where the cleanup must happen before the upstream submission. That's why the OOT builds are diagnostic tools. When a BSP ships several drivers, the first pass is simply to organize them. Structural hints, register region, IRQ patterns, and recurring quirks help us to guess which drivers may share ancestry or wrap up a well-known upstream IP. This hints doesn't prove equivalence, they just narrow the investigation so we know where to look first. Integration differences, synthesis variants, and errata still matter, so the final decision always rely on subsystem review. But sometimes the detective work ends with a smile. You follow the pattern, compare the register map, line up the IRQ flow, and the mysteriously peripheral you were been excavating turns out to be a perfectly ordinary design where you are wearing sunglasses. The lineage was upstream all along. The real complexity was in the glue around it, not in the block itself. The important part here is the Git choreography, is the kernel documentation. The kernel documentation already teaches that. For BSP consolidation, what matters is the structure of the submission. First, you show that the upstream driver really does cover the hardware, compatibles, register, and integration data that demonstrate the shared lineage. Then you isolate what is genuinely different, small behavior, details that tie the integration, and errata. Those go to a minimal, well-scoped patch, not a huge rewrite. Once consolidation is accepted, the redundant driver BSP can be retired. And in the cover letter is where you tell and explain the big picture, what's been unified, why upstream driver applies, and how this ARIS is organized. The goal is simple: make the vendor delta small, clear, and easy to maintain, to review. BSP ages in two different directions. The first divergence is from LTS version it originally forked from. This is the gap that determines how hard it will be to apply stable updates and security fixes. This is your maintenance cost. The second is the divergence from the mainline upstream, which keep evolving while the BSP stay frozen. And this is your upstreaming cost. And these two problems are completely independent. You can have a BSP that tracks LTS well, but it is kilometers away from my line. Or, more rarely, you may have also the opposite. Understanding these two axes is what lets you choose the right strategy for both short-term patchability and long-term sustainability. This slide is about keeping the BSP stable during the upstreaming journey, not as an alternative to upstream, but as a bridge that keeps the system patchable until the upstream work lands. Teams differ in constraints, so transition period is normal. But during this period, the most important thing is continuous visibility. Diffing the BSP against the LTS base, tracking symbol and API changes, and detecting drift as early as possible. This is where CI becomes essential. CI can run out of 3 builds of the BSP against the evolving LTS kernel, for example, when the upstream changes something you depend on, or when the BSP accidentally introduces a dependency on an unstable internal, the CI light up immediately. That usually appears weeks or months before anyone would notice manually. The goal isn't maintain downstream kernel forever. The goal is to keep the BSP delta small enough that LTS updates remain boring instead of catastrophic, while the upstream process continue in parallel. So, most BSP aren't designed to be disposable, but they can become disposable once deadline slips and patch start to piling up. Different teams have different constraints, and sometimes you just need more time before you can engage the upstreaming. The goal here isn't perfection, it's preventing the BSP from turning into a long-term fork. Keep the BSP delta as small as the hardware allows. Upstream reusable pieces early before they fossilize. Separate real silicon requirement from temporary brings up and they tend to accumulate under pressure. And above all, treat the BSP as a bootstrap, not as a parallel kernel. Make every patch something that the future you or the unlucky person that inherits your tree can live with. The healthier the BSP stays during the transition, the cheaper and smoother the eventual upstream becomes. The techniques I show you today are triage, not true detectors. They surface signal, not conclusion. Structural hints and artifact drift simply tell us where to look first. The real answer always comes from understanding the integration errata behind the hardware. And ultimately, the only sustainable outcome isn't maintaining a cleaner BSP, it is upstreaming the work, so we no longer carry a private fork history. And that is all. If you have any question, I'm happy to answer.
Thank you, Alessandro. I'm curious if there might be another way to kind of deal with this problem. So as you said, upstream BSPs have a lot of challenges.
Yes.
Especially when they are taken over from somebody else, you lose a lot of context. There's a lot of reasons why BSPs are challenging to get upstream. Sometimes the devices are very limited in quantity or short lifespan or whatever the reason. But there's also a lot of value in having the BSP support as close to the product launch as possible, so that the product can follow along with kernel updates and security fixes. It occurs to me that Android deals with this problem by creating a binary interface between the kernel and the BSP. That way, they can work together immediately, and then the BSP can continue the upstreaming process while staying in sync with the kernel itself. So I'm kind of curious if that technique might have broader value to the kernel itself or for things beyond Android.
Well, actually, this is something that I noted during the slide. The Android interface applies, the Android kernel image applies the downstream patches that allows most of the driver to be used out, to be compiled and used out of tree. The upstream kernel doesn't allow this because to export everything that needs, the upstream maintainers wants to have a valid use case. And apparently, when a small BSP has this necessity, or it cannot make it necessity valid, or probably is their vendors are not trying to upstream their BSP, so the maintainers are not aware of all this necessity that it exists. Google appears to have intercepted this necessity, and in fact, it applies some downstream patch to the kernel and build what they call common kernel image that is pluggable with almost any out of tree drivers. Don't know if this answers your question.
I know the Android solution is not perfect yet, not fully upstream. I was just kind of curious if there'd be value in the technique in general, because if there was a defined ABI for that, then downstream BSP developers could target that initially, and then there's compatibility immediately versus at some future point.
I think there is a value in this personally, but I also do see the reason why this is not happening. It is probably because making taking this decision, we are somehow violate the idea behind the open source, because this can allow vendors to provide a completely closed source binary version of their drivers. Probably but this is my personal opinion. It is not.
Yeah, there are certainly downsides as well, but the licensing doesn't change. There's no hidden binaries in it.
Okay.
Well, to follow up on that, perhaps a constraint would be to require the BSP to provide a statement about its license so that it could be verified at loading time. But the question I had was, what about KPIs when you do this?
Sorry.
Like, what about KPIs? So power, performance. Do you also get some battery of test cases that you can run while you are performing this work? Like, how do you know that you're not introducing functional and non-functional regressions from a board user perspective when upstreaming?
Well, this is actually a lot of manual work, because as I said, in my process, I help the upstreamer to identify lineage. I do not give a receipt ready to use to have the work complete. So when, for example, you identify the lineage of a driver or a completely new driver. So in the completely new driver, probably you are somehow advantaged by that, because you can take the code as is and try to upstreaming as it is, if the code quality is matching the upstream quality. Instead, if you are trying to adapt an existing driver that may have some quirk or some differences, for example, if you notice that a UART resembles to a UART that exists already upstream, and please note that the upstream rules mandate that if there is any similarity, you need to verify you can reuse an existing driver. So in this case, you need to do this work manually and test manually before the upstream can occur. So I do not have a ready-made or possibly an answer that completely answers your question. It is something that the upstreamer need to verify before upstreaming the code.
Yeah, I was just wondering if when someone provides you the original version of the BSP, if they also give you test cases, reference values.
If this is the case, you will use it and also upstream those test case. In my experience, I never saw this kind of thing, but if you say that exists, I trust you.
It was a question.
There is a question in the chat. If you can scroll up, I think you can see it. Otherwise, I'll read that for you.
It's blocked. It's locked.
Okay, I'll go ahead and read that for you. It's
Thank you.
from Jan Luby. Are you aware of any tools which take a vendor kernel source release and automatically find backported patches, fixes, so that you can reduce the delta?
A magic wand, I mean. In any case, no, I don't think there exists a single tool for this. I am working on a tool that navigates the Git dependencies, for example, to eliminate the delta common to the BSP. There is other work in progress to work with the bindings that I'm personally doing. I didn't find any made from other person, but I cannot exclude they exist. In general, a tool that takes everything and make the work for you, I'm not aware. If anyone knows, please tell me that I go in vacation.
Okay, looks like this is a comment from Jan. Google can allow an ABI because they have contractual economic leverage to force device vendors to regularly rebase. Without that, the pressure that would be a very risky approach for the community to allow. It's just
Okay.
seem to be just a comment.
Julia.
So maybe this is sort of a silly question, but can AI help you?
I'm not sure of that. It would be nice if it can. In my personal experience with AI, the problem is that it provides a very, very trustable result. But when you verify, you often, not always, but you often find that this is really well made, but completely false. So
Yeah, no, I'm sure, but it seems like a problem where you have to make a lot of decisions and you have to
yeah,
kind
it
of
is,
make
it is something that
between
can be.
things that maybe AI could be better trained for working on this kind of problem. I mean, I have no idea. It's just
Well, it is something that worth testing. I do not have an answer on hand. I didn't try, and I'm a little afraid to be frank. But it is something that, in another context, I may try and see if it works.
Well, I tried some proprietary AI tools to essentially, from a commit to get dependencies. The commit, they do reasonably well. It's not complete and always, of course, true 100%. But if you don't have like any idea, it's a good start. So I would say, try.
Okay, something I will try.
Yeah.
Thank you. Any other?
Follow-up comment on the chat. Yes, I meant just such a tool working on the Git commit graph only.
Okay.
I think so. Chris Mason has been working on several tools. One of them is SamCode, which essentially indexing your Git tree and find dependencies also programmatically between commits. So that combined with, again, an AI tool is even more powerful. It has an MCP server that can actually query that database. So that's another thing to possibly try.
Okay. Thank you.
Any other questions?
Thank you. In the upstreaming process, it might happen in the discussion with the Linux kernel developers that you need to change an API or that you need to change something that is backwards incompatible to the BSP. Do you have any comments in, does it make more sense to push these changes early to the BSP than you frustrate the users of the BSP? Or do you keep divergent patches with different interfaces possibly in the BSP, but the proper ones on the upstreaming side?
Well, my suggestion is that once you have the BSP driver accepted upstream,
Sure.
you remove the BSP driver. So you integrate the upstream driver into the BSP and you do not have to deal with it anymore. So my suggestion would be follow the upstream so that once you get your work merged, you don't need to maintain it anymore.
Sure, but I guess there is some transition time where you try to upstream the new driver, you realize you need to modify that, but still keep the old driver in the BSP for...
Well, in the meantime, you have to stick with the LTS and probably take the upstream bug fixes and update from LTS and rebase your BSP.
Yeah.
Any other questions? Just 1 minute left. Do you have a question? Anybody?
Thank you.
Should be able to just pull up your slides. Let's see. What you
Rethinking.
rethinking? Oh, okay. Okay. Go. Okay. Okay. Come on. Oh, okay. That should be up. All right.
Thank you.
So you will see the chat
Yes,
here,
and I can
so you can
keep
monitor
an
that,
eye.
and I'm also going down. I know it's hard to.
Yeah, I can. Thank you. Should I go ahead and get started, or? All right, cool. Yeah, all right, I'm gonna go ahead and get started here. Thank you. So let's see, let me start my timer so I can keep an eye on the time. Yeah, hello everyone. My name is Steven, and I work at Oracle, and I'm gonna be talking a little bit about compact debug info formats and how I think that they can help us rethink some of our tooling, Linux tools that we use, that we're writing, things like that. So I work, again, at Oracle, and the reason that that's important, I work on the sustaining engineering team. And if you're familiar with sustaining engineering and like in enterprise software companies, that essentially means that I fix bugs in old released products. Whereas a lot of people here are probably working on the latest, greatest upstream kernel, adding new features, things like that. I am spending more time on fixing bugs in a production kernel that a customer is using, which has its own set of challenges. In particular, I think a lot of customers don't really like debug info. It has the word debug in it, and it's a little scary. So I'd like to talk a little bit about that and how that informs my strategy with debugging and also just the broader set of Linux tools we have. Okay, cool. It's that button. And so my thesis for this talk is essentially, if we change a little bit about how we think about debug info, then we might find that we can add new interesting capabilities to tools that we're already using, or build new interesting tools. So to start, before I do that, I want to kind of give an overview of what debug info looks like in a couple different examples. Please bear with me. This might be really obvious for some of you. It might be just good foundation for everyone, though. So imagine you've got your Hello World program, right? And if you're like me and you started learning C, you wrote a lot of bugs, and so you needed to immediately learn a debugger in order to start working and to figure those out. So imagine you compiled that program and then promptly stripped the program, removed all the useful information out of it, and you run it with GDB. Then you try to set a breakpoint, and I guess I can highlight, yeah, breakpoint right there. But yeah, GDB can't find the breakpoint or it can't find main because there's no ELF symbol table anymore. And so when you run, it doesn't do anything. It can't stop the program at main, and it just finishes. Rather disappointing, but that's pretty obvious because you stripped all the useful information out of the program. So that's kind of on you. The next option is, say you didn't use strip, you actually left it as it was, then you can do some debugging. you load GDB and you set the breakpoint, and it does find main. But then if you try to step through it, let me highlight here. Using the next command, GDB doesn't know what line number is the next instruction. So normally it would set a breakpoint on the the address of the next line of code, but it can't do that here. So it just continues running until it finds a line that it knows about. And in this case, I happen to have glibc debug info installed, so it stopped there. But more accurately, it would probably just exit out. And again, you wouldn't really get much debugging features. So then obviously the thing that everyone would say from the start is use -G when compiling, and you'll get your dwarf debug info added to your executable, and then you get the full fat GDB debugging experience. Compared to the previous slide, there's a lot of interesting things here. First of all, when you set the breakpoint, you get a file name and a line number pointed out to you, whereas previously there was just an address. And when you actually hit the breakpoint, you get that file name and line number again, but you also get arguments and their names and their values. And as you step through the program, you get the line numbers, the file name, and you get a printout of the source code. And some things that aren't, necessarily demonstrated here, but GDB will also be able to interpret more complex types, structs, unions, all those things. So again, I don't think that this is too new to anybody, but it's a good foundation. And it kind of illustrates what I think is the classical approach to debug info, which is that you get nothing until you use -G, and then you get everything. You get a really great debugging experience with dwarf debug info, but distributions are going to compile that, and then they're either, if you're Arch Linux, they're going to throw it away. They don't do that anymore. They save some of their debug info. That's great. But otherwise, it depends on the distribution. Most of them are just going to put them into separate debug info packages, and the reason being that dwarf is really big. And so that means that runtime binaries they'll have some information, rather minimal, kind of like the second example I showed. And if you encounter a crash, then the typical maybe more legacy or simplified approach is that you're going to need to have your customer, your user, install a debug info package, and then they can run debugging commands, or they can generate a report, or they could send you their entire core dump if they'd like, something like that. This is admittedly a simplified approach. There are other examples of some improvements. I think debug info D is great, and there's a lot of different crash reporting options out there that I would encourage people to explore. But in at least in my experience, what I find a lot of the time is that if you encounter an issue with a customer, you're going to need to get them to install debug info. And like I said, I find a lot of customers, at least in the enterprise world, are really allergic to debug info. Sorry. And I don't think that I have a gripe. That is the classical approach that I think we're all familiar with, and I have a gripe with it. I think that debug info is a kind of a bad word for two reasons. One is that it's misleading. It has the word debug in it, which I know I've been harping on. Customers don't like it. But I think that also it's a little bit misleading that you could use this information for a lot of different cases that aren't just debugging classically like GDB, stepping through a program, things like that. You could use it, you might want to unwind your own stack as an application. You might need to learn something interesting about types at runtime. I'll talk a little bit more about that. The other thing that's not great about the word debug info is that it's not specific. So in that example I was showing, GDB was doing a lot of different things. It was looking up, it could understand types. It was getting a relationship between variable names and their types. It was finding variables by address or by name. It could do source mapping. It was doing a variety of things with stacks. It could even have shown you macro definitions with the right setup. So There's a lot of specific functionalities, and just using one word to say that is a little bit difficult. It's the best we have, and I'm not actually here to propose another word. So I think what it boils down to is that when we say debug info, we usually just mean dwarf information. So to expand a little bit on things that you might be able to do if you have debug info that are not debugging, if you think about a high-level language like Java or Python, you can do reflection and runtime code introspection. And Python would be a hilarious example of just how much you can do that. You can look at the dictionary of global variables or local variables. You can enumerate everything that's in a class, or you can unwind your code. You can actually inspect the bytecode of the code that you're running, which is a little extreme, but good for you. So they don't say that they're using debug info. I mean, in Python, it's not using debug info. This is just evidence of the fact that it's a dynamic interpreted language. And so all of this stuff has to be available in order for the runtime to actually execute code. But C doesn't really have as many of those features for reflection or runtime introspection, right? There are a couple interesting examples. There's like glibc has the backtrace function, and I'm not actually sure if that's a standard or not, but it's a really interesting function that will only work in certain cases. I mean, if I ran that stripped binary and tried to do the backtrace function, I'm pretty sure I wouldn't get a backtrace. So there are other interesting things that modern compilers can do, like static assertions at compile time. Yeah, we got a question over there.
FYI, if we do get S-frames in the kernel, glibc will have a way of doing backtraces reliably.
Oh, yeah, I mean,
Just FYI.
S-frame, thank you, Steve. Yeah, that's S-frame is going to feature highly in this talk, don't worry. Yeah, so compile time assertions are another good example of things that are reasoning about types. For instance, I think in the toolchain track, you would have heard Keys talk about the different ways that you can do annotating arrays with their length in types, things like that. And so that's useful for hardening, but also other features. So the thing is that interesting ability to like assert or reason about types completely disappears after compile time. So you had this great ability to reason about your types, and then you lost it after compile time because there's no C runtime. Cool. Might take a brief. Okay, I am seeing some interesting comments here from Conan. I'm sorry. I'm gonna keep going here. So the kernel is especially interesting because because compared to other C applications, there's not actually, normally C applications don't have much of that information available, but the kernel actually already does have stack unwinding metadata. It already has symbol metadata built in, and it already has a type system, BTF, that's usually around. So unlike a normal C application, which might not have all of this ability, this is all sitting right there in the kernel. So let me just briefly talk. I know I mentioned a little bit about the types of data that you might find in debug info. I think type definitions, they can tell you things about the size of an integer or like what members of a structure are present. Then you've got, mapping function names and to their addresses or to their types. Same with variables. There is stack tracing and unwinding, which are slightly different. Stack tracing will give you a list of functions that are currently executing on the stack, whereas unwinding would give you variables, registers, any extra context about the execution of that function that is not simply just what function address is currently executing or about to be returned to. You've got the source code locations, inline functions, and macros. So And notably, there are, depending on what source of data you're going to use, and I'm going to talk about those more, there might be some limitations. So I'm just highlighting that here, but I'll kind of explain a bit more in a second. So I've talked a lot about dwarf and debug info, but there are other types. So things I consider debug info kind of range from maybe like if you had an alignment chart or something, the lawful good, the normal debug info things, all the way down to maybe weirder things to consider debug info, but that kind of fit the bill. So obviously like dwarf, compact type format, which CTF, BPF type format, BTF, are purpose-built. They contain data about the types and other things. S-frame, again, a purpose-built format that actually has stack tracing data. ORC, similar but specific to the x86-64 kernel. And then ELF symbol tables also, I think, qualifies debug info. But more specifically, there's some other unusual ones like KLSIMs. I think that you might think of that as a debug info format. Plenty of tools will use it. A kind of interesting Fedoraism that I love is GNU debug data, which they essentially find symbols that are useful to have but not at runtime, and they filter them out of the binary and then put them into a separate ELF file that they then compress using LZMA and then put that compressed object into an ELF section of the original runtime binary. It's a little convoluted, but it works, and GDB supports it, Dragon supports it, a few other different systems support it. So I think that's a really interesting option format out there. And then now into the more odd things to consider debug info. I think LBR, last branch record, is debug info, but it's a hardware feature that lets you see the most recent function executions or branch instructions. Perf can use it when you're doing perf recordings, and so it's an interesting way to get stacks if your hardware and it is capable of it. But yeah, and then frame pointers. I think maybe that's not unusual to consider debug info, but it's not in the classical sense of a format or something like that. So I kind of thought it would be cool to put all this into one table to illustrate what each of these things do. And the obvious thing that stands out is if you can use dwarf, probably use it, right? Like it does all of these things very nicely. So, but another interesting thing to look at is that if you want, you can kind of pick and choose a few of these other things on the right and piece together something that might be useful for you. I think that's a really interesting takeaway. Now, I've marked, and especially if you are in an environment where dwarf isn't an option, like if you have customers who really don't like that, then that's an interesting thing that you should take advantage of, is to use some combination of these other formats. So I did note a few of these things with kind of a warning sign, and I'll kind of just illustrate them. So the dwarf macro definitions, they only come about if you add some extra debugging flags. You're not going to get them by default. The BTF currently only contains information types and addresses for per CPU variables. So it doesn't include all global variables, and it does include functions. So all functions, all per CPU variables, not the remaining variables. I'm not entirely certain why. I know there is a reason why. I'm actually working on trying to make that change. And then these two, LBR and frame pointers, I just put little remarks on them because frame pointers you can't really use to unwind in all cases, especially asynchronous stack unwinding. The idea is that, if you have a frame pointer you're setting up, then in the code that you're setting up the frame pointer, if you get interrupted and you're trying to unwind that stack, then you won't be able to unwind it. So that's not really ideal. And then LBR, it's not really ideal because you'll have to have privileged hardware capabilities. So the OS perf can use it, but not in any other situation. And it also has a relatively limited stack depth, I believe, but yeah. So yeah, I think I mentioned these observations already, but yes, if you can combine a few of these non-dwarf options together, you get something really potentially useful. We've been doing this in Dragon, which is a debugger that I think I'll talk a little bit about later. And I think also I've already said the kernel is unusual, and having all of these or several non-dwarf formats available. And then I think another important thing to point out is that a lot of useful non-debugging features don't require everything that dwarf has. So it does. The reason I want to talk about rethinking these formats or rethinking debug info in general is just because you need debugging a couple features of a debug info format doesn't mean you need to have all of dwarf. Maybe you could just pick and choose a few things and put them together. So what I want to go then about is talking about a few case studies historically of how compact formats are useful in different Linux applications and tools, and then kind of talk about potential future ideas. And hopefully other people are already a little interested and might have some thoughts too, because I was thinking kind of how Stephen likes to say this, that the micro conferences are more about brainstorming. Maybe people have some thoughts too. So, but this isn't a micro conference. So my first case study I wanted to kind of mention is the PS utility. I remember reading in LWN when devkmm got removed about how very old PS applications, like around Linux 0.98 or something like that, and maybe other applications too, the way they worked was not by reading the proc file system, because that had yet to be invented or at least implemented in Linux. So they worked by opening devkmm and reading out the task structs that were on the system, which is honestly pretty smart, pretty cool. A little bit dangerous. Probably wouldn't be doing that in a modern enterprise system or whatever, but hey, it had a downside, of course, besides needing to be root or set UID, that this needed to be rebuilt on every change to the kernel, or it might need to be rebuilt because someone could add a field or something to any field, any struct. And so without type info, you just had to rebuild the PS application. But now, of course, you can use the proc file system, and that's definitely the better option. But not everything actually needs an API or an ABI, right? Proc file system, great. Glad we have it. But maybe getting debug information out of KVM, maybe getting strange specific information out of subsystems that you as a developer or as a power user want to know about. It shouldn't have an API or an ABI for user space, but maybe with those compact type formats, you can make something kind of like this that works with Dragon or something like that. So that's just one area where I think compact type formats could be helpful. Obviously, PS solved this issue with the proc file system, but one place where that very, very similar problem was solved in a totally different way is with BPF and co-re. So BPF programs had the same exact problem, that you would need to ship BPF source code and you would need to compile it on your target system because the structure offsets might be different on every kernel that you might want to run the script on. And so you needed to have Clang compiler available on your target system and all these things. Nowadays, when you use BPF, you can use co-re. You compile the application once on or the BPF code once where you're writing it or building it, and then you can ship it off to where you want to use it. And you'll actually get relocations where I just chose dparent here as an idea that if that offset ever changed, co-re would be able to update the offset that you read in your BPF program, and your program would automatically adjust. So had there been a BTF co-re in Linux 0.98, maybe we never would have implemented the proc file system. I'm glad we did, though. So yeah, and that obviously eliminates the need for compiling BPF on the target system. So another case study that I think is really interesting in compact type formats being useful is Dragon, which I mentioned briefly. It's a programmable debugger. It's a Python-based debugger that it normally uses Dwarf for debug info. But if you want, then we've been working on features to enable debugging without Dwarf. So we, in a few releases back, added the ability to load KLSIMs and use it as a symbol table like it had been in the ELF, as if it had been an ELF symbol table. We added the ability to read the orc info out of a x86 VM core and start using that to unwind stacks or do stack traces, I guess, without needing to find that data out of an ELF debug info file again. And then for looking up types and variables, we've got a pull request out for using CTF, which you can find in Oracle's UEK kernels, but BTF and CTF are actually very similar, and we're actually hoping to converge those formats together so that we won't have these two separate bullet points. Ideally, it would just be, you can use BTF to look up type and variable of different things. But like I mentioned, global variables aren't available yet in all BTF. So yeah, that is Dragon and dwarfless debugging. And then this is something I mentioned kind of when I was explaining what GNU debug data is, but Fedora has this GNU debug data feature, and their problem, of course, was that they wanted a similar thing that I was saying with Dragon, that it would be really nice if you could get a stack trace or out of a core dump or a user's application that crashed. And their issue was that while they actually have EHFrame, Dwarf CFI, unwind information available on all runtime applications, I believe it's necessary for C++ exception handling. So everybody just has Dwarf unwind info in all of their runtime binaries right now. But they had the ability to unwind all of their stacks, but the issue was that they didn't have symbols for everything. And so variable, when you get a stack trace, half of it would be, hexadecimal addresses, not very useful. And so GNU debug data was the solution for that, where now you can get a stack trace that has useful information that you can send off to developers without needing to send a core dump. So that's a pretty useful idea. I'm going to stop to see what Neil said. Yes, I just figure Neil knows more about this given his situation. So yeah, all right, that is Fedora. I have one other past idea about compact formats. I didn't really include it in my table, but I think VM core info is a really useful way to think about a compact debug info format. Make-dump-file, as I think many people are familiar with, is a tool to make a compact core dump out of the proc VM core when a crash happens in the kernel. And in order to do that, it needs to know things about like the offsets of fields in struct page. It needs to know about certain symbol locations so that it can find the root page tables. It needs to know, at the end of the day, it just needs to be able to make a determination for every page. Is this useful to include in a core dump? And they could, I mean, you can use Dwarf debug info to do that. Don't get me wrong, it has the ability to do that, but that's a bit of a pain to use. And especially in the KDump environment where there's limited memory, limited everything, honestly. So they instead took those hundreds of megabytes of Dwarf data and shrank it down to a 4 kilobyte piece of text that they read out of the VM core, and it has all the information they need. A few symbols, a few structure offsets, some other information there. And I think this is a really kind of fun example of how compact formats can be useful, but I think it also kind of begs the question, like, what could make-dump-file do with even more compact debug info available? So I started working on an implementation of BTF and KLSIMs, and then Tao Liu noticed that I was doing that and said, hey, didn't you see my patches on the mailing list? And so we'll try to work together on this rather than having separate implementations. But the idea is that, hey, VM core info is great for the basic idea. I just want to filter out certain pages based on very coarse classifications. Is it a user page, a page cache page, or is it a kernel page? Or a zero page or whatever else. But if you want more features, like maybe you want to exclude GPU buffers because there's a lot of them on your LLM training machine or whatever, then that might be a good idea to exclude. Or maybe you want to be able to do stack traces of the user space applications just before a panic happened. I know the situation with a lot of my customers is that we have a system that will crash the kernel in case of a very bad user space situation. And that way you quickly get back up and get into a known good state. But then the problem with that is like, why did we panic now? All I can see is that there was a write to the proc file to crash the kernel. So this might get you the ability to look at a stack trace for what was actually going on for the application that triggered this core dump or the panic. So I think this is, I mean, no promises. I think this would be a really interesting way to expand make dump file in the future. And now we've gotten to basically my last like spitballing page, and I don't necessarily want to say that any of these are great ideas. They're just things that I was spitballing when I came up with these slides. One thought is that GDB and Dragon do a great job of printing out structures that are formatted, printing out memory that's formatted in a way that's useful to a developer rather than as a hexadecimal dump or something. So it might be interesting to see about a way that PrintK could just, obviously not in production, but if you're a developer and you're looking to just get a quick printf debugging feature, maybe you could get something a little bit more user-friendly by using the CTF or the BTF and actually interpreting the type of that argument that you gave. You could maybe see something like that, being part of glibc even as a very silly concept. Enum values converted to strings. Obviously, this is something that you could do with some sort of static feature from the compiler side as well. I kind of wonder why that's not a thing yet, but probably because it's open source and I haven't submitted a pull request. Maybe with perf, there's the idea of using perfmem or perfc2c to look at memory accesses and see which accesses are triggering certain cache line sharing, false sharing issues, or other memory related issues. And it would be interesting if you could do that rather than looking at memory addresses. If you could say, well, this is a slab address and it has this type object, and I can tell you that that's the offset of this field in the kernel. So we have false sharing on this structure in this field, or this symbol, or something like that. I think that would be an interesting way to wire up some of these compact formats. ABI checking is an area where CTF and BTF are already getting used in libabigail, I believe. And I think there are probably other options that I'd love to open the floor out in like discussion or questions. The only other thing that I had here was the idea that BTF and KLSIMs are actually sharing a lot of the same data. So in terms of string tables, we could probably do something, given that these are sharing a lot of the same information, we could probably combine them in some interesting ways too. So to further compact the formats. But let me see, yeah. That brings me to the conclusion here, which is basically Dwarf, really excellent if you have it. If you can use it, definitely use it for debugging. If you can't use it, there are a lot of options out there that can form a minimal alternative to Dwarf. And finally, things like these compact formats don't necessarily need to just be used for debugging. You can pick and choose a few things together and use them for some interesting introspection, kind of like you would see in a higher level language like Python. Turn C into Python, I don't know. And yeah, I think there's a lot of room to rethink different tools and applications that we're already using to make them more user-friendly based on this sort of approach. So that's everything I've got, and I think I'm a little bit short, or not short on time. I'm a little, yeah, we've got like, 10, 15 minutes for questions, or we can have an early break. So thank you.
Yeah, thanks for your talk, and thanks for mentioning the data type profiling in Perf to match the PMU sample memory access information to data types. So we have it right now, but what's missing, not missing, but the needed information is to match the data address and actually the source code code address to match the data type it accesses. That requires the source location information, which is provided only in
In
dwarf.
dwarf.
Yes.
So it's the source. So you're trying to find, it's not the offset in the structure. You're actually looking for code addresses.
Yes, because not just offset in the field data type, it needs to find which data type it accesses.
Yeah. So one, that was why I was potentially suggesting as a different approach, you could look at the type of the page and see whether it's a slab page or something like that. And if it's a slab page, you can figure out which slab and you can get a good guess at which type it is as an alternative.
Yeah, we do have that, but even in slab doesn't have
Yes.
type information.
If the slabs are merged, then yeah, there's and the slab doesn't have type like annotated with it. You're right. I do think it would be really cool to have an annotation. And as the kernel hardening approaches are trying to like make every slab page have it, or slab cache be specific to a kind of type, that might even get easier in the future.
Right. Okay, thanks.
Yeah, thank you.
Other questions? Looks like there are a lot of
Yeah, a lot
discussion
of
and
discussion going on.
Yeah, generated quite a bit of discussion.
Okay,
Great.
that's great. Yeah, I'll read through it once I get off the podium. All right. Well, thank you, everyone. Appreciate it.
We have a coffee break for now, and we'll resume after at noon. You're the next speaker. Okay. Let me put up the.
Updated my slide in the
Oh, did you?
morning.
Oh, you updated this morning. When did you update? Because I pulled them.
Oh, really? Can
I
check
pulled them
mine?
this morning. Yeah, go
Just
ahead
one.
and check yours and see if it looks good. Otherwise, we'll bring it in. I was just going to put a default side up. I just put them in today. I mean, just this morning, probably around 8, 9.
Yeah, it's old.
It's old?
Yeah.
Okay. I need to do this, I think, separately. Let me do that.
Sorry about that.
That's all right. See, I just. Okay, we'll put the default slide up and then we'll go and.
That kernel will collect memory and create the complete order. Right? You can use to make the file in the kernel. Yeah, and we can take that and minimize it. I want to do that without the key kernel. You know?
And that's a problem, and they're all part, I mean, but not the kid.
No kernel involved. I mean, I want to run a safe kernel to execute a new kernel due to various reasons. Security reasons, unable to run another kernel, things like that.
So then the idea would be in the panic handler or something like that.
Maybe I don't have a pack. Maybe the kernel is completely frozen in there.
Okay, so then maybe firmware is sitting
Yeah,
there.
that's what I'm going to discuss. How can we do that in the firmware? How can the kernel help the firmware to collect some data and minimize the over?
Cannot wait to exploit firmware that's parsing the LPC or anything else.
I don't know. Feel free to explore that.
No,
I don't mind. That's good.
No, but I like the idea.
More people get them working
Software or what's found is better for everyone. The problem with that is vendor specific.
Yeah, a way that multiple vendors can use. I think it's something generic that multiple vendors can tap in and get this stuff done without being too much vendors. you have to have some vendor-specific thing for this product. But if the kernel have like a engineering way to provide that, well, you underneath like
But I guess
UEFI is available, but it's not.
but it's not. But there needs some data type that format can parse and say, okay, those are the areas of memory.
That's what they work on, and that works.
Right, that's a good point, yes.
Android,
Yeah, so hardware.
That's what I will discuss. That's why I was thinking. During the presentation, and some opinions. The more opinions, the merrier. Now, because to get it upstream, to get tracking, to feel maybe you work for work and you work like that. I don't know.
I don't know how to get the people who work on firmware for our thing. These people like seem to live a mile, like miles away.
People who work on firmware, not
Yes, exactly.
Yeah. And usually they're very reluctant to say, hey, the Linux wants this. Would you do that? And they say, yeah, we do the firmware, adapt your software. Like Paul said, it's a high-level OS firmware. The high-level OS is not just Linux or anything, and it has to adapt with what our firmware does. But sort of like, you're a bit too strict on what you're doing.
It's the same user space. Don't bring the user space. User space should do.
User space is the king. We just allow the processes to run, stop them, control them, or allow them to run. You were very funny with that. User space question.
Yeah, so, I mean, that's one kind of strange thing that we do, but I don't know if it's common for people.
It happens, but it should not.
Yeah.
It should not. But it happens, I've seen it. Everyone's seen it.
So I am.
Guys,
I've been sending patches.
explain the mini dump whole everything, maybe.
Some things.
I don't want to talk much. I want more your view.
Yes, exactly.
Showing you what I did because
It's similar to sort of thing, right?
someone, yes.
Necessarily.
Sometimes it's difficult to get look at the patches, especially if you have RFCs or something like that. They're not really interested in area. There's so many patches going around. You don't have time to read it. Yeah,
Might need to have some sort of.
even for hypervisor, you should just roll around and find stuff. So it's easier if the kernel itself has something like inventory and so
There might be.
it's easier to find everything.
Might even be.
It should be more something like specific driver data that you want to share. You have a driver data that works. If your kernel crashes, you have this information available for a debugger. Let's say, what you send it to the vendor that makes it GPU, what the vendor needs to know why the GPU crashed. So the hypervisor will not know which GPU is there, what driver is running, what information is there available in the driver. So it's easier for the developer to say, this is my debugging for the in case of the bad habit. This is the mark, this one, and in case of the bad habit, it's all.
Yeah, I like having the pipeline.
Yeah, another argument that we use is right
I will be. Kind of throw the last seconds of
You should go on and all day or at some point have internet connection and your phones there. You like to look at your sensitive data to vendor. You say yes and collect.
Where can I open this?
Sensitive data that's looking at.
You just go here, this plus button. That's how you pull up your stuff. And then that's one, right? For updates. Just check in and switch me back to default. So then you can go into the plus again and then switch us to default, which is the
Good, thanks.
How to get the data to the vendor. Now, the goal is how we collect it, and then the firmware cares for how to store it. Don't store it.
Yeah, but then still, what's happening, you know, when they want to crash? Just to send it back. How does the firmware get access to
You need a hardware mechanism. Qualcomm uses a watch. If the kernel is dead, watch don't. Rings a bell and says,
like the server who sent it that uses hardware?
I suppose so. And the firmware updates can change. The data is encrypted, key that is assigned vendor, the hardware, source is encrypted in their storage. Maybe they have like a hyper-flash disk for the information. You go to your phone, it says system data, then that's the stuff. Stores data. Like maybe 100 years each dump is 30 gigabytes around. You don't dump 15 investors 10 times. You dump like 5 megabytes, 10 megabytes. Like the operating systems. I was running this and that and
And so the companies that are buying.
you can have a running covers, not that works. User space bugs should not be a problem. User space crashes, some user space crashes, your kernel is still running. You know what happened. Have a zombie process, have a test process.
Yeah, so yeah, it depends. It's like,
If the kernel is running, if the kernel is fine.
usually these are, it's not that user space had a problem, it's that user space noticed that the kernel was doing something poorly, like it lost connection with the NIC or lost some important device state, but it's not a crash, but like it's something that's wrong that the user space can't handle, and so it's just going to trigger a panic, and you can't, if it did log anything, great, you know, unless it's gonna hit sync first, you know, then it's not gonna make it a disk. So like, the ideal is just like that information about like, why did I panic the kernel? It's not that the user space itself encountered a bug, it's that it has determined there is a bug with the kernel, it's angry with the kernel, so it's gonna kill the kernel. And it encodes the information about why in its stack that leads up to the point where it decided to kill the kernel.
So some people are just dumping things to their keyboard as they dump to the kernel log.
So
I saw that a lot. They dump into a lot of stuff into the kernel log and then panic.
So I did that.
You can see.
I've done that. I've done that. So because I had people came to me, especially like, how do we get this information? And so first I was like, yeah, you can do that. But then these are the same people who sometimes they like their customers will then configure a 9600 serial port or something. And then the moment you write anything in there, it's just like, well, now we're sitting here for a half hour. Yeah. Depending on how much data you have. So
You write the whole.
Well, yes.
Write them.
And, well, yeah.
And the nice thing is, we did that so a human like likes those can verify that whatever it is, it's incredibly not like, you know, right piece of software that will, you know, manage the satellite, right?
I made a prompt file called Crash Dash, I call it. And every time you open it, it would free whatever was in there before, and it would just let you write arbitrary data into pages of your memory. And like we would allocate it, put them onto a linked list and say like, here's your file, and then like later on you could open VM core and read out the data that had been stashed. Those are terrible idea. You would never. You could use it. If you were trying to debug a particular issue. I would never consider that something was happening.
I've seen people dump stuff into kernel command. Like a whole page of stuff into the command line, and it was all the arguments, and then debug data there from the firmware, from the bootloader, because they couldn't get it out. The bootloader had an issue, and you could see the log. Command line, listen, check it out. This is unknown stuff to user space, and that's it needs. So one second, balance. because they could not anything outright.
Yes. System.error log equals.
They had to patch the code, but at some point it was too huge to be. Nothing more. That's real.
You need to be economical with all your logging.
How to log things from the root of the. Yeah, they added to some kind of really have some pages. There are some very good set. They should be feedback. They talk fast and that. Command line was the full flags. Well,
yeah, that's a problem. The two of us are more working on the servers.
I know,
so
yeah.
we are not.
We're never thinking about mini dumps or things like that. It's like, VM core, it's fine.
Yeah, although time to recovery is a consideration, right?
Yes, that's the biggest issue.
Huge dumps and it takes minutes, hours.
Which is why you don't want the GPU data. It's just because like, hey, it takes too long.
Gigabytes of data, you don't need. All of the whole big things, all the remote processors. And they want to tell me so they have all of them, like modem and like ESPs for all your core stuff, right? That exists. Yeah, the difficult dumb developer told me we should not touch his subsystem. And he said, get out of here. Don't touch my subsystem. So he really not eager to do anything cheap. Use like dev core dump to get dev core dump over Linux application processor. I know, for me, it kind of makes sense to have a dev core dump for this remote processor that runs some firmware. This one, and get like a little dev core dump for the main processors or general multi-purpose cores. Why not? Be like an extension, let's say. But this I don't touch my dev core dump. You don't understand what it does. It's clear you don't understand. No, that's something other people's code that you don't understand. Okay.
No one knows it's about embedded. It's just another embedded process.
Yeah, for Qualcomm it's the same. It's running Linux or it's running their hardware code, some parental code or some other OS for them it's the same.
Because in the end, it's just another backlog.
It's something, it's a process running code that has more like generic purpose and serves multiple things that you not just let the GPU. Going to grab some coffee.
Yeah.
Thanks for the call.
Yeah. Oh, I'm glad. That's awesome. You will need to go to and Dragon Eye uses debugging for you. Yes. So you can use dash options to enable the debugging for you. You can pass command line. Try to by equals debugging. Yeah, but what I mean, that you use the command line. I remember using it on the dash. I had it down. To download, but you could force it. Okay. Yeah. Maybe I'm.
Others too about my rating. You crushed.
Oh, sure.
Yeah. I need power.
Password.
Still locked again. Sounds good. Okay, now that I'm here, I can just switch for you. Perfect.
Yes. Thank you. Okay. So thanks for coming to my talk. My name is Namyeon Kim. I'm working on perf tools at Google and maintaining the code base with Arnaldo. So today I'm gonna talk about the last updates and highlight some new major features in this year and discuss about the future directions on each topic. The first one is data type profiling. I've been working on this project for the last couple of years, and still it needs to improve many things, but I'd like to see others to try it on more and more. Basically, data type profiling is to associate PMU samples with memory access information to data types in the source code. It uses dwarf data information to locate the variable information with the sample instructions in the sample address and translate it to the data type it accesses. So this year we added new memory-related output formats to analyze the data more easily. Most from the data source information in the sample data type. And also it has a couple of useful sort keys to show the type information in your profile data. It's hard to see. So updates in this year is we improved the instruction tracking to update the pointer arithmetics, like in the container of expression. When you have container of kind of translation in the source code, the compiler tends to have the variable with the original data type, but it points to a middle of the data type instead of the start of the variable. So you need to adjust the offsets to find the actual field in the data type you access this. But this year, unfortunately, I don't have much time to work on this project, so we still need more support for more languages like C++ and Rust, and more architecture support. Now it only supports x86 and PowerPCs. This is an example output. Yeah, I forgot to say I added also to annotate the sample code with the data types. So basic perp annotate output is like list all the instruction in the hot functions. And with this option that says code with type, you can list the data type of instructions that access memories. So another example is to see perp mem command. Basically, you can use perp memory code to save the data access profile information. And in this example, I just ran very simple test program which runs in a loop to access two variables in a single data type, struct. And if you run perp-mem report with this option, you will see the access information, like which cache level it touched the data, and which data type it accesses. In this case, it's the time name of the access is just buff, and I just use type and type CLN sort key, which shows a cache line in the data type. So in this example, you have two cache lines in the buff struct. And first one, cache line 0 is accessed like a 68%, and cache line 1 is accessed like 21%. So you can extend this kind of information to get the similar analysis like perp seed to seed does, but you can use the type information instead of just using the raw data cache line address.
Question.
Okay.
So like in the scheduler world, there is a desire to know like that some tasks have a data dependency between each other to try to do like better task placement to keep them on the same last level cache, potentially like even like closer if possible. Can we use perf, like since it gives this caching information to basically detect this and like maybe you can even make it smarter. Like, I mean, can it first detect this data dependency between two tasks? And can we make it give us more information like, yes, these tasks are operating on a like the same data set, and being on the same cache will help with cache misses and this kind of thing. I mean, like from 2 points of view, from analysis, just to know in general, and if you want to create a daemon to automatically detect this dependency and tell the scheduler like, hey, this task has a dependency, maybe you can do a better job if you basically know about that.
Okay. Yeah, that kind of information is basically depends on the hardware capability of your PMU. So the information it shows is captured from the hardware, like when it hits L1 cache or L2 cache, or it misses the TLB or something like that. That kind of information is basis you have in your analysis. With that information, you can shows which data type and which field in the scheduler data structure you access mostly. And
not in the scheduler data structure. We're talking about user space tasks.
Yeah, it's
actually like
user space as well. Yes.
So you think, is it doable, you think, to use perf to capture this kind of information?
Yeah, as long as it's written in like C or C++ or other languages to emit dwarf information, and program has the dwarf information at the moment. Yeah, that's actually one of the problem I have. So some application doesn't have full dwarf information. This dwarf information, including the type information and source code location. So you need to find sample address to translate which their variable and which type of that variable is needed to get this kind of information. But some application doesn't want to have full dwarf because it takes too much time to build and too much space in the disk. Maybe you can separate in a separate debugging sometimes, but maybe it's not available at the moment. And I found some interesting use cases that some applications just want to have line number information only because it helps stack trace when you have the problems. So I have an idea to use that information to get this kind of data type profiling using the line number information only. So actually, line number information is not just line number. It also has file name, line number, and column numbers. With this information, you can look up the source code. Of course, it assumes you have the source code of your binary at the moment. But if that, you can access the source code file and read that portion of the code, and you can parse the source code to get the identifier at the exact point in the source code. And then you can ask some language server to understand the source code, and then it can give the data types and which field you accesses. And we can translate that information in perp tools to produce information like before. Then the problem is how to sync the binary and the source code. In the binary, we have build ID to guarantee this build ID matches what you're running and what you're debugging. But source code, we don't have that. So that's one problem it's solved. And sometimes we don't have a source code at the moment. So guaranteeing that having source code is another problem. But with that, we might try this approach to improve data type profiling. Yep. Any questions?
Is that something that like a server process like debug infod or equivalent could do to, say, provide a way to register and look up the source code for a given binary that you're running?
Yeah, if you have debug info D, you can ask debug info D to download debug information from server. And I think Perp already support debug info D to automate that process.
So I guess my question is, would something similar to that process work also for downloading the source code corresponding to it if you don't have debug info?
I don't know if it had, but yeah, still the problem is you have to guarantee that the source code matches the binary you build. Yeah, but I'm not aware of that service to download source code from this. Yeah, maybe you can ask Git repository or something.
Debug info D actually has, if you look at the debug info D find client, then you'll actually see that it can download source code too.
Oh, fantastic.
Associated with a particular build ID. So that actually might be something you could look into.
Oh, I didn't know that. Yeah, thanks. Cool. Okay, then I can move on to the next topic. Next one is latency profiling, which is a cool work done by Dimitri. Thank you. And it was suggested as at first, but naming is hard. We want to call it at first like a word clock timing, word clock profiling, because we want to find some portion of code or program to impact your program's latency more. So the idea is you have just one sample at the moment. At one point of time, you have like single samples, entire system. Like if you have a single CPU machine, that's natural. You have one sample at the moment. But in a multi-processor machine, you will have multiple samples at one point of time. But the classical profiling shows if you have multiple process, then it will attribute those process more than just single serial execution process, which is good. But sometimes you want to find which application contributes more latencies this program. So the idea is divide the sample weight by the parallelism you detect. If you run this program twice, two CPUs at the same time, you get the two samples, but you divide two samples by two, then you will get one sample. So it will give you a same amount of weight in other samples captured in different time. So with that, you need to track the parallelism. So we use scheduler event, context switch, but saving trace point, whole trace point is quite expensive because it has a lot of information. Right now we have a custom event, synthetic event to cut down unneeded part, but the approach we have is the perp already has a record for scheduler context switch information. So it's much smaller than the trace point. So we use that. And with that, we added latency profiling to identify the serial parts easily. So let me give you an example. This is a perp code on the left side with dash latency, and you run your workload. And at perp report, you can also give dash latency to add the latency columns. Like in this example, the build it profiles the perp build, but when you see the second column overhead, it's a traditional perp overhead in reports with the perp report. It shows 80% of a CPU cycle was spent on the CC1 process, which is compiler, which is expected. And if you run see the latency column, it translates to like 54% of time was spent in the CC1 process, and 21 is Python 3, and 12% is LD, because those Python and LD is mostly run as single-threaded, and CC1 itself may be single-threaded, but it runs in parallel in multiple CPUs. You can see which part of the build process takes more time. So this is good. This is really good, but the most use case is limited in when you profile a single process, or actually a single process tree started from a single process, which means you track the parallelism globally. But if you profile system-wide mode, it will track all CPUs at the moment, or at the same time. And you might not care about parallelism in your application affected by other application from other users. So in this case, we will have multiple origins to track parallelism. Maybe we can just use global tracking of parallelism like we do in the single process case. I think that makes sense in some analysis, but mostly maybe users just care about their programs only and their couple of their programs. Then we can maybe track the parallelism in process level differently. In that case, maybe you can have a multiple threaded application, then you care about how threads are working correctly or not. That's one option. We can support system-wide mode with the latency profiling, or we maybe provide an option to specify from user to which application or process tree you want to track this latency profiling. Another problem is how to track context switch or parallelism efficiently. For system-wide mode, that means we need to track all context switches, which can produce a lot of data and result in loss and some record in the ring buffer. So I'd like to avoid saving context switch data along with the data samples. So I discussed with Dmitry with this the idea was that to like inject perp scale switch information, like we have two path analysis. First path just checks the samples and records the timing of the samples and produce artificial context switch data with the sample information. Basically, perp record use the frequency mode. So you have expected sample rate. Basically, it samples 4,000 data per second. So you expect that amount of sample in a second. If you miss that the timing, that means it goes to idle. That information can be generated, and then we can process that information to track parallelism. Yeah, but actually, I don't want to have the two-pass process to analyze this information. But right now, I don't have a better idea to process this. So maybe, yeah, I will work on to inject this process schedule information using sample data and with frequency. My idea is we expect samples happen in an expected period based on the sampling frequency. But if it misses two period of expected sampling frequency, we identify this CPU is now idle and reduce the parallelism on that CPUs. Any suggestions or ideas? Okay, let's move on to the next topic. Next topic is deferred unwinding. Yeah. Recently, kernel added deferred unwinding support, so we can use in the perp tool. The idea is capture user space text when it goes to. Oh, no problem. Ask questions.
Hi, Nanyun. Yes, I do have a question about your latency analysis. Can you hear me correctly?
Yes.
Very well. So is it purely based on context switch events, or do you also use wait queues and other synchronization mechanism to figure out what are the dependency chains in the workload?
Right now, we only use scheduler context switch events.
Okay, because if you want to do that more accurately, we can discuss later, but there are algorithms you can use that are more based on wake up and dependency chains that you could use to figure out what's the critical path between, let's say, 2 points in a calculation.
Yeah, I think, yeah, that's a good idea.
Thanks.
Yeah, we can talk later. Thanks. So next topic is deferred unwinding. So idea is to collect user stack trace when it goes to the user space. Because when NMI perp samples happens, it usually in the NMI context, which cannot take the page faults. So you might not see all full stack trace in the user space. So if we can delay that processing to right before it goes to the user space, you can be in the sleeper context, then you can take the page fault to get the whole stack traces. And another benefit is you can avoid duplication in case multiple samples are captured while task is running in kernel space. So right now it only supports frame pointer, but I know people are working on to support S frame as well. So it comes with new ABI changes, like we added a couple of perf event attributes and couple and new context format and record format for the deferred call chains. But for the users, it's just a matter of passing this option to perp recode to enable deferred unwinding. And then kernel will generate separate recode for the user space deferred unwinding, and perp report will match those deferred unwind call chains to the samples previously captured. But I think the problem is it only captures user space call stack when it goes to the user space, but profiling can finish before the tasks are going to user space. So I think maybe we can capture the stack trace when it goes to sleep rather than the user space. Then we can share the same stack trace when the task is still in the kernel mode.
We can't use schedule switch. We're going to sleep as the issue. Well, the problem is to look at user space, you might take a fault and do something. And the problem is that just because you go to sleep, you might be holding a mutex that could be also taken in the faulting process.
Mm-hmm.
So, because we originally were going to do that, we're going to say, hey, we schedule out, maybe we'll do it then. One thing that I thought about, but I'm not so sure people will accept, would be to use the might fault, kind of like how voluntary preemption was like, hey, we have these might sleeps. That means that if it might sleep, that means it's allowed to sleep. So if we want to do voluntary preemption, we could just sleep or schedule out at any time we hit a might sleep. I'm wondering if we could do the same thing with might fault. I don't know. That might be a hack. That might be not accepted. That's the thing. This question is, how clean is that to say, hey, saying that it might fault, that means that this call is going to be in position. If you're grabbing any locks that is in the faulting handler, that should set a bug. So that's why we have the might fault in there. So if we hit a might fault, that could be a location and say, hey, we're now allowed to do our stack walk. That was one of the thoughts I had, but I don't know how acceptable that would be upstream.
Okay. Yeah, one thing I noticed in the previous BPF talk was that they're also working the similar approach to get the default user stack trace for BPF. And they have another interface to actually send a signal to that process to capture stack trace, even if it's in the sleep mode.
What do you mean they send a signal to the like if it goes to sleep, it just wakes it up and says, do it?
Yeah, because they want to capture stack trace from the current.
Right. The question is, again, would be, how do you know you're in a safe location that you don't, well, some sleeps, I guess, anytime you're holding any locks, you would be an uninterruptible. So I guess if you're in interruptible mode, if you sleep in an interruptible mode, it may be safe. So that could be another thing. If you schedule out, if you schedule out like a full schedule, not preemption, but if you schedule out full schedule and you're in a interruptible mode, maybe that would be safe to do. I don't know. I have to take a look. I don't know if there's any, also you could have, completions could have an issue. I don't know if if you say, hey, do a stack trace and you do a completion. I don't know. I think locks have to be very careful about that. We could try it, see what happens and see what breaks, but then we'd have to get a lot of buy-in. I would talk to the memory management folks and anyone that's in there and get an act buy from them before we do anything. I wouldn't just do it and try to push it up. But we could do something, send it out and say, hey, memory folks, is this an issue? Well, is there anything that I don't know about that can cause harm? That's what I would recommend.
Or whenever hold the locks, we are uninterruptible. Like I've seen at least some traces, like at least it's from pthread the mutex being locked, but we are not uninterruptible.
pthread, like Futex, you said? Well, that's because that's a user space spin lock. That's a user space lock. So I'm talking about, like, the only thing we're worried about is what happens is if you do this, say, go give me the stack trace says, oh, this is a major fault, and goes to some weird file system that does a whole bunch of stuff and grabs a bunch of locks from the kernel to do that. And you might just happen to have one of those locks held. Now you just deadlock the system. So that's why you can't just randomly say, hey, I'm going to sleep, I could do a user space bin lock. You have to know that when you do the user space, or not user space, user space stack walk, that when you do the stack walk, if you do take a page fault, you're guaranteed not to be taking any locks or anything that could cause a deadlock that you may already hold. And that's where we don't have any really true infrastructure in the kernel. I think the might fault actually does that. So I think might fault means if you have, I think LockDep may even say, if you have a lock, you do might fault, and they say, hey, what, you are only one of these locks that are used in the fault, like the reclaim, like that's memory reclaim is another place. So you get memory reclaim come in there, then you're in trouble. So there's a lot of things you have to be really, really careful about when you do this and what locks you hold.
Okay, yeah. But yeah, without that, there's a risk we don't have user space thread for long sleeping tasks and tasks that.
Matthew, who's up, put his hand up again.
Yep.
Yes. So when you get scheduled out in a faultable context, you may be able to immediately take the stack walk and gather the stack trace. So maybe that could solve it, because then you don't wait until return to user space and you can get it sooner. That's the soonest I think you can get it without having to take it unconditionally on entry into the kernel. I don't know, Stephen, what you think.
Wait, so basically, you mean to take the stack walk if you actually hit a fault?
If you hit context switch, that's taken from a faultable context.
Well, if you do it from the, wait, if you're taking a context switch from a faultable context,
yes.
As long as you're not in the fault handler.
Yes.
Yeah. So like I said, if you take it, what I said was if you take a task switch, I'm assuming that if your task interruptible, because everything in all the locks in the kernel usually take a task uninterruptible. I have to go take a look. Unless there's a timed lock, I think there might be some timed locks or something like that. But every lock in the kernel that you block on, every mutex or even completions and everything else is usually uninterruptible. So you could say if you schedule out and your schedule out, you could do it on the sched switch and say, hey, we're in a task interruptible state. That might be a safe location to do a stack walk. I'm not 100% sure, and I would like to get guarantees from other subsystem maintainers that know this code much better than I do. But that's one solution that may work.
Yeah, maybe.
Any memory management people here? Probably at another. I have to go talk to them. They are in the conference, so.
Thanks.
Okay, yeah, that's one risk I can see. And another idea is to maybe you can also defer collecting other sample data like stack contents or register information, because we use it for dwarf-based stack trace. It can be also deduplicated, like the same reason.
By the way, just want to point out one thing that advantage I like of the deferred stack walking too is you only need to do it once.
Yeah.
It's like a lot of times right now it does it if you're in a system call that's a long system call, you could take 10, 15 stack walks, which wastes the ring buffer and wastes data and all that. So if you only do one, it saves time and memory.
Yeah, right. Yeah, current dwarf-based stack trace requires the capture of whole stack contents and registers. So that's wastes a lot of spaces. So let's move on to the next topic quickly. We switch it to event and metric descriptions in JSON entirely. So each metrics and events are defined in its vendors. And we also support Python language to write metrics more easily. And this JSON can be referenced to external users to understand metrics, events, and more. And one interesting point is that we support event with multiple PMUs together. So when you specify cycles event, you can try to match the CPU PMU first, but it also tries to match another CPU which might have the same name of the event in it. And with that, we need to figure out more information about the PMU. Ideally, those information can be from the kernel directly. Like we have hybrid systems which have multiple core PMUs, like CPU Atom and CPU Core on Intel systems. We need to convert basic CPU cycle events to multiple CPU events on each PMUs. And we have problems to match on-core events which has multiple instances, which provides a different portion of the system. And we need to merge those data into a single data point. Then requires we need to match which PMU shares same information or not. Sometimes it's very obvious from the PMU name, but sometimes not. So it'd be better to for kernel to provide those information. And you also need more information from the PMU capability, like whether it supports sampling by interrupts and which modifiers to exclude some unwanted samples from PMUs. And we also have a pending patch that provides more information about the perp file descriptors using FD-info information. So in case PMU has exclusive events and counters that is taken by another process, then we don't know which process has that. So if the FD-info provides that information, we can provide better error message to users to figure out what's going on at the moment. So this is an example output, not dramatic change, but we now have on the right side, each matrix now defined on JSON, and it produces much easier or understandable output to humans. Next topic is log contention profiling. We added recently a slab object log symbolization support using BPF. And if you have a pointer to the log object and it came from a slab object, you can figure out which slab it came from. And basically, it can just show the name of the slab cache it defined. But ideally, we want to have type information of that struct for a dedicated KMM caches. Also, it needs to it also offset information in the slab object to translate which lock in the data structure it allocated in the slab object, because some large object can have multiple locks, like task struct have multiple spin locks and mutexes, and we don't know which one it is just based on this information. So to improve that kind of information, we need more information from slab and BPM. And one interesting feature is a lock delay injection, which on purpose slows down some kernel lock acquisition passes to check the impact of kernel lock overhead to user space application or other part of the software. So rather than making it fast, we can make it slow. So which part of your program is affected by the lock contentions? But it sounds scary, so we cannot support. We cannot give too much freedom to users. So the limit is now 10 milliseconds for each lock contentions. And we also want to have more information on the lock holders. By design, this lock contention profiling focus on contended path, which means the slow path failed to get the lock at first. But we still want to have more information of the holder, why we have contentions, and what the holder's doing at the moment. That kind of information we have, we support mutex to track the owner field in the mutex to capture stack trace when it hits the contended path. But I feel like it's sometimes unstable. Maybe it cannot capture the stack trace of the owner reliably, because most likely, not most likely, but sometimes the owner may be running on a CPU. One other information we want is lock hold time tracking, which means you need to check both lock acquisition and release path, but that can be very hard. So tracking all the fast path of the lock acquisition is too much. So we cannot do that. But if the lock is highly contended, we may just track the lock contention and path to estimate the lock hold time of the highly contended locks. Oh, we don't have much time, so move on to the next topic. Next one is system call tracing. Perp trace command supports system call tracing like strace does. And we use system call tables to support multiple ABI, multiple platforms. And we also use BPF to gather the system call statistics rather than tracing all the system calls, arguments, etc. We just capture which system calls are called from which process frequently. And we can use BPF, PTF to read user pointers, but now Stephen added tracing subsystem to user pointers in the kernel directly. So maybe we need to think about to synchronize those approach to have better support rather than just rely on the BPF augmentation. Another topic I'd like to discuss is guest machine profiling. So we have perf KVM command to record and report guest profiles, but it's hard to get the information from the guest applications. And in case you have applications running in their own virtual machines, how can we improve profiling the whole machine with application in the guests? So that's a topic I'm now thinking about. And ideally, I just want to share the single ring buffer with hosts and guests per CPU, basically, and somehow orchestrate guests to write the data to the host ring buffer directly. Then we need to provide guarantee for guests to write the ring buffer to atomic manner. Otherwise, we cannot guarantee the correctness of the ring buffer data. And another complex part is mediated PMU path-through work going on. With that, we might not have PMUs enabled in the guest. So I'm still thinking about the idea, but I'd like to hear from audience if you have a better idea or another idea on this.
Damian, I have a question for the guest profiling because as you know, the ARM version 9, CCA architecture have some protect some guard from the host to guest. So I was wondering if there's some plan or some preparing support for that functionality from the ARM-v9 architecture.
From the tooling, I don't. I don't
There's-
have
yeah,
a
yeah.
plan to work on that.
Yeah, I need to ask it to the ARM people. Yeah, thank you.
So the last topic is Python support, and as you see, we have some Python support, and you see in the build profile, latency profile. But we want to make Python application first-class citizen to write a perf application using the sample data. We have a couple of examples, and Ian Rogers has been working on this quite extensively, and he shared a Python app to list all the events in the system and dynamically visualize those information using the captured PMU data at runtime. This is cool. Okay, yeah, that's it. Thanks.
Someone showed me, but let's make sure that it works.
Looking for your slides. Which one is this? I forget. Did
None
we
of
upload?
those.
None of those. We haven't uploaded your slides.
I uploaded it.
Yeah, you did.
I did, but I don't know why it's not showing up for you. If you go to the timetable, there is a
Okay. So when did you upload them?
today or yesterday.
Oh, if it is today.
Oh, here it is.
Yeah. Okay.
This is it.
Yeah, I pulled everything from today.
Okay, here it is.
Okay. Cool.
Okay, so we can start or okay. Hello, my name is Eugene. I'm glad to be here at the Linux Plumbers. So thank you everyone for joining my talk today. So today I will explain a bit about my work in the past year. It's called MEMInspect. Now it's called MEMInspect. And the main goal of this talk is to show you a little bit about it and then to get some feedback from you, because that's the most interesting part for me, is to get your opinion on it, your feedback, and help me improve it and get it better as it goes. Because in the past year, there have been several patch series, a lot of feedback. So what's the current state of the patches? It's thanks to everyone who reviewed and got involved in this. So I will just give you like a quick motivation and overview of what it is, what's the goal, what's the purpose, and then I will show you how exactly it's done now. So this is like a very quick high-level overview of what it is, what's supposed to be do. So in that first blue big thing one, you have like the whole kernel memory, which is big, made of a lot of chunks. And the goal of this MEMInspect is to pick out several things from that memory and recreate it in a smaller state that could be useful for someone. So if we want to inspect the kernel to find out several vital information from it, we don't need this whole memory. And also, we don't know where inside that memory the interesting things for us are. So what this MEMInspect proposes is to get a way to annotate all this kind of memory into a table, that's the lower part of the photo, in which we can find out some vital information about the kernel, even if it's running or it's dead or it's frozen or it's crashed or whatever state the kernel is.
So this is like a high overview of what memory spec should try to do. So I put a photo there in case someone missed the first slide. So as I said, we want to analyze the kernel, but we do not need the whole memory. We can use the whole memory if we want, of course, but that's not feasible in all kinds of situations where you don't have access to all the memory, or maybe you cannot dump it, or you cannot have a way to read it or parse it, the whole one. So what can we do is to analyze this kernel, which is a much smaller memory footprint, so the table below. So why would this be useful, and why would we need that, and what would be the purpose of it? I have a previous talk at Linux Connect, which is the full motivation. There was a Linux MM alignment on that. So there is a lot of background to check. But in short, the idea would be to get some memory and to be able to debug it, to use it, to inspect it, to analyze it, but without the whole memory. Of course, we have this drawback that we are not able to analyze the whole kernel. That's something we have to live with. But in some cases where the small little memory is very small, we can find out some debugging information that would be useful for someone in that case. So the idea would be to do that, to find out this small little table and to use existing tools like the crash tool that can be loaded, can load such a table of memory and then find out some useful information from that. So what is the proposal that I've been implementing and testing it? It would be to mark all those red little regions from the memory of the kernel and then add them to some table for specific purpose, like analyzing the kernel, debugging the kernel, and so on. So we don't need all those pages. All those pages maybe are some unuseful data, some drivers we don't care, some memory pages we don't care. We don't need all that to debug. So what we would need is like some vital pieces. I gave you some examples there, like number of IRQs, number of threads, how many CPUs are there in this system, GIFs, the architecture, for example, Linux banner or the UTS struct, print keyring buffer, and things like that. So all these kind of things help us debug the kernel or analyze the kernel, find out what's going on in the kernel, but without actually having the whole kernel memory, like an usual dump. So how to do that, how to mark all those regions and add them to that table, having some specific goals in mind. One of the main goals is to avoid to interfere with existing code as much as possible. So how can we select all those pieces of memory, all those chunks, without interfering too much? I don't want to barge in subsystems, add code, add a lot of functions, be bloated, add bloat to the kernel, make it more complicated than it already is. So the goal would be to make it as simple as possible to avoid people saying, hey, I don't want this in my subsystem, I don't want this in my code, don't change this, it works like that. But somehow to make this work without interfering so much. And a second goal would be to make it simple, not be so complicated with a huge API, something that would be very difficult to understand and difficult to use. So that being said, I have already 2 real use cases that make this work in a real product. And those are parts of the patch series and can be tested by anyone. So the first one would be the Qualcomm mini dump, which is some kind of firmware-assisted dumping mechanism in which the firmware can read that red table, the one-line table below, and can select all those memory chunks and recreate a small little cute dump called mini dump that can be loaded in some usual tool like crash and then can be read. So with the help of the firmware, we can select all those memory regions and copy them and extract them from a kernel. And the second would be the K-Info Android debug. That's a driver that's on the Pixel phones, and they are using it to extract, again, vital information from the kernel, and they're copying some data into some reserved memory, and their bootloader just reads that and then parses it and gets some useful debugging information from it. So those are 2 use cases that could make use of that and make it work. So during the past year or even more behind that, there have been several proposals on how to do this, how to achieve such information. So I tried to reuse pstore, go through pstore, go through a backend of pstore. There is a link to the patches there. There was an RFC post on that. I made 3 versions, RFC versions of something called KMEM dump, is a previous iteration of all this. There are 3 versions there. There have been a lot of feedback on that. So thank you everyone who contributed there and gave ideas and so on. At some point, the idea was to rename it to MEMInspect because it was too much of a dump in that KMEM dump, to make it like a more generic way of marking memory regions for inspection. So the result is what I call now MEMInspect. And the patches are there in the 6th link. That's the available patches. So that being said, like a quick introduction, let's see how MEMInspect will basically select the data from the kernel. And the first thing that would be of interest is how to mark some static variables that are in the kernel that we want to be able to select in the inspection table. So this is what is done today. There is this cute little macro called MEMInspect entry, which takes an ID, a symbol, and a size. And it creates a static structure in here, you can see, in a dedicated section called the inspection table. And in there, it stores information on this static variable. A specific ID, a specific address to a virtual address point, like a pointer, in fact, and the size. So it will annotate the variable into this table that's created by compilation time. It will be there in this table, and then it can be used by the MEMInspection core, let's say, to create a bigger table out of it. And I've added another cute little macro, which is even simpler than that. Just takes the symbol, generates some ID from it, uses size off, and it's really simple to use in the code with the least interference possible in the code. And to show you how it's done, in this case, when you define your variable, let's say in this case number of IRQs, it will just have a cute little macro, 1 line, simple entry for this variable. And it will store its address, its size into the inspection table. How does this look like? Anyone has any kind of opinion on it? Do you like it? Do you don't like it? You have someone there who wants to ask something.
If there's a lot of some of these small bits of kernel data, it seems like there's a lot of overhead to have a separate table entry for each. Has there been any thought to say putting a bunch of these in a separate linker section where then you can say include that entire section in the MEMInspect table?
Yeah, that's a separate linker section there. It's called section inspect table.
I mean, like putting number IRQs itself in a like .data.mem like .data.critical or something that we then you would have one MEMInspect entry that says here's all the data that we want to include in the dump.
That would be one way, but it would mean that I would need to allocate this number IRQs like that in a separate section.
Right, yeah, with like an attribute, yeah.
Yeah, so it would add an attribute to number IRQs. So I don't know if that would be fine for everyone. I mean, if the IRQ maintainer Thomas would like to have an attribute on number IRQs to be stored in a different section compared to everything else in IRQs. Or all the other variables, GFIs and everything else would be stored in a different section. So if that is okay for people who maintain all these variables, then I'm fine with it. But this was a way to just make it work at some point. But again, what you say is viable. It could be done. Move all the critical variables in a separate section. But it has to be like wanted by everyone. Yeah?
Just a question, but that also means that everybody or every subsystem has to annotate every variable.
You don't have to do anything. If you want your variable to be like marked for inspection, being in the inspection table, then yes, you can annotate it. If you don't care about the inspection table or you don't want your variable to be in there, you can simply ignore it and don't need to add anything. This is like completely optional.
Yeah, but when you want it to be included in the dump or in the data, then you have
If you want to be
annotate.
included, you can just annotate like this, everything. You have your own dedicated driver and you want to annotate a static variable, you do this. And then your inspection table will contain it, an entry corresponding to it. So that's doable and it's optional and it's your choice. You're not obliged to do anything related to that.
Can this be solved with BPF?
I
Sorry,
don't know.
I have to make the joke, but
I don't know.
but the reason I say that is that I find it like when I'm debugging things, usually the subsystem maintainers don't necessarily care about me, not in a negative sense, but they don't want to have to think about the fact that I'm going to debug them. They want to think about the feature they're working on, and they don't want to maintain and add new entries and convert. You know what I mean? They don't want to have to think about debugging. So so like, is there a possibility where you could have this done more dynamically?
Yeah, this is for static variables. I will show you how to do it for like k-malloc things or dynamic variables or memblocks. So I have like 3 different things to do that. Yeah.
Yeah, I think the concern that's being raised here is that the people who might care about doing debugging might be, for example, a company's data center kernel team, and their desire to want to do debugging and what they want to debug may be different from what the kernel maintainer cares about. And so therefore, it might be interesting if there was a way to easily express that some set of variables should be in this inspectable region without having to make, you know, a whole bunch of out-of-tree kernel patches, right? So for example, if we could have a list of variables, it's like, please put all these variables in the inspection, and it's, you know, you don't actually have to modify the .c file. It's just something that the linker or part of the build process would take advantage of. That might be an interesting elaboration of this particular technique. I don't think it needs to be there for the initial, you know, 1.0 minimal viable product, but I predict that when, you know, the data center kernel teams want to start using it, and they go back and try to get, you know, a whole bunch of patches into all different parts of the kernel, that might be an interesting discussion that would take place, and then we might need to come up with some other solution.
Some people are quite reluctant to what they call linker magic. So they kind of say, I want to have control in my C file and not know what the linker magic is doing. So, David, you want to?
So I agree that sounds interesting, but I like my understanding so far was that usually you would use kdump in an environment and you would get everything you need. But what we are focusing on here is primarily like these devices where you only have like specific, like small areas of you can only store like a certain number of areas where you can actually dump something. And most of the cases that you identified here that you add, for example, number IAQs, is actually to get kdump even like do like not kdump, but the crash tool actually do something reasonable, right?
Yes.
So it's like all like what you focused on is like the minimal number of variables that you need to even get like crash to even identify something.
Yeah,
right?
and I will show you how crash will load the image with like 50 or so minimum number of things that crash really requires. Because when crash loads the dump created with this table, from this table, it will try to look how many CPUs are there, what's the root section of memory, and so on. If something is not available, it will crash and say your dump file is broken.
So like regarding the point about data centers, do you see a use for data centers with that, or is like a data center they just use ordinary kdump and like they have
Some people use ordinary kdump and that's fine for them, and they have enough storage to keep ordinary kdump. But
well, yeah. So I think if you have, I can imagine situations where if you have a very, very large number of machines, you're running at massive scale, like you're a hyperscaler, and if some of your customers are really, really paranoid about not having any kind of PII or customer cryptographic information leak into the KDump, this might be a way that you can actually get KDumps when you might not be allowed to otherwise, right? So I could imagine use cases where that would matter.
I'll just quickly add that.
Sorry.
And that's exactly the another use case we have. We just presented 1 hour back for the trusted VMs, where we use this framework or version of it. And I'm from Qualcomm. We are using this from last 12 years for mobile. And we do this for encryption the memory, because with this trusted VM dumps, we do not want some of this information to be leaked up. At the same time, we want very small memory. You can have 2 MB or 3 MB of that dump just for RMA purposes. On the device, you can just dump it over eMMC and then send it to Qualcomm, and we can just look at it. That's enough information for us to start analysis.
Thank you.
Okay.
I mean, just to your point, like I think traditionally you would use like make dump file, and make dump file just throws out all of the user pages, and you could throw out other stuff. But I think then like meminspect would come in handy, that you could say, well, actually, like I need like these areas, and I don't care about like hardware limitations, but it's actually like used in a different context. But that makes sense. I think we roughly discussed something like that, to exposing that to user space somehow as well, these areas, or including it in the what is it called, the VM
Core Info.
VM Core Info, exactly.
Yeah, one of the patch series, the V3, uses all the implementation moved to VM Core Info and having a lot of things there, but it's also a bit tricky with static variables and dynamically allocated memory, which is not named. Let's say you malloc into an array with a pointer, and then you save it somewhere. It would be difficult to parse or to find. So coming back to one of the questions that was asked about dynamic memory and so on. So this is like what I did in the latest patch on dynamic memory, because we had this discussion on whether we should put wrappers, which I personally disliked. David also disliked the wrappers on the mem block. So I was trying to be as least invasive as possible to add like a cute little flag, let's say, where we could not modify the API itself for memblock. That would be the same, and people using it would have to say the same, no change. But it would add like this API that's already is in the memblock with mark something and clear something. So there are some few APIs there already that select flags like from that list. You can mark scratch, clear scratch, or whatever. So I added these two little APIs to mark a memblock for inspection and clear it from inspection. And that flag is there. And then in your code, you just need to call this function, mark inspect, when you do a memblock alloc. So this would be like a minimal interaction with memblock, because some of the things that crash tool wants when it loads a crash dump is to have access to all these kind of mem sections, to read them and recreate the table inside the crash memory. So those are needed by crash tool. And of course, maybe someone else wants memblocks. For me personally, not really, but crash tool wants those. So how is this API looks like if you just need to call this mark inspect at some point when you're allocating, and then when you free the thing, you can clear inspect, or that could be done automatically if the memblock is removed or unlocked. But most of these memblock allocations are never freed, like sections or something. They are allocated at early boot time, and some of them never freed, like ring buffer, for example. It's allocated and never freed during the lifetime of a kernel. So we don't really much care about clearing the inspect flag unless maybe someone wants to reallocate the buffer at some point. But even if so, and if we don't clear the inspect, it will be just another section in the table that would be more or less useless. So how does this look for you, David? Do you have any opinion on that? One thing else, we could put this flag inside this memblock alloc or panic, but it was a bit difficult because all these flags are masked inside memblock API. This goes to some other API, and then it uses an API to get flag, and it looks up the flag corresponding to somewhere the memory was allocated and so on. So it's not a flag that's passed directly from the user like this mem-block alloc.
Yeah. So I think the question of whether or not it is acceptable to have a couple of extra memories dumped really depends on the requirements of why it is that we're trying to do this. If this is, for example, a way to be able to get debugging information out of a confidential compute VM, for example, then we absolutely would want to make sure that when you free memory, that it gets taken off of the dumpable list. If it's just to try to minimize the size of the K-dump because it's a consumer grade device, and if you leak a little bit of information, not a big deal, you don't care. So I think it really depends on the assumption of why it is that you're trying to do this thing.
The answer would be to cover cases for as many use cases as possible. Yeah. So if the confidential computing feels like this should not be there, can be removed. So if it's something that it's usable by someone. So I want to make something like a more generic API that can be used by multiple use cases. So someone using this feature would have to be extra careful if they want to do like confidential something, or if they don't care, then they simply don't care. But the API and the implementation should cover like helping everyone. That's what my take would be on that. I don't want to focus on a specific use case because that would make it very niche or very specific to someone and would not be usable by anyone else, you know?
Yeah, so we had the same question in the morning when we presented trusted VM one, then the confidential compute. So I just talked to Anish a few minutes back on the RMM side for the ARM CCA, right? So we have not reached to that stage. The problems is similar to what you are explaining, but adding the design of RMM and the CCA for them, we have not reached to the use case of this, but we need to solve the same problem there, including the encrypting the memory when you are doing a dump. So we can do another backend is what we just talked for 5 minutes to maybe when it comes for this development of MEM inspect with the over RMM. So
yeah, so when the users of this table come into hand and they want to use it, then they can selectively pick areas from that red line and then create their own whatever they want to do. So the MEM inspection API would be usable by anyone who want to tap into this table, and I will show you exactly how consumers can tap into that. So that's one other thing to discuss after we discuss a bit on how to select the memory, and then I will have a slide on how to use the selected memory.
Just one more thought. I mean, we briefly heard that like it would be nice if you could just pass in like a number of like names and then like magically you get the right things. Did we explore how we could use debug info to at least like for all of the variables derive like what would be there? Because at least like for the static stuff that like the debug info contains like where is which variable, how is it called?
When you
like,
load the dump with Crash Tool just reads the symbols from VM Linux, which contains all the debug information, like structure sizes, offsets, names, and everything for all the members. And then Crash Tool batches what's in the debug symbols with the actual data from the dump. So you can see all the members and the structures and stuff with the debug info from VM Linux, and then match it with the actual core. You cannot use Crash with only this dump because you don't have access to the actual information, structures, members, and so on.
Yeah, I believe, David, you thought about excluding variables by passing the debug info. Is that correct? Because that's at least something MacDumpfile can do. So you can filter out certain memory regions from the dump by parsing dwarf info.
No, that's not what I mean. What's rather thinking like we annotate like all of the variables right now in the kernel which we want to have like part of this table, and I was just wondering like if this could be more dynamic, that like if we have the information in the debug kernel somehow in the kernel itself like composed, that you could just say, well, like this file like tracing or whatever, like this file and this variable, please like include it in the next like in the not included in the dump, but included, for example, in stuff that I want to have in my static areas. But make dump fighters like it's later stage. Like I'm talking about, like you're running on the kernel, you want to include something in these areas or whatever. So you would just like, instead of like annotating all of the variables, you would instead like somehow be able to derive that from debug information.
Yeah, or annotate the whole file, the static section or something.
I don't know like how, but I'm just wondering, like the debug info, we have all of this information, and if we could compose that into something that the kernel could just load, and you as a user could say, well, like instead of saying like number IAQs or whatever, I can say, well, like this file, like number IAQs, and it can just map it. Well, that is located here in memory because like the kernel got loaded, whatever, it can just like derive that. Then you wouldn't have to annotate at least all of the static variables that we have somewhere.
Let's explore that. Yeah.
About generating like a list of addresses that you would then like say parse the debug info from vmlinux.o, generate this, and then embed it in VM Linux, or you're saying like have a like a debugfs or something that you could at runtime load a the first. Okay.
So those are the memblock cases. So I have also some other use cases that some random subsystem or driver want to register some memory into this inspection table. So I created all these function calls. So right now this is not at compile time, this is for like dynamic memory. And again, it's something that the user should just pass an ID, a pointer, or a physical address in this case, or a size and a type for this memory. And this will be added to the table at runtime. And I will give you an example here. The kernel config data, for example, that's stored in some assembly section. It is there. It adds in the assembly section some markers, and then the kernel config data. So to just add that to the table, it would be useful to use this API with a virtual address, like a pointer to the kernel config data, with a specific ID and with a size. So in this case, I'm making here a small little computation on where exactly is the config data in the memory. So this will be exactly added to the inspection table with a pointer to that address with that size, so it can be then selected and for analysis. So there are all these variants of combinations with an ID with a physical address, or just physical address, and the ID doesn't matter, or with an ID and a virtual address, or just a virtual address, in which case all the IDs are derived from that. So this would be for like a dynamic address. Any opinions on that? Does this work? Is it fine to do it like that, or you have maybe some better ideas on how to just select some data that's in the memory? We have a pointer to it. It's not a static variable. We don't need to annotate the pointer itself, the kernel config data, but rather the memory which it points to.
I'm just curious, like we talked about, like when you say dynamic memory, is it all about memblock allocation, or are you also talking about like...
Memblock is done in that part because there are some things allocated with a memblock, but not part of the kernel allocator or some part of other sections or stuff like that. And that memblock things like mem section and stuff like that, number of section roots and so on, like for example, the kernel ring buffer is allocated using memblock. Some other things are, we have a pointer to it. There are in a specific section, like the kernel config. It's written after you build the kernel, there is a Qtl script that takes the config and places it into the section. And then you have some assembly code in the kernel that gets your pointer to that config data, to that actual.
So like what I'm wondering is like as soon as we're dealing with other like virtual addresses, right? Like memblock is mostly like virtual to physical, like you are contiguous. As soon as we would deal with virtual address space, you might no longer have physical continuity.
Yeah.
And I think at that point you would have an issue with, but I don't know, you have two pages in your virtual address space, and it's actually like two different physical ones.
Different physical,
so you could not possibly include that like in one of the sections. I'm just trying to like wrap my head around like how you would handle
the
that.
table would hold a pointer to the virtual address and the size. So anyone trying to use that, if it's larger than one page, then obviously there is something that has to handle that when passing the table. If it's big enough, you have to probably register multiple regions, depending on what you want to do with that inspection table. What the consumer wants to do when parsing that table and finds out this section, these entries too big to be contiguous. So that would be like the freedom of the driver or the consumer that wants to parse the table. So at the moment, I left it for the consumer to handle that.
So if you're doing some sort of like post-mortem memory dump, then you might require the memory dumper to do page table walks then to do that lookup?
Either at the memory dump or maybe at the driver level. For example, I will give you an example for the Qualcomm mini dump. The Qualcomm mini dump, it will look into the firmware will look into that address, and the driver itself will walk the table and find out the address. It will convert to a physical address, and then if the size is too big, it will have to create some multiple entries or whatever it's doing specific to that firmware needs. So it can be that the firmware could walk the table, or it can be that the driver would walk the table at the moment it registers the memory with the firmware. So that can be done ahead of the firmware actually interacting with the memory itself. It can be post-processing after MemInspect comes to play. The driver could post-process it however it sees fits. So that's one way of doing it. So that's this option, and let me show you how consumer drivers will interact with the table. As I said, there are two ways to interact right now. So one way is to traverse the table. So I just created like a callback function for each entry that will get a cookie and an entry. And then the consumer driver will just call traverse with this callback. And the MemInspect code will go through the table, the inspection table, and call the callback for each entry. So what you were asking is what happens with the driver. Driver will just traverse the table. It will get an entry with a virtual address and the size, and then it will figure out, do I need to register this into, I don't know, my reserve memory? Do I need to copy it? Do I need to save it? Do I need to pass this to firmware? How am I passing this to firmware? Am I passing it like a physical address? Am I passing it as a virtual address? Is it too big to be passed as a single entry? Maybe I need to split it, things like that. So right now, I let the driver calling traverse to handle that. So the inspection table should be, from my opinion, as simple as possible. Just call this callback for the driver, and the driver wants to, I don't know, ignore it maybe. He doesn't care about that specific entry, or he needs to parse it, or needs to do something else. One idea was to have like entries with different classes. So different consumers would be interested in a specific type of entries. And another way to get interacting with the table would be to get all these notifiers. So I created this like simple wrapper on the notifier. So I'm a driver that handles the firmware. I want to know when someone wants to register some memory in this inspection table. So when someone calls register into inspection table, the MemInspection code will just look to see how many drivers have been registered to be notified, and I notify them all. And again, there will be a callback called saying that, here you go, you have a new entry, or some entry was deleted from the table. So you can adjust if you want something was removed or something was added after you traverse. So the use case would be traverse at probe, get your table ready, look into what's done before your driver probed, and then register a notifier if you're interested in some new data that would be coming up at a later point. And that's how the notifier call does. So unlike previous versions which I had for KMemDump, where there was a specific backend that could be connected and removed and so on, with this system, you can have a whole bunch of drivers that would be just connecting to the table whenever they want. And you're not limited to just one driver accessing the table. You have anyone using this API can access that table and can traverse it and be notified and so on. So I don't know if this is better or not. There's pros and cons, I guess. So your take on this? Anyone has any opinion on how to access the table itself.
So you're maintaining a table and you're also having a notifier that can get called back, right?
Yeah.
So
Yes, so.
I'm just wondering, like, it seems to me like only one is necessary, unless you, in the sense that if I would like to have a table of all the useful memory regions, then I write a driver that holds that all in one array or something like that, right? Which is what this table that you would traverse does. So I could just be I could just get notified, right?
Yeah.
And then if I guess I'm maybe I'm overthinking this, but it seems I like the idea of the callback that then you can report it to firmware or something. But then is the memory used for this table not really important or being wasted if the firmware callback is just talking to firmware each time? It doesn't need a table in memory, right?
The table just holds addresses and sizes. So it's quite small and not really memory impactful. So it does not copy entries into the table. It's just holding addresses to regions.
Sure,
So
yeah.
the firmware is just like a pointer and a size usually, and the type. So it's like a pre-allocated table of 1,000 entries or whatever defined macro you have there, of, I don't know, few hundred kilobytes. So that's a few hundred bytes, like 1 or 2K, 4K, something like that. So that's the whole table size.
I mean, fair enough. I'm just saying, yeah, I was just saying that.
If it were to copy regions, that would be a different thing.
Yes,
Having just like a metadata for the regions, in fact, the table is like a metadata for the regions.
Yeah.
Okay. So that's the API. I have here some additional info. Just this additional info
Maybe
is
question for you and others as well. Like, what's remaining to get this accepted? So from last 6 months, we kind of made it more than Qualcomm. Of course, some of the comments also we resolved and kind of made it better. So what else you are looking for to get it accepted, or you see that some of these issues are open? So you know any blockers to get it accepted, or you want to share?
right now there should be more people reviewing it and get more opinions on it.
So definitely, I want to openly say here, right? And maybe I'll mention it on a mailing list too. Qualcomm will use it. Qualcomm will convert this driver and use it in mobile, auto, IoT, XR, VR, or whatever you call it, Linux or Android-based products. So we are going to use it. So if you get it accepted, of course, we have our version of it, but we want to move it to upstream version, which is better for us. So just if you want some assurance openly.
All this Minidump works in downstream and on the products that Qualcomm is selling. So they are using it in a downstream way.
Yeah, but
this
we
would
will
be
switch
a way
to this one.
that would be upstream and usable by multiple people. So one of the
But
goals
auto already needs the upstream version, by the way, just because of the safety reasons and other stuff and compliance and everything. So the auto, we will switch to that. And of course, we'll switch it everywhere. So just in case if anyone wants to know, like, hey, what is the use case? Is anybody going to use it? Once you upstream it, so it's using downstream, I hope they're not going to continue using the fork, etc. Right? So
yeah.
Sorry.
Here I had some cute little slides on how when
So,
loaded is to
to upstream use case, if you haven't already participated, you could go talk about how you're using it to any of the patches that are on upstream. Oh, I mean, right. You have to go review and say, hey, yeah, right.
Yeah, so this is how it looks when you load the dump. It reads a lot of information like usual crash tool. So it finds out all this kind of information from the dump, from the table that's created by the firmware. You can read the block buffer and so on. You can print GFIS, you can print number IRQs, as I said. And of course, when there is some region of memory that's not available in the table, in the medium, in a small table, it will just say that it cannot read. So that's expected. That's what the goal is, to have a small little memory footprint dump and be able to analyze some of it, of course, not with the whole kernel, but with some of it into it. And as Trilog said, I'm eager to I thank you for everyone for all the feedback, and if you have ideas, if you have things that look like a red flag, say no, this is a blocker. I'm totally against it, or something like that. Please come and tell me, and I can think of something to find a way to accommodate everyone's needs, because this I know will touch some various aspects of the kernel. So, and also if you think that this is fine and you're happy, then let me know on the mailing list here to see how could this go into the upstream kernel. Which way would be the best way to do that, how to get there. So that, because that's the goal, and to have people in production really using this, because the user is there, the people are there. It's just a matter of getting it done in a way that helps everyone. It doesn't upset anyone, it doesn't bother anyone, it doesn't barge into things that it shouldn't, and it would be something that will be helpful. So yeah. Any other last questions or comments or something on the chat? There is nothing there. So, oh, one question there. Ball.
We're out of time, but
Yeah, last question.
Yeah, less a question, more a comment. So at least for the KDump use and for us as a big distribution, I don't think it's very useful in this way, because we have to support a lot of different hardware and different combinations and everything. So figuring out what piece in the driver is important, etc., is very difficult on this, big and very or diverse environments. But where I could see a use in what Ted also mentioned is maybe if you could also have a mode that negates this table. So instead of saying, please include this data, please exclude this data, because it's maybe some sensitive data, it's some, big IO buffers we don't care about in the dump, just to, give make dump file a hint and make it easier for make dump file to say, okay,
everything is excluded by default. So if we want to block something from being included or something like that, yeah?
Yeah, but that basically says, okay, I need a huge table with everything included, except maybe those small parts. And then we had a mode like that says, okay, we include everything from the kernel except for those buffers or those keyrings or whatever.
I get it.
Sensitive, then it would be a lot easier for us.
Could think of something of that. Another use case I could give you is with pstore. Pstore could tap into the table at panic time and collect data, store it into RAM oops, MTD oops, or whatever, and make it available after reboot. So that might be useful for someone who does not have the firmware or the hardware or something that's involved. So there could be an implementation of a pstore, let's say, driver that would tap into the table and store it in a panic handler. So I didn't have the time yet to do that, but it was an idea that came up, and I think it's pretty neat to be able to read in pstore some binary data or some information that was in the previous run, except the message or whatever pstore is doing right now, today. We're out of time. Yeah, thank you very much. If someone has any other things to discuss,
you can continue the conversation outside, and
yeah, have a nice lunch and see you.
And there is a raised hand, but we're out of time at the moment.
Sorry. Feel free to contact me, and if you have a raised hand, just ping me or find me somewhere. Email me. Thanks. Bye.
Thank you very much.
Symbols or only for the exposed ones?
I mean, almost always. But we're talking about, yeah, it depends.
I thought it would be like, it would only be for the exposed symbol, like the global variables. And we're again in global variable land where the.
Yeah, okay, also. And then obviously that's a configuration. There's big KL symbols, there's big KL symbols.
Yeah.
And so exported.
One of the key things is that I mean, like, I would say that like there's some way that you would need to say without all of the simple, so like only one selected one, for example, you could like list, like instead of like hard coding that, you could have a list and we could only include that mapping, but right. Except during build time to say like I want these or not, because then you wouldn't have to annotate all of those study values. Yeah, no, but I'm not talking about crash tools, I'm talking about the
The leader do that. I had the leader magic as I go multiple list of variables, search where are they? Where are they?
Right, and if you could go so far and say, well, I'm going to create a list of all of the variables, right? Like that might not be your use case, but all of them, but I like essentially SI, like for example, if I'm in the rooted kernel, I could just say, well, like now, like please enable like dumping of this tag set. Like I know like where all of them are residing, I don't have to annotate them, but like dynamically, I can just say, well, like no, use that. Your ID essentially would be like the file path plus the variable name would essentially ID.
Index.
Yeah, or something, but essentially that. I mean, you might decide, well, I don't want to have like all of the annotations in there, only like a subset because it consumes way too much memory. But then you could essentially avoid like annotating all of the static variables.
Or we only need to annotate ones that aren't already in chaos.
Yeah, for example. Then it's like your key would be that, and like for example, for your default use case, where you know, like in order to get the crash tool to even realize something like that, you could just have like a static list that's always like enabled, for example. You could also configure that at compile time, and then you could just do the right thing.
It sounds like things that are always needed by a crash tool. We're going to be info, or there was actually but then it doesn't be used completely. You see it's a single table, right? That happens. You see being able to put offset when you show that measure, smile that measure. So just offset, even real address. As the offset, and then read exactly what the order that's the address. That's very good. So actually those are the problem in the case that the public learner does not know which memory.
Exactly, that's something you could right, but then you would build a table using like static assignments. You would calculate it. You could probably also like I mean like the simplest one thing. You also need the size, but the size is also non-complete. But yeah, and that is something you would read. But then you could just say that thing and like you could build a table without static annotations. That's what it could. Yeah, right. Yeah.
Usually that doesn't work. Like if you get a backtrace that is just you need
like function plus offset slash size, right? That size comes from
that's usually size, yeah. If that's in the kernel log, actually, if that's done in the kernel, then I'm almost certain that they're just using that simple start. That's almost always.
So even does that previous section is next plus size plus size.
Yeah. So there's no, like the VLF symbol actually has a size field, but in the chaos.
Yes.
Which is funny because like on x86 for CPU start, it's 0 or something very small. And so like a null user space address sometimes just created as per CPU start plus 7 whatever, huge large.
So treating the offset to the next symbol chaos sort of works for functions where you assume that like all the functions are laid out more or less continuously, but if we're trying to dump data symbols.
Well, data symbols generally work too because like you have S text, E text, S data, U data. So there's always going to be a symbol at the end of the data section, even if it's the last variable of the data section. So you can get away with just assuming that when that's symbol is your, is the end of what you're trying to do.
All those sequences that you mentioned are like the linkers, that's the end, they're not a compatible file. So Android wants those. No, all those signals. And if I just annotate them in a way, in a C file, you not link. That's the second step. The second step is actually go into the size of the text. Yeah, and then place the value there. Yeah, it's more tricky to
So when you would just integrate a new section out of like existing sections, those processes step right.
These are variables required to belong to PLCs and then create another table section that
Yeah, exactly.
You should look at the resolve UTF IDs program in scripts. That's exactly what resolve UTF section pre-populates with a bunch of zeros. Say, I don't know, it's types ID, place it here, and then after the current survival,
Actually looks at the.
and replaces them. So,
but people math for everyone, selecting a bunch of variables, like math for people who didn't kernel will develop here. You find out that some of their static variables are inside of the external lists and blinkers. Gets addresses to that and creates table. With my annotation, it's like here's the variable.
But that's exactly the point that you like to do, would only be like adding or selecting entries and not
hidden. Yeah, but problem with that is, so also can mention that, you know, upstream maintainer usually doesn't care as much about the target compared to the downstream, this sort of people, and especially when you have an old kernel, which is still supported, you need a way or easy way to say, oh, I want to have this variable included as well. And you don't want to patch your kernel too much.
So you used to write where you used to.
These are users. What you may take or what? So basically that would be, I know continuous changes happens, but you know the nature of big information you need. Get started, but in the as if both of you are very limited on your heart. Oh yeah, except for us, yes, yeah, because you don't have this customers which are using just everything.
And you get a bucket report, and then you have to find out, okay, how much information do we need?
Exactly. There's the hard version, very frequent. Yeah, that's why. So for us, it's a bit more complicated. Yeah, for server, yes, because you get the data of this.
It's certainly an interesting point, like to look into if that's feasible, like it's not the aesthetics.
Came up in the inspection. The function ID is not here. Oh, it is somewhere. Yes. Okay.
Every distro I know and all versions all have
Okay, that's good news.
I
didn't check on GKI, but GKI did not use that.
So GKI has that.
As a
That's the only Android, so I have this table of like all the different things. I can only be able to pay for Androids.
Okay, yeah, that's good. That's only fun to use, yeah.
So, yeah, they all have tables.
This whole inspection be like red kernel or some you need to go. Yeah. I'm sure others too.
Yeah.
Because there was a discussion, should it go to should it
I think like the moment you actually start using like like tool information to like create this table, then maybe one of the biggest part is
yeah. You go to slash kernel. Right now, it's structure. Where most of guys. Oh, okay. Yeah.
You know, yeah, I'll show you how to pull up your slides. And see how you want to do this. That would be-
Do you know if it's the whole screen that's shared or just that application? Because if I open the link in YouTube, will the
Okay, so things work a little bit differently here in terms of there is, so let's see, we can pull up your slide. And then which one? To refresh my memory on.
PMUSB?
All right, and then, so wherever you have your demo, you can click on the link to see how it's there.
And how big is that? That's readable. Okay. So. You can see like a.
It's a PDF, so you.
Should, like on my phone or my, I was able to do it earlier.
Okay, let me see.
Maybe I can just bring it up and have it ready here.
Yes, let's see if you can.
Picture of it. So. Small keyboard.
That's, maybe it's the access issues.
Oh, wait, it's U.2. That's right.
I wonder if you can select the whole
Oh, wait,
thing.
still on video.
Yeah, okay, let's see. Okay. Oh, yeah, did you see? Oh, okay.
There was a little
Oh, yeah,
button
the
that pops up.
training. Yeah, the training that,
I missed
remember
the
the
training.
training? Did you miss the training?
Yeah, okay,
Yes,
so-
that's how you.
Okay.
So is it,
Perfect. And then,
I don't know if it's actually showing.
yeah. Oh.
Show, try that again.
quality
External
of-
video. I think, yes, that's how, I think Stephen was mentioning, that's how it works.
Let me try to play.
I thought you were.
Yeah,
you were
it's
able to
working.
try it. Oh, yeah,
It's
yeah,
running.
that is, it's running. Okay.
Yeah,
Then,
but my plan is to like skip around. Hopefully, it doesn't buffer too much.
yeah. Okay. That's good.
Yeah.
Figured it out. You can exit that and then we can go back to.
Okay.
Now you're good, right?
Yeah.
You can do this.
And can we make this like a little bit smaller, maybe, so that the like this window, just so that.
That's how it works because we have the chat. We need the chat going.
Yeah, but like
because we're
this
people.
part right here, like if we just move it like that, or no.
Let me see. Yeah, I think you can do it. The other one is not changing, which is good.
Yeah, you just need that,
Right.
right?
No, I mean that screen is coming from someplace else. That's fine.
Okay. But yeah, that way you can people can.
This one doesn't change.
Oh, that one
So
doesn't
that
change?
doesn't change.
Oh.
That's what I'm trying
It's
to
coming
say.
from there,
Yeah,
okay.
it's coming from there. So
Okay, yeah.
you got to, yeah.
But you guys want to see that over there? Because like it makes it harder to see some text on the.
I
not
mean,
your-
we just have to deal with
Okay.
it, I think.
So let's get out of this.
Because that's where that's controlled from.
Okay.
Because I don't want to change that setting because people need to see who it is. We
Right.
want to be able to see. Can you make this
Back.
back
Yeah, yeah.
where it is? Because we need to be able to see if somebody is raising their hand or speaking or
Yeah.
all of that. So
Okay. And then,
then-
is there anything else I should know about? Because I didn't do the training. I think that's it.
well, I mean, that's
They
really I
told
mean,
me that.
pulling up your stuff.
Okay.
That's what you do. When,
Okay.
Wherever your stuff is when I ask you to come up.
Yeah.
That's really what you need to do.
Okay.
It is. What's going on? I mean, it's not pulling. We need to get out of this.
It's not going out?
Yeah, we need to get out of this.
Let's see. Actions.
How did you go to the external?
There was a button like this plus.
Yeah, right. You need to get back to the. Can you?
No, I don't want to.
No, no, no. Let me see. Yeah, we need to get. You need to probably need to get back to that.
Like if I just do.
That's what I did default, but it's not. It's showing, but default is behind it. But we need to get out of this. No, 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 no. Not
I
that.
messed that up.
No, no, no. Yeah, get out of there and then. Okay. So let's see. We need to exit this plot.
Yeah, I don't see any options.
Actions.
Maybe that back button, maybe.
Because I selected this and it's not showing. Oh,
Because we're like in the media player.
no. Watch later.
That's in YouTube. That's all YouTube.
Okay. Okay.
Can I try something?
Yeah, sure.
How did you get the other pop up? Here.
Yes. No, we are going to leave. We're not going to. We are going to leave the page.
We don't want that, right?
We don't want that. Okay, let's see. I need to figure out. Okay.
Oh, here. Is this minimize?
No, 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 not that. Okay. I need to figure this out. I don't
Should
know.
I ask someone else?
That's fine. That is fine. Let me see. Actions. How do I get out of stop?
Stop sharing. That's what.
Yeah, exactly. There you
There
go.
we go.
That's good.
Okay.
That's you need to probably know too because
Yeah,
you
let me
need
practice one more
you
time.
need to switch back and forth.
Yeah, but so this icon here changed. This audio one. Do we need to fix this? Because that was blue before. Like the join audio.
It needs to be green. It needs to be muted. No,
So
no,
we don't wanna
don't
do that?
don't mess up. Don't mess with any of that. This one needs to. Oh,
Because this was blue before. That's what I was saying.
that's fine. That's
Okay.
fine.
Can I just?
This is blue.
That was blue when I touched it,
Mhm.
and now it's not. So should we be on listen? Or no, we want to be microphone, yeah. Or is it doing
Okay.
this microphone?
Actually, that's I think that's fine.
I think it's
because
okay.
know
We don't.
I know
The audio is
that's
over there.
Audio.
I think. Yeah.
It's fine.
Okay. Let me just practice
Okay.
one time. We know how it works now. So.
Yeah, yeah.
And yeah. So that's the icon. Still a
And then
video.
you do
And then that brings us to the link.
right,
And then what you do is go here.
and then you do stop.
Stop.
Yes.
And then you're back. And since you want to go to default. Boom.
Yes.
All right. Thank you so much.
Of course. Figure that out if we haven't.
Well, I mean, there was quite a bit of discussion happening here. Right now, really capture. That's cool. So if you are, you'll be able to just kind of list what you develop.
I probably know how to do that, but otherwise, I think it's probably locked at the moment. Okay, so just pull up your slides. Probably already know how tracing, that one? Yeah. That one, okay. And then that's pretty much it.
Yeah,
I think it's
thank you.
already up, and you can just start whenever you feel good. 2 o'clock, 3 o'clock is the time.
Okay, yeah. Okay, it's a time, so I will start. Thank you for coming to my talk. I'm Masami Hiramatsu. I will make a talk with a talk for Linux kernel tracing, recent technical update. So, So here is this agenda. I will cover the three areas and conclusion. I will start from foundational stability and access, and also the tracer updates and the probe and event updates. Okay. So the first one area is the foundational stability and access. So that will cover the tracer for stability and accessibility improvements. The most important updates in this area is resilience. So that we introduced that persistent ring buffer, which allows us to to keep the trace data between the reboot. So that if you get the reboot, machine reboot, one the ring buffer is actually that keep the data. So that is actually that based on the reserved memory area, so that this will the kernel will allocate that the reserved memory, and the ftrace actually that allocate the trace instance, so that the trace link buffer on the reserved memory. Of course, when we reboot the machine, the kernel address randomization and also that module address are different. So that this one record that those offsets into the buffer, so that you can solve that the kernel symbols from the address in recorded in the persistent ring buffer. So using this, you can get the trace data in the last minutes of the crash. To use the tracing, the persistent ring buffer is very easy. You just need one pair of the kernel command line option. The first one is reserve mem, and the second one is a trace instance. So that the reserve mem, for example, this this one shows that the makes the persistent ring buffer instance as a boot map, which size is 12 megabytes and which is 4 megabyte aligned. This alignment is a bit important because that the kernel the kernel boot we will allocate the persistent memory, the reserved memory, but if we don't align the memory on the in that case, if we run the kernel with the Casra, that will randomly shift the address. But with the alignment, it will keep the same address. Yeah, line. You must say that. Sorry. So real use case of the persistent ring buffer, real example is here. I actually hit this issue when I set up the customizer overflow handler for hardware breakpoint on the ARM64. Actually, it freezes machines, and I couldn't find what happened. So yeah, I prepared that persistent ring buffer and enable all events on it, and also adding one trace trace print K handler on it. Then cause the same issue crash and get reboot the machine afterwards and get the persistent ring buffer, and find that there are many events happens right before this freeze happened, but after that I only see that there are 2 or 3 types of the events, and repeated that on the persistent ring buffer. So I found that the other, and also that the address is the same. This means that it will repeat on the it will repeat the hardware breakpoint, so that the watch point break on the same address. So I found that I need to one more single step on that. Yeah. So there are new feature on the persistent ring buffer. There is a backup. To other one trace instance equal backup equal boot map. This one will copy the boot map persistent ring buffer into backup instance. So with that, we don't need to care about persistent ring buffer to be overwritten. So that we sometimes, for example, this case, bootmap persistent ring buffer is used for recording many scheduler events. In that case, when the kernel crashed and rebooted, the kernel start recording the scheduler events again. In that case, the previous boot data is overwritten. So before that, we need to make a backup and to read the previous data. So this can help that. Okay, the next one is the tracer updates. Okay, the first one is Cisco tracer with user context access. So that previously we Cisco events only record that the parameter value itself, but it doesn't record the context, content of the buffer. For example, what what file is open, or what data is written to the memory, to the some FD. With this feature, we can see that some the data, actual data of the system call. So that this means that it will provide that mostly similar to the S-trace feature without any tool. The next one is a function graph tracer with parameters. So actually, Dr. Steve Rosted working on that and enable that. This one is a function graph tracer plus BTF. So that BTF provide the type of the each function parameters and the return return data. So that based on that, we can decode the parameters and show that the parameter name and also that the values with the function graph tracer. So that this means that all function call will show with the function the parameters and return value. Yeah. So the last one, last area is the probes and events updates. Yeah. If you have any questions about, do you have any questions about the previous areas? If not, yeah, I will continue. Oh, okay.
At Open Source Summit EU, Tim Bird was talking about speeding up boot time and identified initialization as a place where boot time, he wanted to measure that. Would this help with that at all?
Yeah, you can, let's say that you can use this trace instance so that you can specify that any event, kernel event on the to the trace instance, so that you can after boot you can get that those events from the instance. This actually that have more options to stop the tracing after boot. Yeah, that will help you to get the kernel events data. Yeah.
Thank you. Yeah.
Yeah. Okay. Sure.
Yeah, I'm curious if it supports the function tracing as well.
Yeah.
Oh.
The function. Yes, I think it's. Function tracer is enabled on some specific instance. Can we do that?
Oh.
Yeah,
repeat the question. Or did someone up here ask? Or? Yes, you can enable, it's ftrace, if you do ftrace equals, it will enable the whatever, you can put ftrace equals function, ftrace equals function graph, ftrace equals get switch, or IRQs off. And yes, the boot, that same thing can enable any event at boot up. Like it does it like it's hard coded like right near the beginning, and it will enable it. And then the trace off will allow you to stop tracing so you don't lose it from when user space starts. So if you only care about the actual kernel boot, you could stop it just before user space starts.
Yeah, actually, that there is another way to set up that those are function tracers on the instance via boot config. But I think that the boot config timing is a bit later, than this one.
No, I think it still does it rather early. So Masami added an extended boot. So sometimes the command line parameter could be limited or it's only so long. So there's a thing called boot config that Masami actually created that you could do. It's more like a JSON format file. And then it will actually compile that into and attach it to the VM Linux file, or you could do it through initRD, whichever one you want. But it's like the VM Linux file. And then it will actually read at boot up, it'll say, oh, the the VM Linux that was loaded into memory has some extra space here. There's a config file, it's a JSON file, and it has a parser that will parse it. And there's a lot of things you do. You could do a lot of function tracing and say, start this, start that, and it will start at the beginning. It's not 100% full, or is it? I mean, there's a thing that you can just use a normal one, but we need to add more features to that.
Yeah. Indeed. Yeah.
Sorry, I have, right. The reserve memory argument, do you need special memory for that, or is this just ordinary system RAM? Because that would vanish during reboot, right?
Yeah.
Actually, so okay, when I first did this, I'm not going to go through the history of because I'm one that actually implemented the reserve mem code with the help of Mike Rappaport, who's also in the conference. What I found out was, yes, years ago, every time I would reboot and any memory would be gone. So one day I decided, or just recently, we were doing something at Chrome OS where we needed to save memory, and I noticed that, wait, the memory is reserved there. So I wrote a quick patch to the Linux kernel and basically took some random spot in memory, wrote, dead beef in there, like when I'm boot up, and on the next boot, I would read that, see what it was, and it was still dead beef. And I tried this on, I had 5 different machines at home, hard bare metal machines. It worked on all but one of them. And I realized as long as you could reboot and the memory's still there, you could use this. And by the way, Chrome OS does this, every Chromebook, it works on every single Chromebook that we've had so far. So, and it works on every laptop, and it works on QEMU. So if you are doing tests on QEMU and it crashes, it works for QEMU as well.
Okay, interesting. And then it probably depends a bit on the machine, right? But yeah, okay, that's cool.
Yeah, and one thing is, okay, so the 3 parameters of the reserve mem, I just want to really quick say that. The first one is the size, the second one is alignment, and the third one is the name. The alignment actually matters. The reason why I found out that Kasler, K-A-S-L, could actually, that's one thing you have to be careful about, because it could randomly move the kernel around, and sometimes it puts it where or worse comes to worse. So it may put it someplace that maybe it doesn't overlap your reserve mem, but it might, by shifting it, something else on boot up that happens just before this might allocate over your reserve mem. And I noticed the larger I make the alignment, the less likely it gets overwritten. So sometimes I'll put like 20 meg alignment, and actually Kasler never touches it, but it's random because it's sort of Kasler is sort of a random anyway.
Okay, thanks.
Yeah,
So
actually,
Matthew is saying it should also work with kexec independent of hardware.
Yeah, actually,
keyword is should.
Yeah. Actually, that we can specify that our actual memory address instead of what's it, that our alignment, right?
There's a memmap parameter that's been there forever. It only works for x86. That is considered a hack. So you can say memmap, and you could put in a physical address, and it will use that. But you have to know the memory map. You have to know the physical memory, where your memory's mapped to use it.
Yeah.
So it's not reliable. It's more reliable if it were, but you have to know the map ahead of time, and it works for a single machine. So.
Yeah. Okay. Okay, then the probes and the events updates here. So the first one is U probes and the F probes performance is optimized these days. So the F probes was refactored with the basement of the F probe is actually that function graph tracer. So that it uses a function graph tracer to specify that one single function to hook that its entry and the exit. But of course, we don't need to use that function graph tracer to hooking the only function entry. So that using that ftrace instead of that. And also using that R hash table that gives us more scalability, so that if we specify that like a all function trace probing or something like that, that is let's say that that is for something like a scalability improvement has been done. So you can see that some are 20% or something like that will be better than the previous one. And also, Giri Orisher worked on trapless U probes and U-ret probes. It's actually replaced the U probes with the system call. So instead of using the int3 or something like the breakpoint, software breakpoint, it uses system call directly to the kernel. I will show that next page. And also fprobes event nowadays accept that a wildcard. So that from the trace-fs interface, we can also specify the what's it, that one probe event can what's it, probe that there are some different what's it, that functions. So here is the U-ret probe system of Cisco optimization works. So that are the probe point. In the probe point, previously user int3 to trap the handler and call that U-probes handler. But the optimization actually that replaced that with if there actually that are if the probe point is 5-byte NOP, that will be also replaced by a call to a trampoline, and trampoline calls that system user syscall to call the kernel. So that this means that we have just one syscall cost to using the probe, a U probe, if possible, actually. But actually, there is a good use case, USDT. So USDT is what's a user space static defined trace point, which is the macro and marking that the trace point with arguments, some arguments with by NOP, and then we can put that U probes on the NOP and get those parameters and save that to the ftrace. This line is very nice, easy, and flexible. However, that has a higher, let's say, that overhead by trap. Compared with that, nowadays, many users are using the trace marker. The trace marker to what's it, that write that some event into the trace what's it, trace buffer, ftrace trace buffer directory. However, that is let's say that of course that we need to give a permission to open that trace marker file to application, and the application also need to open the trace marker file and set up that something like the let's say parameters into the write into the string and write the string into the trace marker. And also in this case, the trace marker event is just one trace marker event. We cannot let's say distinguish from the let's say another event. So, but if we can use that USDT to let's say that use that to put that NOP 5-byte NOP, then we can use our U probes directly on the USDT. So in this case, we have lower cost, lower overhead to enable that. What? Okay.
How is this? There's also the user event.
Yeah.
Are you talking about that? Did I mention that at all?
Oh yeah, user event.
Are you gonna be talking about that here?
Okay. Yeah.
Or did we forget to add that?
Yeah.
Yeah. User events, because user events allow users, or you don't need to have permission to write into it, and it requires an admin to enable them, but the user applications don't need to have permission. That was the whole. Yes, that's the point of the user events, sort of. Yeah.
Yeah.
Okay.
But yeah, it's also need to let's say set up that the user events types or something like that. Yeah. Yeah.
I'm going to point out for the uprobes and urep probes optimization, where you're going from a trap to a syscall. That's all x86 specific, right?
Yes. Currently, this one is x86 specific one implemented. Yeah, we need to improve that.
Yeah, because I think the problem here is x86 specific, that the trap is slower than the syscall, and on other architectures, it's the other way around.
Yeah.
Like on ARM64, they're basically hardware-wise the exact same cost, and it's much cheaper software-wise to do the trap because we don't have to go through all syscall auditing, tracing, etc.
Ah.
So I just want to be clear that that's an x86 problem, an x86 specific solution.
Yeah.
LPC, RISC-V, they're all better too.
Okay, the other one is override event. We actually have two event override event. So that the T-probes and E-probes. T-probes is a trace point event. Usually that we, as you can see that the trace point, something happened, then a trace point kicked, and trace point was a change that some parameters, process that some event parameters, and sent to the trace event. Then trace event will write that data into the trace buffer. T-probes hooks that trace point and get the raw data, and you can use that BTF to get the for example, the something past that some point of the data structure. You can get some your favorite field of the field of that the data structure and record that. And E-probes is more trace event based on one, so that when before trace event write the data into the trace buffer, E-probes will be kicked, and E-probes can also use that these the parameters. Why we have two of those? Of the main reason is syscall event. The syscall event is actually that the syscall don't use the trace point, but the syscall tracer is changing getting the parameters from the raw syscall event. So in that case, T-probes cannot interrupt that because there is no trace point. In that case, user need to use their E-probes to get the data from it. Okay, the last one is the double probe, hardware watch point probe. This one is to get the hardware memory access. To trace the hardware memory access. The basement usage is for specify that some static address to the double probe. Then the double probe will trace that the memory access of the static address. Static, let's say, the symbols. Like that, this one is tracing that the Jiffy's access. Of course, this one is also useful, but you can, the next, let's say, one is more powerful, double probe trigger. This one will let's say, allow the user to specify the local variable to trace that local variable memory access to trace, to be traced. Yeah. How it works. So that the event one here, the first event, this one is let's say something like K probes or something like that. You can set up the I would say trigger action to the event, and trigger the event will set up that the probing or monitoring address to the specific double probe. Then afterwards, the kernel accessing that those local variables or let's say that a dynamic object. Then it will cause a trap and call back the double probe and write it. So in that case, you can record these are how I say these are memory access. So actually, this one is the debugging breakthrough because this mechanism allows for the real-time tracing of the local function variables or slab object. Yeah, without using the static, let's say that data. So the synthesize, let's say that these advanced tracing benefits, we can achieve that context-aware tracing and minimal performance overhead and the dynamic runtime flexibility to that.
In the chat, which architecture support WProbe?
Currently, WProbe is only supported on the x86. Yeah, thank you. Because we found that ARM64, it's hard to get the single step after let's say that hitting that double probe.
Yeah, so across architectures, breakpoints behave differently. On ARM64, breakpoints and watchpoints are taken before the instruction is executed. The idea being that you take the breakpoint, you can go and inspect the state, you do a single step past the instruction and then continue on. I understand on x86, you take it after the execution. So hence, without the single step, on ARM64, you take the breakpoint, go into your handler, return back, take the breakpoint, go into your handler, return back.
Yeah.
So you just need to add that logic, and within the kernel, we need to agree on what the semantic should be across architectures that people can implement the same thing.
Thank you. Okay, so there are many let's say that dynamic probes, probe events. Those are the different strings. Those have different strings. So you can combine those, let's say that are those probes to make your own tracers. So conclusion is actually that this one. Anyway, so we are showing that the current the tracing updates. So that if you have any questions, please make it. Okay, that's all from my side. Yeah. Thank you. Thank you. Okay. Yeah. Thank you very much.
Always here. They can get started if they want to.
All right.
I just
Thank you.
uploaded the slides.
Thank you.
Did you just upload them not too long ago?
Not too long ago, yes.
Oh, okay. So yeah, I didn't see them and then
Oh, it's,
I noticed.
yeah,
I
thank you.
noticed you just uploaded it.
Yeah.
You're all set? Whenever you got about 7 minutes to start, but
Yeah. Can I?
you're not present.
Okay.
Because I have to make myself present to upload your slides. Just a minute, I can update. I can adjust that. for
Thank you.
There you go.
Yeah. But I still like 5 minutes, if you mind. That's all?
If you want to, I mean, you have like, we don't start 3:45, but if you want more time.
Yeah, I see. Thank you. Thank you.
Just one question. I think I agree with you. I think we need to have a work setting a flag. I don't think a lot of direction. Turn it on. Turn it on. That would be really great. Inside. Start recording. I think the other. Yeah, sure.
All right. I think we can just get started. Thank you everyone for coming. I'm Bo Feng. I'm co-hosting this talk with Paul McKinney, and I will do the most talking. Paul will be here answer like hard questions, hopefully. And yes, this is the follow-up talk what I did last year. So basically, give some update of the adoption of hazard pointer in kernel. Let's get started. Ooh. Sorry, press the right button. Give me a second. Okay, so this was like previous on. We have the topic last year, and there's a after these patches, we got some feedbacks. There are some issues we need to resolve, and I think the two major issues. One of them is address dependency issue. The other thing is people want to see more actual usage. And for the people who are not familiar with this, I want to give you guys a briefly description of this graph. It is compare the reader performance with different different reference counting or RCU. So basically, you can see that hazard pointer is basically the similar performance as perceived ref count, and it's slightly slower than RCU, but way much better than atomic ref count. Moving on. Okay, So I'm going to give you guys some high-level reviews and just for the people who joined this year. So basically, hazard pointer is instead of using a counter, you using some other mechanism to count. You have a ref count to an object, and the hazard pointer can be local to CPU or task. Therefore, the access will be fast, and then it will avoid like cache unfriendly access. And yeah, this is basically the basic algorithm of basically just of hazard pointer. And so there are two major components of hazard pointer. One is what I just described. It's you have to have a raw pointer to the project object. The other thing is you have to somehow make sure the updater can observe all the hazard pointer. Depending on how you do the somehow part, it's have different variants. You can do that dynamically, you can do that statically, and so that is the actual cost of using hazard pointer. And so this is a comparison between hazard pointer and ref count. So on the left side, you will see normal ref count, atomic ref count, which we using like cache unfriendly operations to count how many reference to an object. On the right hand, you can see this is what hazard pointer do. So basically, right now there are two CPU access the object, and then if we remove one reader, then you will if you use ref count, then you will have to do a cache unfriended operation on the object, and then the CPU to reference is no longer there. But in hazard pointer, you just change that value to 0, or any other value that not point to the object. Similar for if you have like if CPU 0, the last one also drop the reference. And at this time, if you're using ref count, then you can immediately free the object because the ref count reaches 0, and you can immediately free that. But for hazard pointer, that's not that yet. So this, as you can see, the ref count, atomic ref count can be removed immediately, but you still need to wait for this to be kind of hazard pointer to reclaim the object. So what do we need to do? Basically, it is because of synchronization between the reader and the update. Is there a question? Oh, probably not. It is basically a synchronization between updater and a reader. So you have to make sure that when the updater is going to reclaim the object, it has to make sure there's no reader on that. So what the updater do is, so it will first get it will first initialize something similar as k-free RCU. You can call it a k-free hazard pointer, and it will record that what the object is going to free. And then it will periodically try to gathering all the value of the hazard pointer. Remember that I said somehow you updater can access all the hazard pointer slot, can basically know that how other readers, what object the other readers are actually accessing. So this is the somehow part. So if the updater makes sure there is no reader accessing to the object, then it's going to able to free this object, and it's done. So this is basically give you guys a brief review of this hazard pointer reference compared to atomic ref count. Okay, so there are some good and bad about hazard pointer. The good part, the bad part is basically, as I said, you have to go through something similar to RCU to basically run through a process to check whether there is any reader or not. And you also need to allocate the hard pointer slot. And it has some problem if in certain case where you cannot traverse list like structure, because when you traverse, your previous object may get freed and you may have problems. You don't hold the reference of other thing. And the good part is it's really fast to use compared to normal ref count. And it also compared to RCU, it actually makes sure that it actually will make that the updater can free objective faster compared to RCU. So because it's only check the object, as you previously see in the previous slides, that you only check that whether there's reader for the particular object. You don't wait for all the readers. Okay, so this is like a rule of thumb, like one to use it. I'm not going to go through this, but it's kind of like basically what I just described. And I think this is let me see what I want to mention. I think the recommendation is what has a pointer a kind of better performance in RCU in most of the case. Okay, so this is a slide give you guys a brief view of how you can use as a pointer compared to RCU. So first, you will have to somehow allocate the hazard pointer slot, somehow get a slot. And this is the way we currently have. And then you can, on the reader side, for RCU, it's actually, you just call RCU dereference or global pointer and you use that. For hazard pointer, you will call some function, which I will go to detail later, but this function can detect whether there is an updater updating this global pointer. So if you succeed, then you can use similar as RCU. And you can call hazard pointer clear to actually release the reference. But if you fail in the try protect, then you will need to retry. And this is the updater side. So it's basically similar, except that whatever synchronized hazard pointer, call hazard pointer, or key-free hazard pointer need you to pass a pointer to that, and it will wait for that reader to that particular pointer to go. So this is why a hazard pointer can be potentially faster than RCU for the updater side. Okay, so I'm going to give a little bit introduction of the synchronization behind those API. So again, this is a graph of basically demonstrate the basic idea of hazard pointer slot. You have a slot, you have a global pointer pointing to object, and the slot can be done allocate in multiple ways. And then this is the try protect function. The gist of it is you read the global pointer twice, and in between you have you store that pointer you read in the slot, and you you use a full barrier after that. So this is basically the gist of the algorithm. I'm not going to very detail of this. If you have a question, feel free to ask. Then clear is very easy, just the store release. Just release that slot. And then for the synchronized hazard pointer, which you just, this strong barrier is basically paired to the barrier we see in the try protect. So it will first, normally it will first unpublish the global pointer, and then it will scan out the slot, and it will read if either slot has finished, if there is any slot that match the pointer you're going to free. If no, then you're good. Otherwise, you have to keep doing this scanning. But this thing can be do in a separate thread, and you don't need to be busy waiting on this. And then this is kind of like a, what if you want to publish object? It's similar as RCU, just do a store release. Initialize and do a store release. Okay, so this is a little bit using the previous API we saw and basically describe like some of the synchronization scenarios. This one is kind of why they have to use like to read, because updater may change the global pointer after you save the slot, and then the reader can detect that, and the reader will fail, but then the reader will not use that object, and everything's good. And the other case is that the updater come too late. When the updater deletes the object, the reader is already finished the second read. So this way, the reader has to make the updater wait for the reader gone. This is how the synchronization works. And the third case is when you release, then you actually can notify the updater to make sure that updater can actually free the object. And this is something that we discussed last year after my post patches. This is very subtle issues. So on the right side, we have the updater, which try to publish an object twice. So first it's public object, and then it free that, which is good. And then it's going to publish it's probably allocate and publish something again, but it happened to get the same object. So this is what the right side is doing. The left side is normal hazard pointer reader. So what can happen is that because on the line 5, on the reader we use a normal pointer comparison, then even if in the if branch we use temp2 field, but the compiler may optimize that using temp1 read. And why is the problem? The problem is that we kind of relying on the address dependency to make sure that all the field must be initialized when we accessing via the pointer. And but the pointer, the temp1 is the pointer you read on the first object. And the first time the updater public the object. So if the compiler do this optimization, and it means that semantically you actually reorder this access above, and then you will lose the address dependency, the ordering provided by the address dependency, and then you will basically observe trash data. And this can be fixed by using something we introduced called PTR equal, which is basically just tell the compiler, oh, these two are not pointers, these two just values, and you compare these values, and you cannot use the compare, you cannot the equality of the comparison to do the optimization. This is how we fix that. And anybody has any question about? I'm going to do some case study. If you have any question about the algorithm synchronization, okay. All right. So this year we have some very weird issue in the LockDAP because somebody trying to optimize the performance of LockDAP. And well, I don't know why, but it may make sense because LockDAP is supposed to be like not that not perform that well. It's a debug tool anyway. But I think the case actually convinced me that they really need better performance. So if you so for LockDAP, each class has a key. And there are different kind of classes. One is dynamic classes, one is static classes. For the dynamic classes means that when you create a driver, you create a bunch of objects, and each object can have a bunch of logs, and you want to like LockDAP to track the log dependencies only when the driver is logged. Means that when the driver is allowed, you want to remove that key. So basically, this is why you need dynamic LockDAP key. So when the LockDAP key get unregistered, it will go through a RCU protect list, and then you move the key, and then you will call synchronize RCU, And but that also means that you not only for all the readers of the RCU product list, you also wait for all the RCU readers. And this actually can be problematic for some of the case when you trying to test your. I remember that the case reported is they are trying to test the performance of some, well, not performance, they were trying to do some benchmark with lock type enabled and do some operation on the, sorry. Do some operation on the networking stack, and the operation just got very slow, and it's not ideal, right? So they try to optimize that. And what Brano proposed is using synchronized RCU expedited, and that could work, but it's also introduced a lot of API, because this is how expedited do. It's just API out the CPU and saying, hey, are you finished? Are you finished your RCU read correct section? And when I saw this problem, I feel like, okay, this is maybe we can use hazard pointer, because it's exactly match the same category as hazard pointer can perform better than RCU. So let's see how we can do that. Before we're using hazard pointer, we need to have a plan to handle two kind of failures compared to RCU. The first one is the protection failure, which, if you remember, that the hazard pointer have the try protect function, which if you fail, you have to handle the failure. And the other is kind of the allocation failure, because if you want to use hazard pointer, you have to allocate the pointer slot somehow. And you can do that either way, but if it's allocation, it can be failed, right? You have to handle this as well. And let's see how we do this protection failures. So this is actually easy, because in the locked up case, we actually, if the single change, we actually just return false and everything is good. Like locked up performance can do the things correctly. And on top of that, this is a list, and we can do something special for this case, where we just use the hazard pointer to protect the whole list, not an object. This will make things much, much easier. And so we can do that. And notice there is a new API here. It's called hazard pointer acquire. And so it is, I will talk about this in the next slide. So basically, this is similar. If you want to do this is the code that we currently use to hazard pointer to protect this. And let's see what hazard pointer acquire do. So it's basically acquire. It's basically the first part of hazard pointer try protect, except there is no second read, because we are protecting the whole list. We try to make sure that the updater will wait for any reader to that list. So we don't actually, so the list will always be there. So we actually don't need to worry about the list is gone. We don't actually need to worry about that. So that's why we can use hazard pointer acquire instead of hazard pointer try protect. So this is like the synchronization scenarios of using hazard pointer acquire. So if in the unregistered key, we try to delete something, and we observe that somebody is accessing this list, we will just wait. And otherwise, we will just access the list and observe that the item is already deleted from that list. So this is like a normally this is not like a typical hazard pointer usage, but it works. And so this is overall how we handle overall we handle protection failures. But allocation failure is really tricky. Oh, go ahead.
Hi. Is the acquire approach using pre-allocated slots per CPU slots?
I'm going to talk about that, but yes, we are using the per CPU slot. Yes.
Excellent. Thanks.
Yeah. So thank you for the question. Right to my topic, for the next topic. So the problem of allocation is, first, I don't want to do that. I don't want to allocate anything. It's making things much more complicated. And also it's in lock type, you don't want to do that. You certainly don't want to do that when you running the lock type. You will probably want to do that when the lock type gets initialized. But there comes the problem, what if that allocation fail? But in this case, we actually can work around that. And why? Because we can basically, so as long as we use a per CPU as a point slot, and each time when we access the slot, we have the preemption. Well, in this case, it's actually interrupt disabled. But as long as we access the list using the hazard pointer, and while the preemption is disabled, that we are good to use that per CPU slot. So this is why we can cheat to avoid using the to avoid allocation. So introduce single hazard pointer. So again, as I said, only use this hazard pointer in preemption disabled, which is fine for the case, maybe fine for your user case. And you mostly only reference one object because you have one per CPU, one slot per CPU, so you can only use that. Mostly you can only use that to protect one object. And we can use like a per CPU pre-allocate hazard pointer slot. And but as the previous slide said, mostly, but we do have an issue. We actually have an issue in the is dynamic key, because this function can be called in NMI. So you can have multiple readers at the same time. So we have to fix this. So this is a case like why this is problematic. So let's say we have, this is, thanks for Mark to find this. There is a typo here. This should be slot, not lost. So we are one CPU is doing the dynamic key query, and it's trying to do the hazard pointer acquire, and then it protect the slot, and then NMI happens, and it may call another dynamic key function. And at this time, if we use the slot to protect a new list, then it's going to be problematic because the previous protection is gone. We have to do something. And to do something is what I call wildcard. So basically, we have a special point value that protects all the other addresses. So in the same case, if in NMI, we just change the pointer value to a wildcard, then it's at least correct, right? It actually should work, because you just need to make updater respect this value. It's nothing. It's nothing other it's basically means that you updater has the reader has some agreement on which pointer value they should protect. And this is how you actually recover from multiple readers. So because although you can protect, you also have to make sure that when the reader is gone, you have to make sure that you you clean that slot. So what I did is basically make sure that when you acquire hazard pointer, if it's changed from non-wildcard, or if you don't use the wildcard change, you store something in the guard. And if you only restore the hazard pointer slot to null if that guard has that flag. Otherwise, you just do nothing when you clear. So this is, as long as the hazard pointer reset correct section is perfectly nested, you shouldn't have any problem. Famous last word, but I think I'm right. And so this is, yeah.
Actually, that seems to only work if you have two users of the pointer. If you have more than that, you'd want to encode a ref count with your wildcard flag, and then decrement that ref count until you get to the final one.
No, because we just because we have multiple guard, right? So the only maybe.
Oh, so you have two slots per CPU? Is that correct?
No. I have one slot per CPU.
Okay.
And I just if you go to wildcard, you stay in wildcard, you do nothing. it is only the first one that doesn't use wildcard is responsible to restore the slot. But my assumption is the read set critical section is perfectly nested. There is no hand-to-hand critical section. That would work.
Yeah, that works
Other than
because
that-
preemption is disabled. Yes.
Yes.
Thanks.
Yeah, just a question. In that special case, you are actually have preemption disabled and also interrupt disabled, right? So could you use some kind of per CPU count to count how many tasks or eventful are trying to access the hazard pointer, and then make a determining there? So you add additional count on top of that.
I think that could work, but I guess that will make the thing not simple. And also in this case, this is kind of like a very special case, because if you have an NMI that...
Oh yeah, I know it's a special case. I looked at that before, so...
Yeah, so I think that my argument kind of not doing that right now is just this simple hazard pointer should really be using if you have like very simple cases. And if you having like multiple cases, you may have like 2 readers, multiple readers, you should allocate your hazard pointer slot. And that's kind of what we should do. We should not entertain this idea too much, like making this work, because eventually you can do that, but also like if you maintain like a preferred ref counters, I think that would just be a slip of RCU at that point.
One thing you could do, and this may be the way you implement it, I'm not remembering very well. You could have the guard contain the previous value of the slot. So initially that slot's going to be null. So you put it in there, and then that way when you do the clear, you could restore it to the previous one, again assuming perfect nestling. But is that worth it? I don't know.
I have the feeling that I remember this is not working, but I cannot.
Probably not.
No, so.
If that's not working, that would be a very good debug option.
Thank you. Okay. Any more questions? Otherwise, yes. Yes. So, well, by the way, I think I didn't put in slides. I just want to mention that this idea was mostly the per CPU hazard pointer idea was mostly inspired by Matthew. Matthew has done a few works on using hazard pointer in various areas, and that elegant way of using per CPU is really making me look into this as well. And the other question is that I think people may have the question that since this wildcard is not something maybe some people really like, and they want to get rid of this. The initial idea is that, hey, can we just have multiple per CPU variables, right? Like you use a hazard pointer, I use a hazard pointer, and can we just multiple like hazard domain to do this? And currently my thought on this is we don't. Why? Because hazard pointer itself already using address to separate different objects. So the chance of this actually hitting a wildcard is very low. And even if you have like multiple, even if you have multiple usage outside locked up, if you have multiple usage, and so that's one reason. The other reason is that if we have multiple hazard pointers domains, that means we have multiple hazard pointer synchronized hazard pointer functions, which either you have to spin waiting on each slot, or you have to create a thread or work queue to handle that, to do the scan. So that seems like unnecessary and seems like waste of the system resource. Go ahead.
Sorry, just to check, when you're talking about multiple domains here, are you talking about for nesting of contexts, or are you talking about entirely different like users?
Entirely different users.
Okay, because one of the things that came up before was like using hazard pointers for lazy MN switching. And I think that got shut down in part because of the complexity of the implementation that was shown.
So yeah, so what I suggest that if we have this simple hazard pointer in line in train, and then if we use that if we use that in the lazy MM as well, we just use one. We just share the same perceivable.
Oh, but I get that.
Yeah.
But what I was going to say is that will then not nest perfectly because the time at which you switch the lazy MM stuff is different from time at which you enter tasks. Like you will always be for the lazy MM thing. You will almost always be using a slot among other things. So the likelihood of getting into the wildcard case is actually significantly high. Because you'll always be saying, I have this MM that I am tracking. The only point I'm trying to make is I do think it's probably worth having the domain there early on. But that's it.
Yes, I did the lazy MM stuff. So I needed the per CPU, per domain, mainly because it was usually active. And also I did, on exit of the MM, I did not need to synchronize for the hazard pointer. I could take an action if the pointer was there. So kind of really having that tracking specific pointers for the domain was useful.
But, to Mark's question, Poly Library does have multiple domains, but Megan regretted having added them later because it turned out that the fact that each reader was only holding a very limited number of objects meant that it wasn't helping in the way that something like SSU helps, where you have multiple domains.
Yeah, sorry, I just mean if you've got two entirely different users, like one thing is like tracking MMs and one thing is tracking lock depth keys, because their life cycles are different. Just having two separate per CPU arrays and just using domains for those and just having that as a key you pass in is relatively simple, but would avoid the problem of always hitting the wildcard case.
At some point, I suspect we'll get to a point where we're going to have multiple hazard pointers and allocate and deallocate them anyway, at which point you could just have your use case allocate the ones you needed.
Sure, I just strongly suspect that the use cases here, if they're simple enough that you have multiple users that only need one slot per CPU each, and therefore taking the key and just that being like a pointer to a per CPU array or some structure that points that.
I actually don't follow your argument about this will be having multiple, make the wildcard more, because you basically you do this while you use the hard pointer while you disable the preemption. So you do some lazy MM access, and then you just release that hard pointer, and then you do some lockdown. So this two, as long as these two corrective sections doesn't overlap.
Okay, so sorry, if the assumption for simple hazard pointers you have to disable preemption in order to use the tool, I don't think it ends up being usable for the lazy MM case.
Right.
Okay.
Okay. Oh, this. I have a technical issue that the screen is locked. Sorry.
We forgot to drop the hazard pointer on that slide.
Yeah.
Screen lock monkey is here.
Okay. So that's, I think overall, I guess the idea is probably we can just try to use if the single hard pointer fits the usage, we can just use it one in the beginning. And if there is a performance issue, we can analyze it and see what. But I guess that the point that Matthew reached out that if the callback of that pointer exists, we can do something. I think that's maybe something also I need to think a little bit more. That's a good point. So this is the information of the implementation, and we have some evaluation. First is the lockup usage. It's basically similar as Breno's result with our synchronized RCU expected, and but with less API, of course. And I also have some micro benchmark against RCU on the application side. This is the this is the thing I'm most curious about to take a look. So there are 5 rows. The first row is RCU, and this is the grace period duration with RCU scale, and it's a benchmark in the kernel, macro benchmark. And the second line is just using synchronized simple hazard pointer, and I also currently the simple hazard pointer has implementation where we use a thread to scan. So the third line is basically we just don't do optimization of using like per CPU, trying to do a busy wait to scan other per CPU hard slot. Just go to that thread and use that thread to scan. And then the fourth line is just make sure every reader just use wildcard. And the fifth line is combine the third and the fourth line header. So you can see that it has a relatively good result compared to RCU if there's no if it works, right? If it works, it's this the second line basically means that if we are not hitting wildcard, then it's really fast. But it's a macro benchmark, so I don't know whether the real life case will work. And this is even if we use a thread to scan, we also get reasonable performance. This is even we have wildcard. It's not that bad. It's still like compared to RCU, it's still good if that fits your user case. And the fourth line is basically similar. I guess this is also very interesting. If we skip the busy waiting and we have the wildcard, that it's actually performs better. I guess it's because if there is a wildcard and you keep spinning, then the spinning will also fail, and you better just go to the thread and use the thread to scan. But this is my iteration of the result. And for the reader side, I don't have the data, sorry, but I have like the previous data for the normal hazard pointer. So it's basically slower compared to RCU because you have a strong memory battery, but it's faster compared to SRCU because we only have one, SRCU have two. So this basically, I would say that the simple hazard pointer will have the similar result as the hazard pointer right now. Right, that's the end of my presentation. Any question?
So I just want to know under what condition will generate the worst case scenario for your.
You mean the micro benchmark? Or
yeah. In previous slide you showed the worst case can be a thousand. Yeah, the max case can be thousands of microseconds. So under what condition will that happen?
I don't know.
Oh, okay.
It's a result from the benchmark. So I guess. But Paul, do you know? It's for, I think his question is more for RCU, right? For the RCU, where RCU can be worse in that case, grace period.
So what Bochun did was he compared against the current code, which uses synchronized RCU. Synchronized RCU is designed for throughput, not grace period latency. And so that's kind of by design. It takes some number of milliseconds of just kind of going through the state machine. Yeah. Oh, you're looking at the difference between simple hazard pointer and say, okay, so simple hazard pointer, he's just spinning. And then as soon as the thing goes away, bang, he's got it. But if bad things happen, if, for example, if the guy holding the hazard pointer gets interrupted or something, then you've got that max being kind of large, and that's CPU bound, which.
Okay, I think I understand the question. So I can explain. So in the case where you do a spin check and you didn't hit anything, you can finish that very, very fast. But if you if you spin hit on one hard point slot, you will like kick up a thread, and the thread will scan, and that can make things really slow. And if in the worst case, you also in that thread also the hard point is still used, then you will have like bad luck. So I think that's why you have to consider like the wake up thread and thread getting wake up and thread getting bad luck like multiple times, and then that's why we have the bad result.
I have two questions. Like the first one is, what are some practical applications of hazard points you envision next? Like kind of what are obvious targets? I remember Dave Watson was proposing something related to file descriptors a few years ago, but I think it didn't go anywhere. And my second question is like on your second slide, how it will stack up against trace RCU, which is used for like protecting sleepable BPF programs right now.
Do you want to answer this? I think Paul had a question answer for the second.
Okay, so I'll start with in the hazard pointers. If you're asking for David Watson's proposal Linux kernel or David Oh, okay.
If I want to use.
Okay, in the Linux kernel. Okay, so hazard pointers Linux kernel. One possible. So we have some. So hazard pointers and RCU are kind of different design points, but there's a lot of overlap in use cases. We've had RCU and Linux kernel for a long time, and it's kind of filled in what it can. But there are some places where its disadvantages can be annoying, might be annoying. So, for example, let's take for one of the things it has is there's a per CPU reference count, which if you have large objects and don't have very many of them, why you just use that? Why use this? Why use hazard pointers? Why add the new thing in the kernel? But let's say you had a bunch of, let's say you had 1,000,000 32-byte objects. And if you use per CPU ref count, and you're on a 256 CPU machine, you're having 256 integers to protect 32 bytes of storage, and that may not be what you want. And hazard pointers will be able to do that at much better memory efficiency. Okay, so that's kind of a example of a way of thinking about it. Another situation is if you have cases where, and we have other ways of dealing with this. So for example, everywhere in the kernel right now where it uses RCU to kind of hold down a object and acquires a reference count on the object once it's gotten to it, maybe some of those, why not just directly use a hazard pointer? So instead of RCU, okay, now use a reference count, which is doing a write operation of that object and messing up the cache locality. If you instead say, okay, we're not going to do that, and it's going to depend on the use case whether you can or not, right? It's not but that's another case where you might be better off just saying, okay, make a hazard pointer to it. We changed our local pointer to point to it. We haven't invalidated the object, so it's still read-shared across all the CPU caches, so it's fast. And then that might work better for some of those use cases. Is that a decent set?
General, but like any more specific examples, maybe.
We had the one from Mark on the
lazy MM.
Yeah, the lazy MM is a possibility. But at this point, we need to stay focused because, as we do with RCU initially, right? The first one in RCU was some kind of module thing that Andrea Cangeli and Andy Clean put in, right? And so, if we try to solve the whole thing at once, our initial offer of hazard pointers is really complicated. Okay, and it may be that we end up with something simple, and then it's hard to get it accepted, and it's also hard to justify. Whereas we start somewhere, and then we add a thing at a time. So, for example, with Mark's lazy MM, it may be that we just have 2 hazard pointers per CPU, and we do that way. But maybe we have to add the more complexity.
Yeah, sorry, with the lazy MM case, I had gotten confused, and fundamentally you have to be able to use preemption with that. So if we do that, that's a much larger step change. That was all I was going to say.
Yeah, well, so the lazy MM stuff I did, it was 1 pointer per CPU, But the idea is you add a domain that was specific for the lazy MM for the scheduler, because you always have at most one pointer per CPU. So that was pretty simple. It was really the simple case, but with preemption enabled, and then having the ability to do a callback rather than wait in the synchronize.
Yeah, but critically, you're holding on to that pointer across a preemption by design. That's the whole point of lazy MM, which means it fundamentally violates what was on the earlier slide as an assumption for.
Yes, but the idea is if you have your own domain and you're guaranteed to be the only one touching that, then you're fine.
Yep, no one's disagreeing that whether it works. We're saying that there's a step change in complexity, and hence leave that for later.
Yep.
Paul, did you answer the question about the trace RCU?
No, I didn't actually. Good, thank you. Yeah, I only remember so much. I'm sorry. So Roman also asked about RCU task trace, so RCU task trace is kind of a special case of SRCU, and in fact, in the next merge window after this one, we'll be making it so it is a variant of a sped up SRCU. So we're kind of getting rid of it, but leaving the use case there. And the nice thing about that is it means that if there are multiple BPF kind of domains, they can just make another lightweight SRCU and then have fun with it. Hazard pointers. I would have to know more about BPF than I do to answer the specific question about where in BPF should we use hazard pointers. It may well be there is some place, but I haven't looked myself. If you have some ideas, I think you've touched it. Let us know.
No, just my understanding is like at least the current version of SRCU is too slow for my understanding is, but
yeah. So Bochun is absolutely right. Standard SRCU has a full memory barrier, both an SRC read lock and SRC read unlock. The thing is that that gives it freedom. So you can do SRC read lock in the no-instir kernel entry chunk if you want to, all right? You can also use it from an offline CPU. You can use it deep in the idle loop where you can't use RCU. So and task trace RCU has the same freedom. The difference with, so what's happened is they have added the no-instir things on x86 and ARM and a few other architectures, enough to where it makes sense to say, all right, for those we're going to optimize. So the trade-off is that you're only using this where you can legally attach trace points, which is where RCU is watching. So SRCU uses a combination of RCU itself plus the SRCU counters in order to get a faster read time. It's under 2 nanoseconds on x86. It's like 6 or 8 or something like that on ARM, on the big data center ARMs. And probably varies on exactly which one. That's the ones I had access to and I measured it. So there, measure it yourself if you want to. And that's, in the case of ARM, that's a little bit slower than with RCU task trace. Hopefully the ARM hardware guys are making that better because they're like several times slower than x86 on that operation in some cases. But the effect is that because we can use because we're restricting it and we say, okay, you can only use because they marked all the stuff. Peter Zylstra and Thomas Gleichner and a bunch of other people made it so that, okay, you can only attach traces where RCU is watching, essentially. On those architectures, we can just use SRCU and use RCU with it so that you have that restriction. But there's a kconfig variable that says whether or not the architecture is confident of its no-instir stuff. And in the case where it isn't, we'll throw a full memory barrier in there.
I'm done.
Does that answer the question, or am I confused? Okay.
So I think overall the difficulty of using hazard pointer or find a hazard pointer user is because we keep optimizing RCU. So
we're a few minutes over. So if you guys don't get out there, they're going to drink all the coffee and tea, and you won't get any. But if you have more questions, we're happy to stay around. I don't drink coffee anyway. Okay.
Interrupt. I figured. Great.
Thank you. Thank you.
Great. Great job.
Thank you.
Understand, or at least in my the only to do is the design. There is a that we can store. I just want to make sure I was using one. Like I said, okay, that's next version. All that into and the that's right real soon. And then that will make this thing use the alpha part. Yeah, use that's something I'm thinking because I can't make it work. But it's still gonna work. I'll it work, but we hold it off. That in the context switch, which is not you don't want to be synchronized on the pointer to log your context switch. Because you have to this you look at the graph and this recording is on the pointer to a thread structure. Something with the out, right? And this view is doing a synchronized will get them off. You basically can have a case where the synchronized pointer log the context switches. It is and there's I'm trying to figure out whether I was going to do that. The other thing I think also like mentioned that in this API you have to make that this pointer is still using something else. Right now, in this case, it's kind of just the only one that you it's through the worst case. Like I said, it's through the word. At the call that you need to turn it off in the schedule. And it's not scheduled. Like RCU knows context words it use. So we have to let I can't do some smart trick like for CPU log. But it's got a special case here. I'm not sure. I haven't really looked at that. I don't think you can. I don't think because but seriously, if say you already store your pointer and you are scheduled back to say your task already get ramped, so and it's scheduled back and you're trying to restore it pointer. Yeah, so I have a case where if the task keeps getting corrupted, you can actually indulge the scan and make sure that everything else is observed. That is something that's how we like, which can happen. So yeah, it depends. So he's going to because we already have the way, I think the already work is stronger. They actually use it as a on-site allocate. So yeah, I think that so myself, I'm just going to make this single one, make a gateway drive for people who use that, and maybe release and probably performance issues or switch to that's kind of my plan. We're all happy. So obviously we're going to prototype Yes. So we still, like I said, we still have like a very decent user because we keep making our views on the better. The thing has to be added to the user, right? It also has to do with, RC also has a property that it is it doesn't have to kind of figures, right? You don't say like you don't read a figure like a reader with that's very important because that is nobody in the world has to like there are many cases when you have like a arrow you do not you just only want to a users. Basically, those are skills. You can cover how it's compared to RTU, only like the challenging, like only beneficial or all beneficial, and people really care is you can free object class, right? And nobody really cares that some students have memory issues. But I'm not working in any like my brother.
Hello? Can you hear me?
I can hear you. You're all set.
Okay, thank you.
Okay, yeah. Yeah, that's but also making the camera as you are. Yeah. Also, it's how fast is fast. This is the case where we run our funds actually. That's a control thing. It is on the end. And at that point, it's just locking is really weird constraint. In part because very few architectures have common instructions. So they have to do their locks and just go through steps. Look, it's like way too especially if it catches on the voice or space or something that has to work in the same transition. So it's actually but in most cases you have to think about things a little bit, especially RCU as it's closer to a reference count. RCU is not quite there. Let's see, so I did an explanation working hard, so what is girl working hard? And if so, Anyways, PDF you can download. Okay, this PDF you can download. And there's a repo you can make them the PDF. This is going to come from servers. So, now, section 9 is not deferred synchronization, not sync chapter. Deferred processing chapter. So that's reference counts, your reference count, say we have to sometime later, so they really get stuff left. And it's also like deferred section. And as for saying, they say, all right, this is what you're now said, finally, everybody, they sometime later, so I see something other years for this, we'll get to us, and I need to code, but RC. Yeah, just got to have what you were doing. I have a cell phone reports, actually get reports. Sure, there's something that isn't proven in there. Yes. The pull request, please send me. I did know that I need to look at different things. Pull request, I might not see. I'm sure this is what I've got set up. So I can look and something there. So that'll help something. So what do you price on this? Okay, so the son of Shark or the grandson of Shark, there's something like a Shark was their sources. No. Oh, different. Okay, okay. So just right here, this is associated with Frank makes another one. No. Random. Okay. Yeah, I want to think. Okay. Needs to be with those. Say here. This is my first storage. I'm still less than half. No, but I mean, most of my career is where my career started.
After market. I did it.
Okay. I'm actually. I started in 2000. So 77, 2023 versus 25. You're right, I did. I just didn't notice.
Yeah.
So actually, yeah.
I did like, about a couple of years ago.
Okay.
I also started full source back in 19.
Okay.
And so I started open source in 2007.
Okay. You got pretty fast.
Yes, I have worked longer in open source and closed source at this point. And I don't think I can. I think most of people will not like it. Exactly.
I've done a few projects.
Have you done going back and forth?
You have to be careful. I was helping out one of my partners with the net synchronization. But the way I did that is I wrote C code. And C code I originally provided to open source. And then I handed it to another IBM employee who was proprietary. And the actual code was C++. So there was kind of a firewall. And also they were taking advantage of a lot of property of their overall application. But I just use ours instead. They had some other optimizations that were rather clever ones that that's what understand it, I can't say what those are because it's up there in the air, right? So I'm thinking, look, by the way, if you're gonna actually do this thing in Azure. But it isn't my book yet, because I'm slow about that thing. No, yeah, so cool. Cool. Well, the source. Okay. I've been here. It was maybe the first time when I haven't actually been speaking.
Oh, this is the first time. Yeah, you're
This is
usually.
the first time I haven't had a true speaking part.
So you successfully transitioned to, got some.
Behind the scenes trouble here.
It is fun to be behind the scenes. It is actually fun to be behind the scenes. Advantage to it. Thanks, Paul. Good to see you again.
Oh, you're the chair of the committee. Congratulations. And condolences. Very good. Okay. Okay. You and Ted working together out there. Okay. 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 The big thing about getting other people to do MCing, you just have to ask them. Doing it a year or two by yourself is a good way to be involved. So it's not a bad thing. Yeah. That's not bad. So, but at some point you want to get it out. And again, people usually they like to get up there. Yeah. Oh, that's. Okay, nice. Okay. All right. There you are. No, that's good. I know about that.
Like to keep it. You will announce it today.
Okay. Very good to see you. Have to make up for your son.
Of course.
So like the time.
I think that's one of them.
That's really
Yes.
all right. Well, thank you for your.
Thank you. There's one thing I wanted to do, but remember my name was on the page. So for our office and places, people reserve slots, at least for speaker, they reserve some slots. So that name should not be added on the. Yes, for speakers, separate records.
So that's why.
Okay, thank you.
where the NPU talk is?
MPU talk. That is the next one?
I'm trying. Mystifying.
Yes.
NPU subsystem.
Yes, yes, that's what, this is where it's happening. Our speaker is remote today. So,
Oh, it's remote?
yeah.
Ah, okay.
I mean, I guess you can be anywhere.
Sorry?
I mean, since it's a remote,
Yeah.
you can be anywhere, but.
Yeah. Yeah, no.
I have to invest in a battery pack. I am sitting here charging mine.
There aren't a lot of clubs.
There aren't, not in the convenient locations. There is one all the way in the back. And then they don't seem to have anything on the side. And then since I am shepherding the room, I'm here.
Yeah.
So
I mean, they usually have these straps at the board.
that would be nice, yeah. If we don't. But I think 50% is okay, I think. Okay, let me see, take presenter. Okay, right.
Can I start?
You can start now, Jagan.
Yeah.
Welcome. Welcome.
Yeah. Thank you. Thanks everyone for joining this call. Sorry, joining this presentation. I was unable to attend physical because of the visa issues. So thanks for accepting first of all, because this is essentially very new topic in Linux community, and there are a lot of debates why this subsystem has happened because of the existing GPU cycles already been there. So essentially, my name is Jagan. I'm the almost key contributor in the U-Boot and Linux community since from almost 13 to 15 years. And right now I'm handling building the company similar like NPUs for the edge inferencing. To start with the context, something like so our last few years NPUs has become standalone blocks in both in embedded and PCI nodes, just like earlier GPU does. But from the Linux point of view, NPUs are still in a special case, not like a first class compute, because not like a first class compute. So this talk will address why that is and what it took so far and what are the cracks to start to show, especially from the vision to LLM models on the edge workloads. So yeah, before going to further, I'm just quick context what I wanted to talk in this particular presentation. Everything I will show based on the real deployment has happened on our nodes. Since the NPUs in the early stage, we did use the most of the workloads from the vendor NPU drivers. Focus more on the inferencing rather than the training frameworks. So the goal is not to propose a solution, but to highlight what is working today and what are the potential gaps that might or might not handle over a period of time in the next consecutive RCs in the next community. Yeah. So to start with the NPU things, just like a training and inferencing from the both in terms of the memory and the kernel point of view, these are the simplified stacks. Say for example, training requires a lot of a cloud and massive memory compute. So the Linux both in the vendor are stable in handling those. On the other hand, the inferencing is stateless. You can run the model and get the results and move on. But there is a other phenomena, other possibilities where the self-learning is possible to approach with the current edge workloads. That is where the combination of both training and inferencing happens on the edge, which is called as a on-device learning and on-device self-learning, something like that. That is where the NP assumptions will getting stressed a bit. That is where I would essentially see the possibilities of having the full-fledged NP stack on the war run. So, so then what exactly the Linux supports so far? So essentially, to be clear, the Linux has so much things extremely well for the NPUs. That is one of the reason the vendor NPU companies are releasing so many chips without doing any upstreaming and without compatible with their NPU drivers to open source. That is because the NPUs more or less the compatible are depending on the existing Linux stacks, exclusive on the DMA buffer and IOMMU, and the some parts on the DRM, which is exclusive for the DRM jump things and other things. And more importantly, the NPUs or edge inference nodes inputs are three different identical. One is a vision. We have a very much strong vision upstream capabilities in the camera or media. And there is other thing is a sound, acoustic. That is where the NPU's inputs are something like a Wi-Fi and other things are possible to have a voice extent. And the last but not least, the LLM workloads, which are requires a job in QZoo, and the even the LLM interaction from the user space buffer is very much straightforward, since the Linux stack is very much supporting these memory map and other things on the Linux side. So far things are good with NPU variants, NPU subsystems, but what falling short, something like this. So the main difficulty start from the NPUs is becoming an NPU as an NPU compute accelerator. Similar like early stages in the GPU, we have an Axel framework that can create some kind of a device, Axel device, that can run with the individual NPU controllers. So those will expose to the user space as something like a OpenGL or lib framework or TF-Lite, something like that. These things are pretty much straightforward, like in early stages of GPUs. But the problem is not exactly that. Uh, not exactly this point, but the thing is that all the expositions happens like flawlessly. Like you have a device called a device XLX, and the conventional driver GPUs like FOPS glue, and we have a DRM controller IOCTL that can any of the DRM control driver can access. But the thing is like whether these are working in a full-fledged or not is really matters, because at the end of the day, Excel is another DRM device basically. So, but the TF flow works straightforward because it is a fixed graph mode, and the like a GPU has a cores and the CPU has a cores, NPU has a tensors that can handle the both the static and tracer memories. So even the vision works well up to some extent. The core problem is not about the vision, because all the entire NPU workloads are categorized into stateless and stateful. So for the vision and the sound, both are stateless. So whatever you operate, they will give the result and exit the memory. That's it. But in case of LLM, that is a very quite different basically. LLM workflows are looped. The model stays buffer permissed. If you ask something, the model will be persistent on the memory. So jobs are keep updating, and we need to maintain a long term memory, the scheduling and powerhouse and other things. That is where the DRM XL is clearly failure. I would say not supporting at this point of time, because in order to add those kind of stuff, you need to have a strongest memory policies, even the job models and executive cycles and the scheduling systems, which are unlikely not very much relevant to the existing DRM stack, because the NPUs and GPUs work very quite differently with respect to how they handle those workloads. So why the problem is not happening in vendor drivers? Vendor drivers are not doing much on their own portfolio, but they did some kind of hacks with respect to how they wanted to support their NPU drivers and give to the customers to deploy the NPU models. Because many of the NPU models right now are running in the edge or inferencing are running with the vendor NPU drivers, because they did some kind of a tweak on the existing DRM, not just a kind of a layer. They did still directly use the DRM, act as another DRM driver. So that means they can get some kind of a DRM node, which is called as a dev NPU. So what very much working for them is the strongest vendor tool chain. Whatever the models they wanted to deploy, both in the vision, sound, or LLMs, they have a full-fledged life cycle for the vendor tool chains. That means these drivers will not work without these vendor tool chains. That is the classical problem we are facing in early stages of our GPU standalone. But these drivers act as a micro runtime inside NPU, which is very much similar like conventional early days of GPU. So because of this, have a stronger tool chain. What these guys do, like they build some kind of a their own entities in the DRM drivers, like a job model, execution cycle, and power handling of those NPUs, and even the scheduling and other stuff. They are proprietary to their own entity without touching the existing infrastructure of the Linux community. Because if they want to touch, they need to handle the proper API that can be sustainable towards the community or a device tree. But because the ideal situation is to not to upstream those things at the edge, so that is a classical issue they are facing, even with respect to both handling of those nodes along with supporting those vendor workloads and in a faster way. So how these can be supported with respect to the Linux community by pumping their own drivers is something like this. I can take a classical example of how the vision workloads has happened with the vendor driver. So as I mentioned, the vision sound are stateless. So we need to allocate some kind of a buffer that can all these stuffs are handled user space on their vendor tool chains. So once they create some kind of a buffer, they can run the buffer and then signal to the NPU driver inside the DRM. So DRM acts something like a KMS, what we have in the existing display drivers and the display bridges. Whatever happens from the user space, it can poke and then call to the executors inside the tensors. Whether the tensors is 0, 1, or 2, they create the jobs according to that. And since these are vision sound, those jobs are stateless. Like you can allocate a memory, run the inferencing, at the same time signal to the completion and then release the job. That's it. So whatever happened on the user space, that can clearly go to the DRM, but it cannot use the complete DRM stack. They can use the vendor DRM or vendor NPU drivers alone. So that is one of the reason you can run the reason models exclusive on their portfolios by combining those entities on their vendor tool chains. So you can define your nodes and you can build your tool chains to convert these models to your data sets. So that is compatible exclusive for their vendor tool chains, both in terms of the drivers or in terms of the user space. So most essential point here I need to stress here, like so even if you wanted to tune the NPU on the vendor DRMs, we need to handle the entire the stack starting from the user space toward the NPU drivers. That is very much hardcore job, because Similar thing happens with our early stages of the GPUs, where the GPUs are prohibited to not to create some kind of API to implement your use cases and other stuff. There are some projects right now working on these exclusive areas like exclusive XUs, PyTorch and other stuff. They wanted to minimize this into a unified layer for the NPU, but that is still taking some time because the deployment so far happens on the vision or the sound and the in the industries. They are sustainable in nature, so that the existing NPU vendor drivers are okay with for them to have the better performance to give the hacker stack, but that cannot be a single API to run the longer run. So on the other hand, what happens with the LLM workloads is a different scenario. From the LLM point of view, NPU driver, even the vendor driver reacts as a differently. So since the LLM are stateful, it's a long looped workloads. It has a job control models. So once you run the LLMs on the edge, you need to create some kind of a model to stay buffer persistence. So these jobs are need to be repeated and repeated, and we need to handle the SRM memory inside the NPU vendor driver, even the power cycles on the tensor flows and tensor initiation, tensor scheduling. All this is done by the vendor driver itself. So from the user's point of view, it's just a matter of taking the foundational LLM, quantize it to the chip, and then convert to their NPUs and then run it. That's it. Because the core part is handling on the vendor driver, the things are pretty much straightforward for them to run these LLM models and other stuff. So we did use some kind of a open source LLM, open source Excel models to start with. But since the open source Excel has the control over the job models and execution, these things are pretty much in early stage basically. Uh, so these jobs are repeated to execute, so it requires a persistent buffers. So either it is a user space headache or the kernel space headache. It's up to the vendor kernel that handle these stuffs in a predominantly way. So and what are the verdicts basically? So it's again the trade-off, I would say. When I create some kind of a parameters, what are the parameters to support these drivers full-fledged into the mainline? That is something like we need to monetize in different areas, like identify the models starting from the vision sound to LLM. So the critical part is the job model. Right now, the Excel support OSL like any of the DRM model, but in vendor kernel, it's different basically. We have an explicit job models that will create some kind of a threads inside the kernel that talks to the user space drivers, both in terms of the inferencing or even the Python or a CPB or any of the runtime code from the inference point of view. These job models work pretty well. So another important asset with respect to the Excel versus the vendor NPU is like they have an explicit algorithm that can create these SRAM buffers. This is pretty much working perfectly required for the LLM workloads, because once you talk to the LLM, we need to the memory has to persistent in nature where the inference happens in the loop. It will not stop like or complete or give a signal that it's not completed. So these jobs are need to be looped in nature. So in that case, you need to have some kind of a SRAM algorithm that need to be run on the NPU drivers, which is something difficult for the DRM to allocate these kind of buffers in a real-time NPU or in real-time Linux kernel. The other one is a persistent in a nature. So it need to be preempted in a nature that the model need to rerun again and again. So the model has to be in the RAM, and as soon as the user asks to the interaction, so the NPU driver act seamlessly and then give the persistent results on the go by giving some kind of a chatbot or talking some kind of a history to get the results from the workloads and other stuff. So other thing is the scheduling. So the Excel driver right now using the TensorFlow Lite, which is a traditional ML algorithm to run your inferencing on top of Ethernet GPU drivers. So they use a user space as a really clear dominant. But in case of driver, the NPU drivers, is the driver is handling the scheduling part. So this scheduling is not like a conventional scheduling what happens on the edge. This scheduling is a model specific basically. It could be the stateless or stateful based on the requirements of the AI workloads, or the inference parameters. So this scheduling
and how many tops you are operating for the NPUs, and what are the precision, like whether it is int8 or int4 or FP16. All other parameters are these scheduling happens on the NPU driver, which is something missed on the driver axle. So that can eventually add it in user space also for basically. So even if you are running the tensors on the Excel driver, we are not full-fledged using the all the tops in a consecutive way or simultaneously. Maybe specific tensor we are right now using because of the compatibility issues with the TensorFlow right now in the user space. So from the vision and sound point of view, you can still use the driver Excel up to some extent, but in case of the vendor NPU, these are all these classified based on the SOC companies are keep releasing their SDKs with new models of workloads. So those are well matured to deploy in real time. So the last one is the LLM viability, which is constraint, as I mentioned about the Excel, which is missing both in terms of the just giving the IOCTL and FOP. That's it with respect to the existing DRM node. A lot of workload need to be happen in terms of the job model execution, the scheduling, and even the SRAM allocation for the specific NPU workloads, both in terms of the tops and other stuff. So that will work with the NPU on the vendor's NPU because they have seamlessly integrate their own stack, both in terms of the user space toolchain versus the one NPU drivers, what they are doing basically. So this is mostly the last slide from my side. So what would be the first class NPU? As I mentioned about the verdict, and I'm not trying to what you can say conclude anything here, but what I'm proposing, like the workloads are still starting in early stage, but there are deployments happening on the edge, even on the cloud side as well. But most of these deployments handled by using the obviously the vendor NPUs. If they wanted to have a seamless integration with upstream kernels to use these NPUs, we need to have a job extraction or execution in the context or on-chip visibilities and persistent scheduling. All this needs to be happen, which is something early stages like what the DRM has happened. It could be thinking like an opportunity for the community. At the same time, it would really a big job even for the kernel to handle the variety of NPU classes, as I mentioned about the training, inferencing, and on-demand learning and other stuff, which eventually potential liability even for the changes on the kernel architecture. Based on my experience with Edgewell so far, I was thinking basically. So on and on, the existing LPU accelerator or NPU subsystem has hidden the gaps with vision, but it is exposing the gaps for the LLM or LLM workloads, even on the edge or inferencing. So that's mostly from my side. Thank you. Any questions, please let me know.
Yep. Hi, thank you for the presentation. So you're making a parallel with other sort of hardware that exists that is supported in Linux. And the evolution of a lot of that stuff came because there's a bit of commonality between these things. So like you can sort of say, well, one GPU does this, the other GPU does that, but more or less they share some characteristics. Have you sort of studied like the commonalities between the NPUs that are out there and sort of drawn maybe a matrix of, okay, here's 5 NPUs and here's what they share, and therefore we can sort of maybe infer what the kernel should provide in that regard?
So what I understand so far with my experience working with the real loads, like most of the NPUs from the vendor NPU drivers, they need to use the DRM in their persistent area, because DRM is very what you can say very advanced stage right now. So they use for DRM for the jump buffers, DRM buffer handling and fences. But what they are taking out of it, like all these job models, scheduling their NPUs on chip memories, because those are exclusive for their entities. Say for example, Axelra NPUs has their on chip on memory entitlement. So that particular stuff, those are specific to their vendors. So they still use the DRM capabilities and the Linux capabilities, both in terms of the gem and diversities and the DMA buffers. But these specific stuff with respect to their NPUs, they're handling as a separate vendor drivers. I've seen both in the Arc NPU, and even I'm trying to read the Qualcomm QC6490. They are also doing similar stuff of handling these NPUs on their own proprietary stuff and using some kind of a DRM and other subsystems. And even the DPEX I'm right now studying on their NPU drivers as well. So they still they create some kind of a tensors on their own with their own algorithms as a separate by integrating the existing DRM.
If I flip the question around, I mean, if you disregard how they're doing it right now with Linux, how much commonality, in your experience, maybe you don't have a chart for that, but I mean, how much commonality do they actually have in terms of functionality? I mean, are they comparable in terms of feature set, or are they completely different and there's no commonality between them?
There are commonalities. The feature compatibilities remains the same. So, say for example, if I run any visual model, I need to run the NPU. I need to say similarly use a different NPU to run the same vision model and do the computation benchmark and other stuff. So the workflow or the propagation towards from user space to kernel to use these NPU drivers remains the same. But the only thing is like how they create, how they schedule the jobs, and how they execute inside the NPUs, and how they allocate the memory on their SRAM. Those are the critical differentiators. Other than this, there are the commonalities each and every workloads with respect to their NPUs versus the other NPUs.
All right, thank you.
Yeah, thank you.
Thank you. Looks
Thank
like
you.
there are no
Thank
more
you.
questions. Thanks for taking the time.
Thank you. Thank you.
Sense to start instead of just keeping the. Come on. What happened here? Yeah. Oh. Okay. I just woke up. Yeah, he is done rather early. No. Okay. Let me see. We need to take presenter back. What? What did he?
We ended the presentation.
No. Gosh. No, did he end the presentation?
I think we have so much time.
I hope he didn't. Don't know what he did.
Okay.
Or you can just use my laptop. It just lets me since you have time.
Yeah.
Don't know why.
So should we wait anyways?
We are gonna probably wait anyways. Why? Yeah.
We'll start at 5:45.
Okay, I'm just I can join. I mean, if everybody's ready, we can do this. Not a problem. I'm just starting. Because I was thinking some people might be timing themselves and then, let me see, all A1. No, not that one, right? No. Yeah. So we are back in there and then take presenter. And so, okay, you are set at this point.
Go to the first slide. Is there a way to get rid of this white box? 'Cause it's blocking my,
What is
like this white box up here. It blocks the
I-
text.
I don't know.
Probably not.
Yeah. Click on that thing. I mean, just leave that alone and just, do the presentation.
Okay. Yeah.
Or you can pull up your slides again to see if that works.
Well, I don't think, I think it's just
Yeah.
always there.
Obviously. You can leave it since it's.
Yeah.
Demo, I think you're.
Oh, it's just for me though.
Oh, it just does for you.
Yeah.
That's what I thought. I know you want to do demos and.
Yeah, that's fine.
I mean, if I take it on yours. Show me how. Yeah. Just hold.
growing trend right now. Well, I think it's been busier, but there's a lot of
And it's very I think probably it's safe on wow.
You want the picture now or in the middle?
Just while I'm talking. Okay. Thanks. Okay. Okay. Can you guys hear me? Okay. Well, thank you guys for staying and those who came in. So today we're going to be talking about a modular approach to power management fuzzing. And thanks to my colleagues, Dr. Tuba Yavuz, Abai Yang, and Victoria Siver for help advising me on this. And of course, the NSF and FIX for funding. So let's start. All right. So brief overview of what we're going to talk about. I'm going to go over the motivation and background of fuzzing in general, why this is an important thing to do, and then some initial challenges of implementing this system. Then our first implementation, which is actually using S2E in a virtual machine, which didn't actually give us the results we wanted. So then we moved to a physical architecture, which is a separate physical machine that we're fuzzing separate from the host device. Demoing these things and then summarizing and going over future steps for this. So what problems are we looking to solve? Well, for power management, the low power states when we're going into suspend are notoriously difficult to kind of understand in crashes because all of our logging mechanisms are turned off because we're in suspend, right? So it's kind of like a black box in situations where we have issues. And so we're trying to uncover that more, especially things with system interdependencies, race conditions. These things are especially hard to understand. There are some like tracing and failure analysis, especially for like drivers, but no fault-based exploration. And so that's what we hope to fill with this. So our goals, we want to create a fuzzer that explores the PM bug space to give us an understanding of these faults. We want it to be modular so we can swap out the mutator of the fuzzer so that we can, if you want to change the way you're fuzzing, you can do that separately from the actual architecture, and you can do the target as well. We also want to be able to make sure that we can reproduce our faults. So let's say we have a crash, we want to make sure that we can then repeat that. So we want to make sure our sequence is saved from a crash. Of course, understand low power states, what happened there. So we need to have some tracking and coverage collection there. And so to start with this, we're targeting power management and USB interactions for race conditions, especially remote wake up, which is, when you have your laptop and you hit a key press, it'll wake your system up from sleep. So we're kind of using that as a starting point, very simple. And then so background of what a fuzzer is, if you're not familiar, this is essentially, we normally have a small program and you have inputs to that program, right? And the fuzzer is basically supplying an input to that program and try to maybe give it a malformed input to see what will happen, right? And try to understand and hit every little branch in your program. And then it'll output some coverage of what actually happened in the program, right? And then we'll feed that back to the fuzzer so we get some coverage guided fuzzing and it's intelligent so that the next input can be mutated to explore the space more intelligently. That's essentially what the fuzzing system is. And in this case, we're targeting the Linux kernel itself, and that's our binary. So with that in mind, just talking about the importance of this. So these are like real power management and USB related bugs that have been recently patched. So these are still real issues are being found on this. So in January last year, there's a patch for DWC3. Suspend was blocked from an incorrect flag. And then in August 2024, there was a incorrect polling occurring for the DSTS link state, which is essentially, connection between a gadget device and your host. The DSTS link will inform the gadget of the power state of the host device. And so the gadget was actually polling for this. And when I did a remote wake up, it missed the timing for that notification. And so the gadget thought it was in one state while the host thought it was in another. So like the suspend and resume didn't actually occur properly. And both you'd see in the demessage logs as like saying, the host would say, is USB cable bad? I cannot wake this device up. And then the gadget would say the remote wake up failed. And so I actually was able to encounter this bug myself. And so I reproduced that and had to update my kernel to get around that. But this is just emphasizing that these are, real issues that we want to find, and they're still relevant. So having a fuzzer to explore the space more effectively is beneficial. So some existing kernel fuzzing solutions and why we can't use these solutions for this problem. syscaller is a big one, and we've heard a lot over the past couple of days. There's other things like KFL, Unicore, and of course syscaller you can use for USB fuzzing. But all these architectures, they don't have in mind when you turn off your system. I mean, that's kind of like a big architectural decision. So, I mean, I actually tried to go into syscaller and looking to see if I can leverage some of their tools for the system, but it just doesn't make much sense. You have to really start from scratch because if you're suspending your device, that's something you need to account for. And then also we've discovered that virtual machines just don't have enough power management emulation, and all of these things are going to be running in virtual machines. So that's the other thing. So our first challenge that we want to discuss is low power coverage. So low power meaning that while we're suspending, all our other logging devices are turned off. So how are we going to understand what happens if we crash, right? So existing tools, you have like these configs, you have trace resume, and like this is actually pretty interesting using the real-time clock to like store the hash information of a driver. And so this will give you an understanding of which driver was called last in your crash until you can understand, okay, this driver caused my issue. But there's not a lot of deep analysis or any kind of fault space exploration. This is some basic tools. Some other things like pstore and kdump or other serial ports, like the logging mechanisms, these are all going to stop. Like you see in the bottom here, if you start suspend, at some point, all these tools like kdump are going to lose functionality while we're suspending. Like at some point, they're going to turn off, right? And then let's say we crash after that, there's going to be some missed coverage. So how are we going to fill that gap? So I skip over that. I talked about that. But so initially, I wanted to use VM and understand that with a virtual machine, you're hosting that kernel and you can externally understand what's happening, right? So you have the basic blocks that are running in that kernel binary and that virtual machine is hosting it. So you can see what it's doing exactly, even if it's what doesn't matter what power state it's in, right? You know exactly what's happening, so you get full coverage. So that was the plan initially. And so instead of doing this from scratch, I was like, okay, there's gotta be something that's already doing this, right? And that's where S2E comes in. So if you're not familiar with S2E, it's like a symbolic execution platform, which is like a way to fuzz a program and find bugs. So symbolic is like instead of having concrete inputs, it's actually like variables that can change. It's kind of interesting, but in this case, we're just using normal concrete execution and just leveraging S2E as a tool that already implements our coverage of basic blocks just to get like a proof of concept without having to do the legwork ourselves, right? But there's obviously a trade-off that there's a lot of overhead added from using this program that has all these other tools added. And then, so our second challenge would be implementing remote wake up. So this is what we're going to be using is an input device, because we have to be a separate device, right? If we use the same device on the computer, it's going to be suspended and it can't give you that wake up input, it has to be external, right? So we want to have a separate physical board. And there's some options for this. So Face Dancer is like a USB emulation tool. There's like hardware and software support. There's actually a lot of different configurations, a lot of complex things you can do. But Raw Gadget is a similar thing, gives you on-the-go support, but it's a lot simpler. And there's already like a keyboard example that you can just leverage off the shelf. So we decided to go with that. And we had to modify that a bit to give it the remote wake up actually happening, because it supports on the go, but it didn't actually, the example didn't do that. So we had an IO control call to basically, it would detect in the DSTS link when our host goes into suspend, and then it'll be able to initiate that wake up response automatically. And this is our emulated keyboard, right? And we also had support for like more key press events, because it was a basic example initially. So our findings from that are that 2.0 actually on the go does not support wake up, which is interesting. So we can't use Raspberry Pi Zero, which we initially wanted to. We needed a 3.0 device, so we used the Rock Pi, and that actually gave us the reproduction of that DSTS link bug, because the Rock Pi doesn't have as much kernel support, so it was using a 5.10 kernel without that patch. And so we ran into that, and then so we moved into BeagleBone Black, which is the newer kernel, and so then we'll be able to get remote wake up happen consistently and work properly. So now we understand that background. Also want to mention that for our fuzzing campaign, we're going to be using libafl, which is if you've heard of AFL++, it's like one of the bigger fuzzing programs. So libafl is like a library that you can use. So this is what we wanted to use because we wanted to have a way to have the mutator and the fuzzing very separate from our actual inputs, because normally your fuzzer will directly harness your program, but in this case, our inputs need to be externally sent to a raw gadget like device, like a keyboard emulator, and also our kernel. So we have to handle that ourselves and just have the mutator be a separate entity. That's why we use the libafl. So a finite state machine of how this fuzzer is working. So we initialize our corpus. So like a corpus is like your first test cases for the fuzzing machine. Then we're going to start up the kernel under test. So that's what the cut is there. You see that that's what the kernel we're testing, obviously. And then once those are set up, we'll get libafl to generate our first test sequence, and then the kernel is ready. We'll start executing each index, and so the libafl is just generating bytes that we're going to interpret as like if this is an ASCII character, we'll send a key press event, or we'll do a remote wake up, or we can also define things as a suspend event or another power management related event. And so based on the index value, we'll do a power event, send that to the kernel under test, or we'll do a key press event. And then we'll just keep looping and doing that. And then once we finish that defined sequence, we'll make sure that the kernel under test actually finished that, so that it ran what we wanted it to do. And then if there's an issue, then we check, okay, is this kernel under test not responsive anymore? Was there a crash, right? And it's checking for this while we're working as well. And then if there's a crash, we know we found what we wanted. We got our goal, and we'll dump the input sequence so we know what caused it. We can reproduce it. And then we restart the fuzzer as well. And then we also have like a soft reset in there. So if, let's say, the kernel is still responsive, but the sequence didn't go through, maybe there's just something on the fuzzing side, the kernel is still responsive. So we'll just send the sequence again. And if that happens where there's a failure 3 times, we'll do a hard reset, right? So here's like a high-level architecture. I know it's kind of small. I was hoping for more screen real estate. But the red side here is the host controller. So high-level idea of this is that we have S2 in the bottom that's going to be giving us our observation of the kernel under low power environments, because that can access the basic blocks, right? And then we have our mutator coverage, and all this stuff is independent. So that libafl mutator on the top is just interfacing with 2 memory maps. So you have the coverage that comes into the mutator, and then you have the sequence that's an output. So you can easily just swap that out with any other your own C fuzzer that you want, and you can just change the behavior that way without having to change your whole system. And then the advantage of this is that VMs provide that safe, consistent start, but of course we have this problem with the functionality, which we'll talk about in a moment here. But just to finish with this architecture, because we'll still be reusing this later with other design. So we talked about that's libafl there. It's creating our byte sequence that's going to be representing USB events and power management events, and it's going to be mutating based off of our coverage that we're getting from S2E, right? And then we have the input processor here that's taking those outputs from the sequence generated from the libafl, and then it's actually giving those to the appropriate areas, so the gadget device and your target. And And then we have the gadget device itself, which will just be sending the remote wake-up events. So that's our BeagleBone Black external hardware. And then we have, so the S2E itself here, that's going to be hosting our kernel and giving us the coverage that we were talking about. So talk about those limitations now. So this is like the ideal setup where we can monitor those basic blocks, but unfortunately, when you try to set up this power management in the QEMU virtual machines, they don't actually support a lot of the functionality we were looking for. So if you do a basic suspend and resume, that'll work. But if you want to do a remote wake up, that's just not supported at all. Like you can try lots of things. Like if you pass through the whole hub, like the whole entire USB hub, right, with VFIO, the power management event bits, which will determine if the kernel sees that hub as remote wake up capable and thus will not suspend it during suspend. Those bits are actually masked in the QEMU code. They're just like, yeah, we're not going to implement this because, I mean, they don't really have a good reason to, so that makes sense. And the other things are like ACPI tables. They're not really implemented. You can do it yourself, but just all of this backend stuff is not implemented for QEMU. And so we have to just move on and try with a other real hardware device, right? So here's kind of like a demonstration of that working. Let's get this. Okay. So on the left here we have, that's our program that's running the fuzzer. This is our QEMU instance starting up. And the other downside of this is that our QEMU is going to take a really long time to load all this because we have to, with S2E, you have to manually add all these things to the image afterwards. So it takes about a minute and a half to start up this fuzzer. This is a big downside of this, but if you implemented this without S2E, that would speed things up. So I'll skip ahead here. And hopefully it's not too small, but you'll start seeing like key presses just run across the screen on the right there. Yeah, you can see that. So that's coming from our gadget device. And again, this is a basic example, but so now we're attempting to suspend, and that's also going to take a while with this VM. And our new physical architecture, it's a lot faster. But if I skip ahead, it takes like 20 seconds. You see that QEMU turns off, and then we'll automatically turn it back on, but it's not through remote wake up. We're actually just using the QMP socket. And that's kind of the other interesting thing is that to wake up QEMU, there's no like, when you wake it up, it actually goes through a QEMU system wake up function call. And that's just kind of tugging on the kernel saying, wake up, but it doesn't know what happened. Like the actual traditional like power management paths that would be like, in your API table, all that backend stuff is just kind of gone over because they don't want to deal with that, right? So, and then this will, it's resumed again, starts fuzzing more. But obviously, we're lacking a lot of things here. And this is also showing, we're looking at some specific functions, some coverage there, but we'll also have a better demo with the physical architecture. So keep moving on here. All right, so kind of hammer this in, but pros are that good monitoring, but cons are that power management is not sufficient, and there's some overhead issues, but you can solve that if you implement it yourself from scratch. So now we got to move to a physical machine. There's going to be some new challenges, right? How are we going to approach that? So the thing is, we have an external hardware device, right? So completely separate. How are we going to like get coverage from that and like bring it back to our host device for in-loop coverage? And how are we going to get this coverage if there's a crash? There's a lot of questions here, right? So we're going to be using ftrace for in-loop coverage. So hashing like the caller-callee pairs to get a basic idea of what was executed at the system level, and then use that for our fuzzer campaign. And then we're going to be using Intel processor trace and RTC to like work together because Intel processor trace will get suspended still, but RTC will not. And actually, I was just talking to Stephen Rostedt about this. And so there's actually a lot simpler method here. Instead of having to use all this stuff, because in this previous talk, they were talking about reserved memory. And this reserved memory, if you use a soft reset, will not actually get wiped from your RAM. And so we don't even have to worry about this RTC, the Intel processor trace. That's kind of outdated now. We can just use ftrace and then store it to reserved memory, which will not get wiped unless you don't do a soft reset, which means the soft reset just means that you tell it to restart without powering off so that the RAM will stay alive, right? So we can kind of skip over that. The other issue is to reset the device. With a virtual machine, you kind of easily control that, right? But so here we're going to be, right now we're using like a USB relay physically connected to the reset pins of we're using like Intel NUC. And there's some other tools like my colleague was talking about, adaptive tracing or management technology from Intel. So it's like a kernel level remote control of a device. So it's kind of interesting for future directions, a little cleaner than a physical reset connection, some kind of remote management tool that will be able to detect a crash and restart it if the kernel panic doesn't go off. And another thing is we want to be able to track event completion. In the virtual machines previously, we were able to access the basic blocks. So we know exactly when a key press happened or whatever happened, we knew. You'd be able to put in a plugin, you could track that easily. But with an external device, we need a way to track all these things, right? So I have a dev script to just monitor whenever there's a key press, we'll log that and put into a memory map, kind of get a counter going. And whenever there's a suspend event, we'll also log that. And so that's how we're keeping track of those things. So now let's go look in the physical architecture here, a little bigger. But so it's kind of the same thing. There's some similar things here in green. So this gadget device and the basic architecture on the host side is the same. So we still have the libAFL as the fuzzer, and the input processor is a little different, but it's serving the same purpose, right? So now let's talk about the new things, which you kind of already talked about. So we have ftrace here. We have a program that's hashing that ftrace into a map, and then we are using like SSH to like send across the information in block updates. So we're not sending it all at once because obviously it's a lot of throughput issue, but we're just scanning that map for any updates and sending those to the host so that our fuzzer can actually get that, intelligently mutate new inputs. And then here's kind of our failure analysis, which we're going to replace now because we've learned new things, which is great. And then, so this is our control flow, like I talked about. We need a way to log what actually happened. So we have the PM logger, the evdev tracker, go into map. And then this event counter program gets an input from the host side that tells it, okay, we're starting a sequence of 36, and that like we want to make sure that 30 characters get sent and these suspend events happen. And so then this event counter will wait until that happens and then signal it so that it knows when things are done and if they need to wait for a crash and understand basically if the fuzzing loop is finished. And then we have that relay to issue the reset. So pros are that we have the full power management support. We don't have any kind of remote wake-up issues. There's this real-world stuff, kind of cool. There's no emulation involved, which like almost all fuzzers have, which of course they have a benefit of higher speed sometimes. So there's some cons of higher complexity. You saw the diagram there, and there's more synchronization you have to do with another machine. Not as safe with a virtual machine because you have a consistent start point, but we don't expect like too many issues. We're not like fuzzing system calls directly with really bad malformed inputs. It's more about focusing on timing and race conditions. So ideally you shouldn't be like going in and breaking your device, but of course you'll like kind of have to have more backups since you don't have a virtual machine. And this low power coverage, we said it was more difficult, but it seems like it's not. So hopefully I can come back and use ftrace and then it's not an issue. Because we were thinking we have to use this RTC, which is tiny and all these other problems, but with this new memory understanding that it doesn't get wiped, that's pretty awesome. So now we can demo this physical design here. It's only 1080. This is a lot faster startup. So we have the laptop here. That's our host controller device, right? And then it should pan over here in a second. So that's our kernel under test. That's an Intel NUC. So that's what we're actually fuzzing. And then that's our BeagleBone Black. So that's going to be giving us our key press inputs and our remote wake up. And that monitor on the left is showing what the kernel under test is doing. So then we'll kind of skip ahead of the quick setup. So that setup takes a while here because ftrace got to load functions. You can see the key presses go across again. And then, we do a suspend. We see the screen turns black. And then this will automatically turn back on. There's no like tricks here. This is real remote wake up, which is pretty cool. So we can kind of really see these USB emulation working. The USB emulation of the BeagleBone. And then, this will take a little bit and it keeps setting, you can't see the keys because it's no login screen, but it keeps setting these key presses and USB events. And the idea is that we, extend this to have multiple devices. We can have, control the timing very explicitly. So like you can really say, like, okay, we suspend and then within 2 seconds, we send this remote wake up or we send these malformed inputs while we're suspending, what's going to happen, right? So that's the idea. Another thing is like added some robustness of, like if there's a crash, I'm showing like I'm unplugging the Ethernet here, so which will not which will make it so that the host no longer can communicate to the device, and so it'll think that it crashed, and then we'll see that here it'll detect the crash, and it'll actually just restart the whole thing. You don't have to do anything. Right now, I don't have the USB relay connected just because of it's a little messy, but so it's doing that hard recheck. It says, okay, you see that SSH failed. We can't connect to it, so we got to restart the whole fuzzing system. There's some kernel crash, right? And so it's also dumping our input sequence. Okay, that's a solution. We want to look at that later for fault reproduction, right? And then you'll see that it starts the whole input processor again. And I'll skip ahead, but it'll start fuzzing again without having us to do anything. Yeah, so you can see the key presses are going off again. Suspend will happen again. So just showing that it's got that built in. All right, so what are the results we got from this? So we only did some shorter fuzzing campaigns because we're still like in the phase of building the system and working out like how to extend it for better things. So one of the bugs we found is actually I think it's probably more of a Red Hat bug than a kernel bug, but after this fuzzing, like if you try to type in your password, like the keys will just disappear. Like you can't log in, so you have to like use Control-Alt F1 a couple of times to like refresh the Red Hat screen, and then like you can log in again. But kind of interesting. And then we reproduced that DSTS link bug. But the plan is, to improve the system by adding more timing control, because right now it's still pretty basic. But add more timing control, add more other devices for more race conditions, and then we can run some longer campaigns and look at the traces. Get better understanding of what crashes are happening. So conclusions is that power management code can really improve and benefit from more fault space exploration, especially like in these low power states where we kind of don't know what happens a lot of times when things fail. Of course, you can trace things when it works, but we don't really care. We know what happens then, right, when it works. So existing fuzzing solutions can't really target this kind of thing because it's a really unique scenario where you're turning off your whole system. So everything else will turn off. We also learned that virtual machines really don't do as much power management as a lot of people might expect. With ACPI tables, power management events just being masked. So we got to use something else. What am I contributing here? So this fuzzing setup is going to be real device and kernel interactions. Like there's no like, oh, is this going to be a real situation? Like this is literally a computer connected to a keyboard, right? These are real things, and you're getting this no guesswork here of will this be a real issue. A lot of synchronization exploration, which I don't think a lot of fuzzers do, is taking in system level account of all these different things, like a power management event, and then understanding different timings of events with devices. It's pretty unique, I think. And then, of course, we have that low power state coverage. So it's not as unique to this, I guess, because you can use ftrace with just normally, but this will give us a better understanding of what happens in crashes scenarios. And then some features are, timing control, failure recovery from crashes quickly, and having your fuzzer still work. And then you have the modularity of being able to swap out your fuzzer easily so that you can change that behavior or the target without changing your fuzzer. That way you can kind of keep things simpler. And then so here's kind of like overview of the architectures just to recap. So, based off of for the low power coverage, so that's kind of void now because we know that ftrace is a little bit easier. We can actually use that. So I would say that they're both easy to get low power coverage acquisition, but physical device is a lot faster just because, suspend is not something that you want to do in a virtual machine. The kernel state safety is better in a virtual machine, obviously, because you have that snapshot. You can always come back to that. But of course, we're focused on power management, so that's why we kind of go to a physical device, because virtual machines are not supporting that. So future work, as I said previously, we want to do some longer campaigns. We want to get more in depth with the trace analysis, because right now I was looking at Intel PT, and there's a lot of information that you really have to know what you're looking for to kind of understand that. So kind of need to spend some more time on that. Look into remote management technologies to, instead of having a physical wire connection, so it's a little bit easier to set up. And then also improve our coverage. So instead of using RTC, because like right now I actually did not implement the RTC, I was just using Intel PT because that was proven already. but we don't need to use that. We'll just switch to ftrace because we discovered that will work better. And then also like use EPBF to like add more specific coverage points for like power management event, like functions that we're really interested in, right? And then the real focus is to add more devices. So you can have multiple devices, USB devices. You could have, I was talking to someone that Bluetooth apparently has a lot of issues with suspend events. So you could have like an app on your phone that this fuzzer can control, and then you can send Bluetooth communications to fuzz that as well. You can do any kind of thing with this real system as long as you are able to, somehow control that input in a programmatic way. So I want to give a thank you to my colleagues, Dr. Yves, all these people I said earlier, and of course some other people that helped me online. Alan Stern helped me with the on-the-go thing, USB emulation. Andrei Konolov and SysCaller helped me with when I was trying to work through some of that stuff with USB emulation and trying to look into that fuzzer. Vitaly and S2E helped me a lot with understanding how to add those plugins to S2E to get the basic block coverage I wanted. And then Dominic and libafl helped me understand, because I didn't know Rust. I was like, okay, I got to get some help here on how to get this fuzzer to work. So thanks to those guys for help. And so any questions, please send them my email, or anyone here have any questions. So thank you so much.
This is cool. like this is a problem I face every day right now.
Oh, really? Great.
Yeah,
or not great. Great for me, but
yeah, no, I hate it. So I think I'm hitting the keyboard lockup bug that you're describing for Red Hat, where
oh, really?
Yeah. So I'm like, I'm in suspend.
Yeah.
I'm trying to resume, and then like the trackpad works, like the mouse cursor moves, but I can't type anything. It's like the keyboard's completely gone. Is that?
That's not exactly what I had. I actually had, you would be able to type, but the keys would immediately disappear. Yeah, like you'd see them go across and boop, it would like clear it. But like that's interesting. It just shows that there are these weird things that happen, and it's like a lot of this like hardware dependent, probably, right? Based on your configuration, and I think that's a lot of the powerful thing about this is that you can put on any hardware device and test that and like test that setup, because a lot of these fuzzers right now are focused on like the individual system calls, right? You have like, okay, we want to make sure this function works, right? Based on any input, but it's not talking about, okay, will this configuration work with all these little devices, like this edge case here with, okay, you have this Asus laptop and this Logitech keyboard that's like 20 years old that we never thought about, right? But this is actually going to be a edge case for this timing that's actually pretty important,
So this is like, you talked about emulating the USB keyboard, like, okay, yeah, that's fair. Like you want power managed to work on your Intel NUC, but like in my case, like it's a ThinkPad, right? So is it like on ThinkPads, is the keyboard the same internally? Is it USB internally? Do you
So usually I think keyboards are PS2 internally. I think that's for the most part. I'm not sure 100% of that, but like you could still like fuzz your laptop with like you can just plug in a USB keyboard to it and see if it would do the same thing, or like maybe get a PS. No, if you did adapter, it'd still be USB.
Right, but would the code path be different for PS?
Yeah, for sure.
Yeah, so that's like
an interesting,
that's the code path I want to exercise.
I'm more curious about, that's good questions. I'm more curious about failure mode detection. Like, are you looking in the ring buffer for oopses, and like, how are you detecting failures?
Yeah, so right now I'm just looking at if the kernel crashes, but that's a good point. Like I'm sure there's some other things. So you're saying like in the ring buffers, it'll tell you if there's other errors that aren't causing fatal issues that I should look at?
Yeah, like if you throw an oops, that might be a sign, but I'm just in generally, failure detection, I think, I'm fascinated with that with SysCaller too. Like they're way ahead of this, but how you detect when you have a failure so that you can just like let this run all night long. And
yeah, that's a good point. So I'd have to look into, all the different levels of failures that can be thrown and find a way to, well, I can easily, if it's not a kernel failure, then you can still communicate normally, I would say. I mean, it depends on the failure, but
maybe I've seen systems that you can ping and everything, but that's it.
Right now, I'm basing it off like timeout. So like if that kernel sequence if that testing sequence we send to the kernel under test doesn't finish, like you can change the time, but you can say, let's say 10 seconds after you finish it on the host controller, right? It's like, okay, something's not right, obviously. And then you can check, okay, is the kernel responsive, like network wise, or you can do some other tests, but if it's not, we'll just call it a failure. That's how I'm doing it right now. But yeah, it's probably a good idea to look into things that aren't completely crippling your kernel, but that could also be interesting.
Yeah, and I think you can hook into that too, so you can record that information. Yeah. Excellent. Nice work.
Thank you.
Yeah.
So the other thing that so like there's the opening and closing the laptop, right?
Yes,
That's suspend, resume.
Yeah, that's in the ACPI table as a power management event. Yep.
Yeah, so that's like the other thing I would want to emulate. So I haven't experienced problems yet because I don't even get that far, right? My keyboard locks up. But once that's fixed, I imagine then opening, closing is going to be the next.
So when you have that failure, is it when you're trying to wake it up from the keyboard, or just anytime you wake it up?
So here's one: like you close it, it doesn't actually go into suspend. Like it keeps eating up battery, and then when you open it, then it doesn't, it doesn't resume.
Okay.
Those are the kinds.
Did you like check? Because I know some times you have to manually go in and configure that as a wake up device.
Yeah. So it seems to work. Like I haven't hit that problem yet, but I've had on MacBooks. Like I've had hardware failures. Like I've had the sensor that detects that opening and closing just fail, and so
that's an interesting point. I'm just not sure if anyone has any ideas on how I would be able to like use that as an input, like because the laptop closing and opening and that you can't unless you get like a robot to automate that.
Right.
I don't know how to.
And it's a microcontroller probably inside that's handling that opening and closing. So yeah, I don't know. Well, I mean, when you think about it, it's a micro that's in your USB keyboard, and you're using the BeagleBone Black to emulate that. So so you could emulate the micro using the Black somehow. I mean, I don't know what code you would run,
but like it would have to be like with the BeagleBone. I think you have to use the USB connection. So like you can. I mean, I don't see a way to.
There's
emulate the interface and then internally in the laptop. I mean, maybe you can open up, but the idea is to have it kind of where you can put it on any system easily, right? But that is an interesting point. I'll have to look into how to emulate.
Just my personal problems that
No, but I mean that's a valid thing because I mean a lot of laptops. That's the main thing is for laptops is to have suspend, right? That's the most use case I would imagine. And so like the screen closing and opening is probably a big factor of the wake ups. Yeah.
Thank you.
On one of your slides, you told that testing in QEMU is slower.
Yes.
Could you, first of all, tell us what kind of how slow it is in comparison to hardware testing, first of all? And could you explain why you think it is slower in QEMU? Because my feeling is that it should be, of course, it can be slower, but it should be comparable.
Right. No, that's a very valid point. But so I might have misspoke, but it's not really QEMU that's causing the slowdown. It's S2E, which is hosting QEMU. So it's another device or application on top of it, which is what we're using to because S2E is giving us that block coverage, right? And so we're using S2E to launch a QEMU instance. And so that's giving us a lot of overhead because you have to instrument the entire kernel. And so that's where the overhead's coming from, is where you're you have to build the kernel with all this logging, right? And then you have S2E doing all these additional plugins and functionalities to track what's happening in the kernel. And then there's other things with, a lot of requirements with S2E, with older QEMU versions. So that's where the slowdown is. I don't think if you got a real, if you built it from scratch with QEMU, you probably have around the same speed, I would imagine. Does that answer your question?
Yeah, thanks so. Yeah, makes sense. Thank you. Other question? Once again, great work. Thank you.
Thank you guys. Appreciate it.
I am so glad.
Yes, I appreciate it.
I took a bunch of pictures. So, because I couldn't know which ones you would.
Yeah.
Great work.
Thank you.
Just what?
Just grabbed 3 laptops. I never shut down the other thing.
Oh, yeah, I'll go and do this. I'll bring this and then we will. So I'm just going to,
Just kill it.
I just kill it at this point.
Did you kill it?
I'm kicking everyone off. Yeah. Okay. All right. And